इसे पोस्ट बना दूं।
एक मिनट से बस
मैं बना देना होगा।
नहीं एक्चुअली लाइव नहीं गया ना अभी।
नहीं
हाँ लाइव नहीं लेकिन सारे नहीं आई बोली
रितेश आ गए। रितेश आ गए।
अच्छा रितेश के बाद
So, Alok, I will present my PowerPoint from Google Drive or from my laptop. Okay.
Okay.
हेलो रितेश। हेलो रितेश।
Yes, can you hear me? Yes, can you
Yes,
hear
I
me?
think yes, we can.
Okay, hi Vinay.
Yeah, hi Ritesh.
रितेश।
Yes, can you
Yes,
hear me?
Yes, I can.
Yes.
Okay, very good. Yeah.
Ritesh, you are on each side or central time?
No, so I'm in Washington, so East Coast. Yeah.
Oh, East Coast. So for you it is 9:30.
No, 11:30.
Oh, you are East Coast. Oh, okay. Oh, sorry. Yeah, for me it is 10:30.
Are you in Texas, Vinay?
Yes, Texas in Corpus Christi.
Okay.
So I'm working basically on hydrological models. But this work I did with one of the friend, Uday Bhaskar Gunturu. So on IGP fog. Yeah.
Dr. Ranjit sir, good morning.
morning.
Dr. Ranjit sir from Department of Chemistry, Dalbagh Education Institute, Agra से.
Agra, okay. Good morning, sir. Good morning.
और कैसे हैं डॉक्टर रितेश?
बस ठीक है। ये किसकी आवाज आ रही है?
रंजीत कुमार, दयालबाग यूनिवर्सिटी, आगरा।
अच्छा।
अरे रितेश जी नमस्कार।
We met some time back and we were sometime in correspondence through email.
अच्छा, बढ़िया।
Related to this IGAC workshop or something.
Okay.
Good morning, Dr. Tiwari sir.
Okay, Tiwari नमस्कार।
तिवारी जी कैसे हैं? आपकी आवाज नहीं आ रही तिवारी जी।
हाँ, आवाज नहीं आ रही।
सर आपकी आवाज आप
अनम्यूट कीजिए। हाँ, माइक्रोफोन।
हेलो, हम लोग की आवाज आ रही है?
गुड मॉर्निंग ऑल।
यस सर आपकी आवाज साफ आ रही।
आ रही?
यस सर साफ आ रही एकदम।
चलो।
Ritesh, you can share a screen. Yes, kindly ready.
So should I get started or?
No,
Just 1 minute.
No, just share.
Okay.
Then
Oh, share my screen.
Yeah.
Okay. Right.
तुमका सर YouTube का लिंक दूसरा है ना, सबको हम लोगों को भेज दिया है।
अपने होम पेज वाले में डाल दिया है सब।
ठीक है सर, ठीक है।
मैंने भेज दिया, वो कल भी काम वही करेगा।
ठीक है। इसमें जो जूम जो है मतलब कंटिन्यूटी टॉक्स के लिए, इनवाइटेड टॉक्स के लिए दिया गया है, बाकी सबको YouTube लिंक दिया गया है।
Can you see the screen?
Yes.
Yes.
Okay, very good. So should I stop sharing or?
No.
Okay, leave it like that. Okay, very
You
good.
have to wait for a few minutes.
Right. Okay.
जी आप अब आपके वहां से नॉइज आ रही है।
तिवारी जी सुनाई नहीं दे रहा हमको। तिवारी जी
अपने आप को म्यूट कर लीजिए। हाँ, नॉइज आ रही है।
चलो भी देखते फिर करते हैं।
स्टार्ट कीजिए।
बीस स्टॉक में हो जाएगा तो रमोला जी
Yes, I am here. I am ready.
सर शुरू कीजिए।
शुरू करें?
हाँ सर।
Okay. Thank you very much. And a very good morning to all of you. So we are now here for the third session of this conference, or I'll say the first session of the day. And this is, of course, it's a very busy session because we have 5 invited talks and 12 contributed papers, and it will go up to 1 p.m. So I have my co-chair, I think he's here, Dr. Suresh Tiwari from Indian Institute of Tropological Meteorology, and then reporter Priyanka Srivastava, I think she is from Aries. So I, with the co-chair and reporter of this session, welcome you all to this third session of the online seminar or online webinar. So the first talk, of course, from Dr. Professor Ritesh Gautam. But before that, I would like to say a few words. The invited talk is of 20 minutes with 15 minutes presentation and 5 minutes for the discussion. And the contributor talk is of 10 minutes with 7 minutes presentation and 3 minutes for the discussion. So I request all speakers to keep your talk within the time limit of the 15 minutes for the invited talk and 7 minutes for the contributed papers, so that we can have some time for the discussion, because it's always better if we have an interactive session. Otherwise, if it exceeds the time limit, I have no option other than to stop this discussion session. So we'll skip the discussion session if anybody exceed that presentation session. So I have a special request to all of you. So please keep the time so that we can have, because it's a very long session and we have to complete or conclude it by 1 o'clock. So again, I request all of you to keep the time and make it interactive. Now, with the first talk, before inviting Professor Gautam, I would like to introduce him briefly, because it is obligatory from our part to introduce our invited speaker. And Professor Ritesh Gautam is a senior physical scientist at Environmental Defense Funds in Washington, D.C., where he leads atmospheric composition research, mainly using remote sensing observations. He obtained his PhD degree in Earth System and Geoinformation Science from George Mason University, Virginia. He has published widely in aerosol, remote sensing, and climate effect of aerosols. His recent interests include applications of satellite data in gaining actionable insights for climate changes mitigation. And prior to his current position, Dr. Gautam was a research scientist at NASA GSFC and faculty member at IIT Mumbai. So with this brief introduction, I invite Professor Gautam to present his talk on the topic absorbing aerosols, snow, albedo, and darkening of Himalayan cryosphere. So please, Professor Gautam. Your mic is mute, please.
Can you hear me now?
Yeah.
Yes.
Okay, please.
Okay, very good. Yeah. Can you see the screen?
Yeah, it's visible.
Yes.
No problem.
Okay, perfect. Yeah. So thank you very much for the introduction and asking me to give this talk. And actually, thanks to UC Dumka for even suggesting the topic of my or the topic of this talk. I was thinking what topic to give the talk on, but thanks for the Thanks for the tip. Yeah, I'll just get started, and I have two screens here actually. I'm going to talk about our work on satellite observations of snow darkening in the Himalayan region. The question is why and how to characterize snow in the presence of absorbing aerosols, and also assess their radiative impacts. So as we can see in the satellite image over South Asia focused on northern India and Pakistan, there's a big dust storm, right? And a part of this plume, the dust plume, is reaching elevated snow and glacier ice in the Himalaya, which is already higher than 4-kilometer altitude. So there's observed darkening of the snowpack, something we are not really used to when we think about snow, because snow is remarkably bright. So this topic is quite relevant, for instance, in the case of snow darkening, as it can accelerate snow melt rates, especially over critical regions such as the Himalayan Tibetan Plateau. But Himalayan Tibetan Plateau is not the only region which is subject to black carbon and dust deposition. There are other regions such as the Alps and the Arctic sea ice, which is also subject to absorbing impurities from the atmosphere that are being deposited. So this is one such region, but it is a very critical region, especially when we think of a large population that relies on the multiple rivers originating in the glaciers, Himalayan glaciers. So again, when we think of snow and clouds and look at satellite images like this, snow and clouds appear very bright and white, right? So there is almost a sense of purity about them. And clouds and snow are, as we know, the brightest components of the Earth atmosphere system. And they reflect majority of the sunlight back to space. So effectively, they have a cooling effect on the Earth's climate. But the question is the snow always pure? So in some places, perhaps yes, it is close to being pure, but in many regions around the globe, snow is not as pure, or in fact, not so pure. It can become contaminated by impurities, where the snow and ice cover appears actually quite dark. So I'm showing two images or two photos from, one is from Rocky Mountains in Colorado on the left side, and one is from the Mera base camp area in Nepal. So we can see the impure snow or relatively dark snow. Absorbing impurities, once they mix with snowpack, that can result in warming of the snowpack and could accelerate the rate of snow melt, at least on an intra-seasonal scale. But if there's an ongoing trend of, let's say, an increasing concentration of absorbing impurities in the regional atmosphere, there could be a long-term trend in snow melt rates. So this is another example of darkening of snowpack, which is not just limited on intra-seasonal scale in some areas, but it may also, this phenomenon could also operate in terms of long-term trends. So, for example, there's increasing trends in absorbing impurity in some parts of the Tibetan Plateau, some glaciers that have been measured using ice core measurements. So this is an image, very nice image or illustration from a paper by Susan Kaspari from one of the ice core measurements in Tibetan Plateau. And you can see the annual layers of deposition that are being shown on the left in terms of the black carbon and dust peaks that we can see annually. And then on the right, I'm showing a figure from a paper by Xu et al., which shows this increasing trend of black carbon concentration in one of the glacier sites. So before I get into the results, I just wanted to quickly introduce this idea, or it's not just an idea, but actually a measured sort of concept of snow darkening. So this figure is actually from a famous paper by Steve Warren and Warren Wiscombe, published 40 years ago in 1980. And this gives a really good theoretical background of snow darkening due to absorbing aerosol impurities in snowpack. So pure snow, as I said before, is remarkably bright, reflects more than 80% of the incident solar radiation. But once we have these absorbing aerosols such as dust and black carbon, the snow starts to get darker. The reflectance, specifically the reflectance or the albedo, reduces. So the top panel on the left shows snow albedo as a function of wavelengths. Pure snow is characterized by albedo of more than 95% in the visible bands or the visible wavelengths. But the visible albedo significantly reduces once we have dust deposition starts to happen on the snow. And so this deposition results in a strong gradient across the shorter visible to near infrared wavelengths. So my background is remote sensing, so I'm trying to communicate this idea from this paper, and we'll use this concept later in the remote sensing measurements to try to characterize snow darkening. On the other hand, black carbon is a much more effective absorber of solar radiation than dust, but black carbon causes snow albedo reduction more uniformly, as we can see on the bottom left, as opposed to the dust deposition, which is shown on the top left. And on the right, we can see field measurements showing almost 40 to 50% reduction in the shorter visible bands as a response to aerosol deposition, particularly dust. So just to put things in a broader context over the Himalaya, we all know that Himalaya Tibetan Plateau is among the largest ice cover regions on the Earth. And in recent years, climate modeling simulations suggest significant warming and accelerated snowmelt in the Himalaya due to snow albedo feedbacks induced by dust and black carbon deposition. So on the left, I'm showing a figure from one of Mark Flanner's papers from 2009. So this was perhaps the first paper or one of the first papers to show this localized enhanced radiative forcing due to dust and black carbon over the Tibetan Plateau. And on the right, so these two papers came out about the same time. This is one of our previous works showing this enhanced tropospheric temperature trend around the same area. So we see we actually observed the largest upward trend around the northern Indian region, just south of the Himalaya or surrounding the Himalaya. So, and I'm not showing these two figures side by side to infer any cause and effect, but there could be a possibility that aerosol solar absorption may have amplified the overall greenhouse gas warming signal. So I think this group very well already is familiar with aerosol effects on monsoon, but I just wanted to highlight that the changes in monsoon circulation are not only from an aerosol perspective are not only due to the aerosol radiative warming that's occurring in the atmosphere, but it could also be mediated by absorbing aerosol deposition on snow and glacier ice in the Himalaya Tibetan Plateau. So maybe someone else might be talking about this this aspect in this presentation in this seminar or not, but there are some published studies that refer to this this aspect or the separation of aerosol induced atmospheric warming and the component that's being deposited on the snowpack. So the absorbing aerosol deposition in the Himalayan Tibetan Plateau typically, I would say, peak in the pre-monsoon season or just before the onset of the monsoon, from a dry deposition perspective. And there are not many co-located field observations of snow albedo impurity and atmospheric aerosol measurements. So that's one of the reasons why we are using remote sensing observations from satellite in this work. So I'm just going to go very quickly here, just try to show this pre-monsoon aerosol buildup from April to May to June. This is observed from MODIS and from other multiple sensors. On the bottom panel, I'm showing a Calypso snapshot, showing this elevated and deep aerosol layer just south of the Himalaya Tibetan Plateau. Almost looks like piling up against the southern slopes of the Himalayas. So dust storms are common in pre-monsoon and summer. And this is just an example of a dust storm from June 2003 that I wanted to show just to sort of grab some attention on the scale of dust and the advection pattern of dust above the Himalaya Tibetan Plateau, or the Western Himalaya in particular. But I just want to zoom in and see if you can see these dust-laden snow-covered peaks in the Western Himalaya as part of this dust front. So I'm just going to zoom in another time, and it clearly shows these darkened snow peaks. This is one more zoom. So it's also interesting to see that the valleys are getting filled up with the dust. So there is intrusion happening from the Thar Desert and neighboring desert regions. So there is a massive amount of dust influx going on that we can clearly observe in these satellite images. So this is another image showing the shortwave reflected flux at the top of atmosphere from the Cirrus satellite observation. So there's a large difference of about 200 watts per meter square between dust deposited snow cover, which I'm showing in the circle region, and a relatively clean snowpack, which is basically north of that. So the higher the colder colors correspond to when the dust deposition resulted in reduced fluxes, and north of that circle you can see where dust is relatively less compared to the Western Himalaya, where the dust influx is the largest. And the companion time series shows the aerosol optical depth peaking just south of the Himalaya around the same date, 9 June 2003, when this Cirrus shortwave flux observation was taken. So this is a slide from a previous paper showing basically this concept that we saw initially in Warren and Wiscombe's paper. And what we did in this work was to try to sort of mimic that, or see if we can mimic that observation of dust deposition on snow using remote sensing measurements from space. And in fact, we saw a very similar measurement because it's very consistent with the theory of dust deposition or black carbon deposition on snow. So I'm showing here the spectral surface reflectance for snow-covered pixels from MODIS data over the Western Himalayan region. And the reflectance in the blue band particularly reduces associated with absorption by the dusty snowpack, especially in comparison to the red and the near infrared bands. So this contrast results in a strong spectral gradient, similar to what we saw in the theoretical results. Next slide. This is a comparison of the spectral shape before and after the dust event. So when the snow appears cleaner before the dust event, the visible to near IR reflectance is relatively flat, in contrast to after the impurity or the absorbing aerosol has been deposited. This is trying to characterize the intra-seasonal variation of snow albedo or snow reflectance in response to absorbing aerosol deposition. And I think the main part to highlight is the reflectance generally reduces from February to June as the transition occurs from winter to spring to summer months. And this results in a near systematic decrease in the overall spectral reflectance from, let's say, the blue band, which is centered at 470 nanometer, to 2.1 micron, suggesting the progression of snow melt and snow aging. So here, the snow aging and the progressive snow melt results in the coarsening or the large, basically the snow grain size becomes larger. And that also reduces the reflectance in the longer wavelengths. So the wavelengths which are longer than 1.5 micron. And the reduction at shorter wavelengths due to the accumulation of impurities. So this is happening at, for example, the 0.47, the blue channel. So anyway, so these are details, and I probably should move forward in the interest of time. But this is the physical basis of how we can, we have sort of demonstrated how these satellite measurements or remote sensing measurements can be used to characterize the different types of impurities. In this particular case, it's mostly dust. So I just wanted to compare these results with a paper by Patrick Gienot, who is a glaciologist in France. And they made measurements in ice core measurements in the Nepal part of the Himalaya. And so this plot shows the various tracers and dust and black carbon concentration in the ice core they drilled in the Himalaya. So basically showing again the annual layers of deposition. They found the largest dust signal in the year 2003, which is actually consistent with our satellite-based study in the last decade. So these ice core data are very limited, just point-based and sparse around the Himalaya. But this particular case study is a really very in-depth case study where we compared our results from the MODIS analysis and found that generally good agreement. So I just wanted to also show you some recent work that we have been doing using other satellite sensors. So for example, Landsat. So this is much higher resolution, actually an order of magnitude higher resolution than MODIS. So this is 30 meter by 30 meter. So you can see the snow structure very clearly, the structure of the glacier and the various patterns. So we can also see this progressive decline in the general brightness of the snowpack from March to April to May to June, as well as the progressive loss in the snow cover that's also happening. So this is really very in-depth from Landsat. So we repeated the work that we did using MODIS with Landsat and basically find similar sort of signals or spectral signature from Landsat. So for example, if you look at the dates that are indicated for June or for May, they are quite contrasting compared to, for example, April, where that particular time frame of early April marks just the onset of snow melt, but really the majority of the snow melt or the dust deposition or other absorbing aerosol deposition is happening in May and June. And I just wanted to also mention that we were also able to retrieve snow grain size using very high resolution measurements by Landsat and obtain this range that I'm showing on the slide. And the reason why I'm highlighting this is that we actually use these independent measurements from MODIS and Landsat and the snow grain size retrieval to also compute the radiative forcing of dust deposition on snowpack. So this is all based on satellite observations and radiative transfer modeling, because we don't have access to ground-based measurements. But it will be nice to have some data to compare with from ground. So this is going to be my last slide, or one of my last slides. that I can go very quickly. And I just wanted to highlight here that we calculated this radiative forcing. So this is very recent work. I'm just finalizing a manuscript on this topic, and so I'm showing this instantaneous forcing due to absorbing aerosols here, and the diurnal mean radiative forcing over the Western Himalaya is as high as more than 40 watts per meter square. But we estimate an area averaged forcing of about 30 watts per meter square during the pre-monsoon season. And this is much, much higher in the Western Himalaya in comparison to, for example, the Karakoram, where relatively much less dust is being deposited. So that's pretty much my talk. I just wanted to highlight a few papers I couldn't really talk about in my presentation, but recently in the past year or so, there have been a number of, well, not a huge number, but at least a handful of some really interesting work that's happening. For example, this paper that used high resolution WRF-Chem simulations showing the impacts on snow albedo darkening. Then there's another paper that looks at black carbon deposition and its impacts on glacier runoff. So this is another really interesting work that's sort of connecting end to end, right? So what's happening at the runoff level, because that's where all the downstream population is being impacted. So this is another really interesting work. Then from the perspective of climate also. So I mean, I would encourage people, if there's interest in the audience or in some group, for them to take a look at some of these papers, in addition to the work that I tried to describe earlier as part of my earlier work. So in summary, our satellite-based study has underscored the effects of dust deposition towards snow darkening in Western Himalaya. And we have developed this method to, I couldn't get into a lot of details, but using this relatively simple gradient of simple observed gradient of across the visible to near area radiances, using MODIS and Landsat data, we were able to characterize the snow darkening, retrieve the impurity concentration and snow grain size, and then feed that into a radiative transfer model to compute the radiative forcing of dusty snowpack in particular. We also tried to do something similar with black carbon, but I think these spectral measurements are sort of more sensitive to dust absorption. And then, like I mentioned, related to the radiative forcing calculations, we observe a much stronger signal in the Western Himalaya compared to the Karakoram. And I'm happy to elaborate why we see that, but yeah, that's my presentation. So thank you very much.
Thank you, Dr. Gautam, for this nice and informative presentation. And I think we can have one or two quick questions. So
yeah, sorry if I went over time. Yeah.
Can I ask a question?
Yeah, please.
Hi, Ritesh. This is Neeraj. First of all, thank you very much for a very nice talk. Can you hear me?
Yes, I can hear you. Yeah, thank you.
Yeah. Okay. I just simple query means when you say it is dust, so dust was there since many years. Now, when you say dust and absorbing species is understandable. But when you say only dust, will it cause the snow melting? Because that was there since long time. It's a natural thing. But we started adding this light absorbing species, black carbon or brown carbon or other things. So that effect, would you like to comment on that?
Yeah. So I think you have raised a very important point, and maybe I didn't clearly define that. So what I tried to show is the intra-seasonal impact of dust. So you're right that dust has been there for many decades, if not centuries. But black carbon, there might be an increasing trend of black carbon. So you could derive an anthropogenic induced signal in terms of a long-term trend. But from the intra-seasonal perspective, dust, I think it is very important in terms of the total amount of absorbing aerosol deposition, because you also have to realize that although black carbon is a much effective absorber of solar radiation, but in terms of the mass concentration, the dust loading is orders of magnitude higher than black carbon concentration, right? So effectively, you'll have larger snow albedo reduction in response to dust deposition compared to black carbon. But black carbon could be more significant in terms of a long-term trend. So I hope that clarifies.
Thank you, Dr. Gautam. I think we can have more questions, but the time does not permit us, because we are already running late by 20 minutes and we have a lot of presentations. So thanks again for this nice presentation. And I now would like to invite the second speaker, that is Dr. Vinay Kumar. And just before inviting him, a brief introduction of Dr. Vinay Kumar is, Dr. Vinay Kumar is a research scientist in the Department of Environmental Engineering at Texas Agriculture and Mechanical University, Kingsville, USA. He obtained his PhD degree in physics with a specialization in meteorology from Pune University. His research work involves the simulation of surface rainfall, stream flows, and prediction of the floods drought over a US river basin using hydrological models. Additionally, he takes a great interest in the meteorological problems over the Indian region. So with this brief introduction, I would like to invite Dr. Vinay Kumar, and he will be talking on the topic fog in the Indo-Gangetic plain, the critical role of subsidence and baroclinic activity. So Dr. Kumar, please.
Okay, can everybody listen to me?
Yeah, it's fine.
And can you see my PPT?
Yeah, it's visible, no problem. Please go ahead.
Okay, thank you, Professor Ramola, for the introduction, and organizing committee for this chance. So this is the work which I completed with Uday Bhaskar Gunturu, and we are going to submit in GRL in a couple of days. So this is a critical role of subsidence and baroclinic activity for the fog over the Indo-Gangetic plain. So a subsidence, in a simple way, you can say the high pressure region, and baroclinic activity, we are referring to the western disturbances. So this is the well-known figure from Terra Modis. You can see the fog is over the IGP and northeast Pakistan, and it is extended up to the Bangladesh also. And it occurs every year for a 1 month, like from 15th December to 15th January. Here you can say for 1 month, but it may go to 25 days and sometimes 35 days also, but this is a climatological. And due to this fog, we all know that there is a higher rates of accidents, road accidents, and train accidents, and takeoff or landing of the aeroplanes over the international airports over this region. And agricultural damages due to fog, and the economic losses. So I think last 3 points are quite enough to do the research on fog. And the last one is the mood swings. Okay, if there is a fog, okay, let's do this work tomorrow. So on mood swings, the Kalidas has written a big book, and name is Ritu Sambhar. So why you should study the fog? Okay, so if you will see the figure over India and Pakistan region, this is an IGP, the fog is keep on increasing since like 1997 or 95. But over other places like Los Angeles, California in USA, and Sao Paulo in Brazil, the fog incidents and events are decreasing with the time. So what is the reason why the fog is increasing over the IGP? So I will talk about the salient and important characteristics of surface boundary layer. And so, at the time, in the time of winter, the troposphere is cloud free, and the region of IGP is under the influence of subsidence, which stabilize the boundary layer. And then the stable boundary layer maintains the turbulence. Okay, and in the winter time, the surface is colder. And the last one is irrigation, which is a source of water, which is local. So these are the dynamical and thermodynamical aspects which maintains the fog over the IGP region. But over the IGP fog, you may find so many papers those talks about the importance of aerosol and fog microphysics. But here we are not talking. We are talking about the thermodynamics and dynamical aspects of the fog due to cloud-free troposphere, subsidence, and turbulence. Okay, and the source of the water vapors. So we will start from the very basic, and this is the graphical view of the Glacier-Clapeyron equation. And Glacier-Clapeyron equation described how vapor pressure changes with the temperature. So this dark blue line, this is the line of what the name dew point temperature line. Above this, you can see the saturation, and below this line is the air is unsaturated. The middle one arrow, it tells about the fogs. Means I want to say that in clouds, the saturation is attained by adiabatic cooling due to lifting. But in radiation fog, the cooling and moistening is attained by the transport of the heat from upper level of the fog layer to the surface, and moisture from surface to upper level of the fog layer. So this is the left side, you can see the Indian region and the IGP plain, and Pakistan and Bangladesh also. This is based on 40 years of data from reanalysis like MERA. So you see over the India region, it is completely red, means vertical velocity, it is downward, while rest of the India is blue. And you can compare this red color over the IGP and Pakistan and Bangladesh region with the Terra Modis fog structure. So we can say that in this IGP region is completely filled with this red color, means subsidence. And over the IGP region, you say right side, the B figure, if you will see the vertical profile of vertical pressure velocity. So this subsidence is not very shallow. It is quite deep. It reaches up to the upper troposphere. But at the same time, you will see the blue curve for the December and January. The moisture is very small and it decreases vertically very sharply. So at the time, in the time of winter, when the winds are from land to ocean, you don't have any source. While in the monsoon time, you will find that all the moistures come from Indian Ocean and Arabian Ocean and Bay of Bengal. But in winter time, you don't have much moisture, and it is prevailed by the subsidence. This is the annual cycle of subsidence over IGP. So you can see in the summertime from May to September, the Indian region, the IGP region is prevailed by the convection, upward velocity, vertical velocity upward, while the rest of the year and all the months, there is huge subsidence. And here in the middle troposphere, the arrow you can see upward, and we are telling that this is due to volcanic activity, that is western disturbance. So some of the surface observations, those are related to fog, like visibility. So you can see the visibility is keep on decreasing, and it is sharp decrease around 1997, and then almost constant. And the dew point, which is related to fog, it is keep on increasing. And that dew point temperature, that depend on the water vapor mixing ratio, moisture, and vapor pressure. While the surface temperature is fluctuating, it is increasing, but it is fluctuating. So here the red line is smoothen, while the low is smooth, for 18 years of span, and it is a local, based on local regression. While the blue line is for the average of 2 months, December and June for every year. There is an abrupt change in the atmospheric and boundary layer variables. So there are many variables, so it will be difficult to explain everyone, but just support to take the case of B. Figure B, we have the high cloud fractions. So this is, you can see the vertical dot line, the violet dot line. See, this is a change point. So change point in any time series is a distribution of anything which is sharply changes. So here on distribution, we are talking about the mean. This is the first mean before the change point, and this is the second mean, 14, after change point. That is around, like here in case of this high cloud fraction, it is 2000, but in other figures, you will see like it is 1997, here also it is 1997 in this case. So you see there is a change from 17.5 to 14, a change in mean. And this is the percentage change. So cloud fraction change, you can see the long wave radiation changes. So this long wave radiation changes means more OLR is going. So it means cloud free. And you can see high cloud fraction has decreased. So there's not much clouds, or you can see you can say that there's a decrease in baroclinic activity or western disturbances over the IGP region. Okay, and the third one, D, I will explain the Richardson number. If the Richardson number increases, means the turbulence is decreases, and that is maintained by the subsidence. So like this, we have analyzed almost 12 more variables, and in all these variables, we saw at 1996 and 97, there is a sharp change in those variables, and those are related to the fog in boundary layer. So the most important one is the western disturbance. If there is a western disturbance, that day you can see that there will not be any fog, because the atmosphere is so warm and the surface didn't get enough cool. Okay, so you see the first is western disturbance, the rainfall from western disturbance, and you see there is a change point here also during 1996 and 97. So before change point, you can see the mean is 3.81 and to each power 10 to the minus 6, and afterwards you see it has decreased. So rainfall due to western disturbance has decreased after change point, but temperature it has a different relationship. You can see more rainfall and more temperature, less rainfall, less temperature. And the same thing you can see in this diagram, where the green one is the regime after the change point when the rainfall decreased, and the blue one is before the change point. So these two regimes are very separate, but little bit only overlapping. So this also shows that how the western disturbance activity has changed during the time. So to now the another last one point, like how the moisture is keep on increasing. So from the time of 1959, we have shown that irrigated area has keep on increasing over the IGP plane, and power consumption also increasing over the IGP, and in IGP we have calculated the same thing for Bihar, UP, Haryana, and Punjab also. Okay, so you will see at the time of 90s, the government given subsidies on the electricity. so that the farmers can switch over from engine, like diesel engine, to electric motors. So this is the last one, almost last one. The evaporation and specific humidity at the surface. So again, like specific humidity and humidity increasing due to evaporation, and that has a correlation of 0.83 over IGP region. So again, it is proving that the moisture supply is very local, because the western disturbances are dry and cold cyclonic systems coming out from tropical subtropical westerly jet. So this is the impact of TKE, okay, turbulent kinetic energy, or turbulent eddies. You see the subsidence from the top of the atmosphere. It warms the atmosphere, and while the surface is very cold. So we say the fog level is 10-meter height from the surface. So if turbulent eddies due to subsidence is limited from fog level to the surface level, then fog can sustain. Otherwise, if the turbulence is very small due to any reason, due to subsidence or due to wind, then the fog will not generate. And if the turbulent eddies is very high, then all the moisture from surface may go above the fog level. But if this eddy is sufficient from fog level to surface, then this eddy can take the moisture from surface level to fog level, and from fog level it can bring the heat to the surface layer, so that more of the moisture can be pumped into the atmosphere. So like that, subsidence and this turbulence maintains the fog in the IGP region. This is the conclusion based on this research, that in 1996-97, most of the variables related to fog and boundary layer has abrupt changes. And those abrupt changes we have shown in almost 15 variables, but most important one are in the clouds, western disturbances, and moisture supply. So deep and widespread subsidence in the IGP plane is one of the critical one, which maintains the stable stratification in the region, and turbulence. So subsidence, turbulence, and radiative cooling together maintains the condition for saturation in the adjacent air to the ground surface. And another is the western disturbance has changed from the time of 1997 to 96. And due to that, clouds in the upper troposphere and middle troposphere has an abrupt change from the time of 1996 and 97. Thanks.
Thank you, Dr. Vinay Kumar.
Okay.
We have, I will say, enough time for the discussion, because you're well in time. So now I think we can have few question answer.
Sure.
Can I ask the question again?
Hello.
Yes, yes.
Yeah. Can I ask? Yeah.
Yes.
Yeah, please.
Thank you very much, Dr. Vinay. It was a good talk. And you nicely explained how meteorological conditions affect fog. I would like to know whether aerosol composition has any role to play. For a certain region, suppose meteorological conditions are same, but composition is quite different. So how it will affect fog?
See, some are necessary and sufficient conditions. Okay, so aerosols are required for the rainfall and for the fog. So these are the initiation stage. But further, how the fog is maintained, the dynamical process and thermodynamical process. So I'm not ignoring the role of aerosols or the fog microphysics. It is there. But we are not, because mixing these two things become very difficult. I think then we cannot explain. In the second paper, we will try to do this. Because like in earlier question, somebody told that dust and other aerosols over the Indian regions are since long time. So why this change is now? Why the fog is increasing over Indian region? So I think apart than this aerosols or dust, there is something else also which maintains the fog over that region.
Any other question?
Yeah, I have a question. Hello, Professor. It was nice talk.
Okay, thank you.
So when you say the fog is increasing, you mean to say the fog lifetime or the fog thickness, or what property are you talking?
Visibility.
You mean fog
Visibility.
density is increasing?
Visibility, sir. Visibility only. We are not doing any experiments, so we are not telling about the hourly basis or something else, or thickening or something. We are saying visibility will less than 1 kilometer, then we are talking for that fog.
Means I understand it's the fog occurrence that you are right.
Any other? We can have one or two questions.
Hello, Binevia. This is Naren, and it was really nice talk. Are you able to listen?
Yes.
Actually, since it is very much associated with Western disturbances as well. I mean, you have explained very nicely all this baroclinicity and other processes that are happening in the boundary layer. So what exactly happens when a Western disturbance passes over and it cleans basically the atmosphere for some time, say for a couple of days, then it picks up and picks up very, kind of high intensity. So, I mean, does this moisture, which is already there on the surface of the earth, plays an important role as the previous question was asked about aerosol. So, I mean, does this have any role, or because if there are sufficient cesiums, so this must be dispersed immediately, but then otherwise the other big aerosols, they may play some role, or we call it some kind of smog.
So, okay, then I will not talk about the aerosol, because I already told that I am not considering here in this study the role of aerosols. That will be a second study. We have done it, but we are still writing it. But role of aerosol is there for the formation of, like, if rough language, if you will say what is fog. So many of the scientists will say the clouds near the surface. On the surface. So the role of aerosol is there, but it is sufficient, like for the initiation purposes. But I will say that is not everything.
Thank you, Dr. Vinay Kumar. It was a nice presentation, and you also concluded it within time. So we had time for the discussion also. So thank you very much.
I gave the answer to everyone. Let's say. You can email me if you have any question, please.
Yeah, there is a chat box here, and if anybody want to ask a question, they can write in the chat box, and I request organizers to compile all these questions and send to the invited speaker. Thank you again. And now we are moving to next presentation. And the next presentation is by Professor S.C. Nainwal. And though Professor Nainwal does not need any introduction, but it's a formal part of this conference. So I would like to give a brief introduction of Professor Nainwal. Professor Nainwal is presently working as a professor in the Department of Geology, Himati Nandan Bhagwana Garhwal University. For the last 20 years, he's working on Himalayan glacier and climate change studies. And his work is focused mainly on the dynamics, mass balance, and volume estimation of the Himalayan glacier through field-based and remote sensing techniques, and has published quality scientific papers in this field. So with this brief introduction, I would like to invite Professor Nainwal for his presentation or for his talk on the topic response of glacier to climate change, a study from Upper Alaknanda Basin, Central Himalaya. So Professor Nainwal, please.
Thank you, Professor Ramola. I am audible?
Yeah, you are audible, please.
Okay, and the slide is also there?
This is also visible.
Okay, thank you, Professor Ramola, for a nice introduction. I also thank the organizing committee for inviting me to deliver a talk. So basically, I am not an atmospheric scientist. I am basically a geologist, and my presentation is totally based upon the field study, which we are carrying out in the Upper Alaknanda Basin. So in this diagram, in this slide, you can see this is the headwall region of the Satupan Glacier, where a huge avalanches is going on. And actually these avalanches are sustaining the glacier. In the inset of this slide, there is a Chokamba peak. This is a very important peak. On the east of this peak, the you can say Gangotri Glacier is there, which is around 30 kilometers long. On the west of this glacier, toward the east, there are two major glaciers. One of the Satopan Glacier and another is the Bhagirath Khada Glacier. And in the south, there is a Choravari Glacier near about to Kedarnath. And from that glacier, the Mandakini is emerged. So this is the basic, you can say, therefore we are calling this Chokamba Peak, or particularly this region, as the water tower of the Himalaya, because it is the source of the major two tributaries of the Ganges. One is the Alaknanda and another is the Bhagirathi river. So before going through this one in the glacier, this is some of the, you can say, terminology where we are talking about some of the glacier, that this is somewhat, there is the snout, then there are different terminal moraine, medial moraine, they are there. But very important thing is that this is the equilibrium line. This equilibrium line actually is differentiate the accumulation zone from the ablation zone. Ablation zone means from where the ice is going to be melt, and in accumulation zone where the ice is going to be stored. So this is the basic concept, how we can identify a glacier there. Now, when we are talking about the climate change and we are talking about some of the glaciers, so you can see this is the IPCC diagram, and you can see the in one of the you can say line, this is the CO2 concentration and another is the temperature. So you can see there is a surprise, whether it is a temperature or whether it is a CO2 concentration. Now you will see the maximum level of CO2 in the past is less than 300 ppm, and present it is around 400, 380 and 390, likewise this one. So this is one of the signals that Earth is going to be warmer. If you compare these, the changes in the CO2, changes in the temperature, and changes in the mean sea level, so everything is going to be changing, and it is actually accelerating at a higher rate. So I think everyone is known about this one. Now I am coming up to the glacier presentation. So glacier, actually they are the result of the ice ages, and basically we are talking about the glacier of which are basically related to the Quaternary Pleistocene period. And all the Himalayan glacier, actually they are, you can say, formed or developed in the pre-existing valley. Pre-existing valley means before it was the river valley, which was the B-shaped valley. Now it became the U-shaped valley due to the erosion of the glacier basically. So if you say about the whole Himalaya, I have given this diagram. And in this diagram, the major 9 rivers are also there. Ganges, Indus, Brahmaputra, Salween, Mekong, likewise, these all rivers are there. But here we can say there are 15,000 glaciers in the Himalaya. And if you say how much are in the Indian Himalayan region, so it is around 9,575 glaciers. So glacier, why we are talking about only glacier? Because glaciers are so sensitive to temperature fluctuation, and hence they provide clues about the effect of global warming. So that are the basic reason why we are studying the glacier in the present scenario of the global warming. So we have the 3 basic scientific concerns about the glacier. What is the regional pattern? Define the distribution of the snout, or basically you can say instead of the snout, if you take about the ELA, equilibrium line along the Himalaya, is the climate only forcing factor of the glacial retreat? This is the second question. And what should be the observational strategy to capture changes in mass, volume, area, and length of the glacier? So if you go for the Uttarakhand, you can see in Uttarakhand there are 968 glaciers, and basically the 3 districts, you say Chamoli, Uttarkasi, and Pithoragarh, they are accounting more than 90%, whether we are talking about the total number of the glacier, as well as the glacier cover, as well as the ice volume locked up in the glacier. So this is, I have given one of the, you can say, table here, which is giving the various idea of the basin, the 4 basin, Yamuna, Bhagirathi, Alaknanda, and Kaliganga. And the average size of the glacier is 3.87 square kilometer, and about 9% of the land of Uttarakhand is covered by the glacier. So this is a little about the inventory of the glacier resources of the Uttarakhand. Now, basically in my presentation, I'm talking about only two things. One is the retreat and second about the thinning of the glacier. So how we'll do this one? This is what is the basic methodology. So the recession, we have the two basic important factors. One is you have to estimate the mass balance of the glacier, or you have to estimate the snout fluctuation. So in mass balance, as in the previous slide, we have given that there are two things. One is the accumulation ablation, and we are going for the surface melting as well as the basin melting. Then we are identifying how much ablation is there. In the snout fluctuation, either we have to monitor it frontal or we have to go for the shrinkage. So I think shrinkage is more better one. And in shrinkage, we are estimating what is the thickness, what is the loss in thickness, and what is the loss in the area of the glacier. So this is the basic methodology which we have adopted during our study. Now, if you'll see about, first I'm taking about the glacier fluctuation. So basically in Himalaya, you will say most of the glacier in average, they are retreating 5 to 20 meters. And most of the glacier, they show the negative mass balance. I have given the two diagrams, one diagram from the Nepal Himalaya. You can see this. This is a figure of 1890, and this is the recent figure. So this particular figure is not showing a very, you can say, alarming retreat, but there is a lot of, you can say, loss of thickness in the glacier. If you see this one, and this is totally filled up the glacier, and now you can see there is some of the material has been washed away due to the downwash. If you see the another figure, it is the figure of the Pindari Glacier, which is located in Uttarakhand, Himalaya. However, there is no evidence that how much thickness is going to be there, but there is a thickness, there is a evidence that how much area has been vacated by the glacier. So this is one of the diagram where 28 data of the glacier is available. It is not only for Uttarakhand, for all of the Himalaya. And if you see about the total Hindu Kush Himalaya, that what is the advancing and retreating. So if you see from 1990, only 95, majority of glacier, 95%, they are retreating, advancing 5, and stationary is 0. So most of the glacier, you can say, they are retreating. Some of the glacier which are located in the Karakoram Himalaya, Karakoram area, they are advancing, either they are stable, and probably due to the enhanced precipitation, this is the reason maybe. Now, this is one of the retreat diagram. I have, you can say, compiled this data from the various sources. And if you see, most of the glacier with an average rate, it is 18 to 20 meters per year. But some of the glacier, like Chorabari, Dunagiri, and Bhagirath Kharak Glacier, they all are located in the Uttarakhand Himalaya. So they are retreating at a lesser rate. And as I have already told that in Indian Himalayan region, there are around 9,575 glaciers. This is based upon the inventory given by the Geological Survey of India. Again, this is 95%, 94.9%, they are retreating, 0.1% advancing, and 5.0% they are stationary. So this is a, you can see in sum up, you can say what is going in the Indian Himalayan region as well as in the whole Himalayan region. Now, this is some of the data I have compiled from the various sources, and basically our focus in the two glaciers were the Satopant and Bhagirath Kharak Glacier. So our university has also a base camp there. And since 2005, we are monitoring this glacier, not only for the retreat, for the other parameters also, for the mass balance. We have also established a AWS there, automatic weather station. So we are doing mass balance, surface velocity, and some black carbon study also with the collaboration with the Department of Physics of our department. Now, before the Satopant Glacier in you can say 90 and 92, we have also worked on the Gangotri Glacier. So Gangotri, it is the second largest glacier located in the Indian Himalayan region, and it is around 30 kilometers long. So this is one of the diagram given by the, one of the figure given by the Jeff Cargill, and it is totally based upon the remote sensing data. As I have already told that our particular work is based upon the field measurement. So based on the geomorphological analysis, we have pointed out some of the location which show that where the glacier was, or you can say basically It was in 1890, the snout was here, then likewise this is repeating. So if you say our data of 61 years, so that total recession of Gangotri Glacier is 1147 meter basically. And based upon this data, we can say it is 90 meter per year, but if you say 1996 and 2002, it is 22 meter. So you can say when we are taking a long-term data, naturally the retreat will be lower. When you are taking a short-term data, retreat is going to be higher one. But at present, some of the papers, some of the recent publications, they are showing that the retreat is now, you can say, came down, and it is 12 to 14 meter only. Now I am coming to the only upper Arakunda basin because it is very much, you can say, concerned with people. So this has given the total area, and there are about 272 glaciers here. And there are basically three sub-basins. One is the Upper Arakunda Basin, another is Saraswati Basin, and the third is the Dhaliganga Basin. So Saraswati Basin, actually it is, Saraswati is coming from the Indian and Tibetan border. And if you see, there are only 38 glaciers only, which is 5 kilometers more on length. And majority of the glacier, they are monsoon dominated region. However, some of the glaciers, particularly in the Dhaliganga Basin, they are the Trans-Himalayan range shadow zone. So this particular diagram is showing, and I have given that this is our Satopant, and this is the Satopant glacier, and this is the Bhagirath Khadak glacier, where our present field in investigation are going on. Now you will see in a glance what is the Upper Arakunda Basin. So we have marked here 15 major glaciers there, and if you see these two glaciers, so it is total area of the Satopant is 21.17, and similarly for the Bhagirath Khadak is around 31 square kilometer. So it is around, Satopant is the 13 kilometer long glacier, where it is 18.50 kilometer long glacier. And you will see this is the Alaknanda, which is emerging from here, and then it is meeting the Saraswati near about to, it is somewhat, there is the Mana, and after that is going towards this one. So somewhat there is the Badrinath. So if you see what is going, what is the recent changes going in the Upper Arakunda basis, if you see in 1994, we have only 147 glaciers, which have area of 376.99, you can say around 377 square kilometer area was there. But now glacier has been, you can say it has been increased. It is 152 glacier now, but the area has been decreased. It is 364 square kilometer. So this increase is due to the fragmentation of the glacier. If there are two glaciers, initially in 1994, they are behaving like a one glacier. Now due to the retreat, they have been fragmented, and they have been, now we are counting in the inventory as a two glacier. So there may be, the number of glacier may be increased in any basin, but basic thing is about the area, how much area. So area loss, if you say, particularly in Upper Arakunda Basin, that is 3.50% area loss is there. And the area vacated is 0.58 kilometer square annually. This is the area vacated by the glacier. Now, after that, this is all about the retreat. Now I'm coming to the another one, which is, I think, more serious problem. Rather than everybody is giving the retreat data, and most of the data is based upon the remote sensing method. So sometime without the field validation, the remote sensing method may give you some, you can say, wrong result, erroneous result. So what we will do, we want to take that what is going in the thinning of the glacier. So we have compared the two data. We have a topographic map, which is published by the Survey of India, and this is 1962 map was there, which is known as the topo sheet. And particularly we have make a DM along this line. Then we have taken some measurement with the total station measurement, and based upon this, we found that it is 0.70 meter per year, you can say thinning is there. Then another, you can say, for the data for this is basically our field data, 2018 and 2012. Here, this is 1962 data. It is the topo sheet data. It is not the field data. And 2010, it is our data. So we compare the one of the, you can say, remote sensing plus field data to the field data only. And here we are comparing these two data which we have taken solely with the field data. So approximate the thinning is more or less similar. But however, this is not a very, you can say, a specific method to identify the thinning of the glacier. So what we did under the various, you can say, funding agency, the Institute of Mathematical Science, Chennai, DST, and this Space Application Center, ISRO, we launched a very, you can say, extensive program. And we have installed, you can say, these are the stakes, wooden stakes, so that we can measure how much ablation is there. And if you are ablation, then we have, we can generate various DM of the glacier. And based upon this DM, when we are compare this DM, we can say what is going to the thinning. So it is an ongoing, still we are going, we are working on the glacier, but basically this work of the installation of the stake was started in field trip of 2014. And every year we are monitoring fortnightly, we are monitoring for 6 months for this glacier. So you can say there is a lot of, you can say, wooden stake is there. And if you compare this stake diagram, you cannot find any such a glacier where such a dense network of the stake is available. So based upon this, we have identified what is the thinning of the glacier. This paper has already been published. So this is our data. We can say what are the elevation changes is going with the thinning of the glacier. So actually we have made this, particularly we have taken this as a representation 8-kilometer span of the glacier, and we found that it is 9 meters in the last 51 years. So after that one, we have some of the data with our German collaborator, and this is the 10 DMX data. Based upon this 10 DM data, they have given a scenario, not only the, you can say, Satopant and Bhagirath Kharak glacier, but majority of the glacier located in the basin, including the Gangotri. Now you can see if I am giving, this is this thickness measurement, meter per annum, minus 0.5. So you will see it is, when you will see if 2015, maximum portion is going to be there. Okay. Here it is the lesser one, 2014, and in 2013, it is very, very smaller one. So it you can say reflect that thinning is going on with a larger rate in all the glaciers. Now, another important thing is that one, we have to measure the surface velocity of the glacier. So normally, the peoples are taking this surface velocity with help of the remote sensing data. But what is the problem? Basically, you cannot take a velocity of a glacier, particularly in the accumulation zone, because in accumulation, overall, there is a snow, there is not a ice in the downstream area, basically downstream region. So we have, based upon their stake data, we have measured the total velocity of the glacier, and the data said that the velocity is increasing from snout to upstream direction. In snout, it is 2 meters per year, and when you are going to upstream, it is around 40 meters per year. It is the average velocity. If you say some point, so sometime it is more than, you can say 80 and even 100 also. So based upon this data, mass balance data, because we have a, you can say ablation data of the glacier, we find that it is -2 meter water equivalent of the glacier, particularly for the season 2014 and 15. The rest of the data is under process. Now, if you compare the mass balance, this is the mass balance of most of the some of the Himalayan glacier, and you will see both are, our results are also in, you can say, agreement with the other glacier. There are some of the glacier, Nehenar, Sonegarang, Goregunga, Gara. You will see this Chorabari, Dokrani, Tipraban, and Donagri. They are the glacier located in the Uttarakhand region. So we have compared our result with these mass balance trend of these other Himalayan glaciers. Now, these are some of the field photographs. Now, normally people are saying that if you are seeing the glacier, so everybody there will be ice, but it is not like this one. You can see this, most of the Himalayan glacier, they are the debris cover glacier, and due to the debris cover, the, you can say, melting rate or ablation rate is lower. Okay. Now, beside this, there are so many, you can say, supraglacial lakes are there. The crevasses are there. These are the proglacial lake. These proglacial lake are normally located near the downstream of the snout. And these are some of the photographs of the accumulation zone of the glacier. Particularly if you see this, it is known as the Swargaroni region. And you will find some footstep there in the Swargaroni accumulation zone of the glacier. And above this, the Chokamba, you can say, hills. So these are some of the field photographs, how we are measuring the glacier for the mass balance. We are making the stack installation over the glacier. So this is some of the photograph. Now you can see it is looking like the glacier. But actually it is the area above the 4,500 meters. And this is one of the Luri-Bamak, one of the tributary glacier. And we are also doing some of the work there. You can see these are our stakes. And we are doing the stake installation here. Now, what are the consequences about that? So basic consequences of the melting of ice caps, particularly the perennial Himalayan rivers become more seasonal, sea level will be the rise, there will be extreme events like cyclone, they will be more intense, the extinction of species is likely to increase, negative consequences on biodiversity, water and food supply, and productivity will decrease due to increased hunger. So all of these things you can say, if the glacier is going to be melted at this alarming rate, then these may be the consequences of the glacier. Now, one of the diagram I am showing you, normally people are saying that there is no globe in particular in this region. And I'm not talking this is a globe, but basically this is the Lakshmiban area. And you will see this is Wagner Glacier. So there are, you can say, some of the blockade of the Alaknanda River, and it was blockaded in 2007. So some of the things are there that may be happened, that sometime river may be blocked due to the, you can say, some landslides also, or due to the some burst of the proglacial or supraglacial lake. So this has happened in the Alaknanda Valley. However, it was only for, you can say, on 23rd June 2007, we have taken this photograph. But this particularly happened in the October. I think it is not for 3 or 5 days. After that, the lake has been bleached out and no major, you can say, damage has been taken into the downstream valley. But if you see in the Kedarnath, during the Kedarnath tragedy, what has happened in the Alaknanda Valley? Normally people are saying nothing has been happened in the Alaknanda Valley. But actually, if you see above the Hanuman Chatti, there are no sign of any type of the flooding. But just after the Hanuman Chatti, there is a, you can see river on the right side of the Alaknanda, that is known as the Khirobagar. So some major landslide has been taken along the Khirobagar. And this is one of the barrage site. You will see it is totally damaged. And this was, you can say, hydropower or site of the GP. And from this totally damaged, and now they have, you can say, reconstructed all this one. So this is the, I'm showing one of the temple photograph, which was located on the left side of this barrage. You can see this was the temple after the, you can say, Lambagar incidents, and this is the before that one. Now, based upon this, I have some conclusion, and some recommendation also. So like many glacier, Himalayan glacier also retreating. But the glacial retreat, they are not only controlled by the climate, but the topographic and morphological factors are equally play important role in the glacial retreat. The second is glacier recession also lead to volume loss, which is more serious than the snout retreat. Therefore, we are started to do the thinning study and the mass balance study on these glaciers. Study indicates that glacier with the thick debris cover respond differently to a warming climate as compared to debris-free glacier. So if you see these two glaciers, so their response to climate is entirely different from each other. So the land change do not necessarily reflect the ice volume loss. Sometimes the glacier is not showing a very higher retreat, okay, but it doesn't mean that there is nothing is going into the glacier. There may be some volume loss in the glacier. So the study here suggests an overall recession trend that compare with the other study carried out in the Himalayan glacier. Shrinkage and melting of glacier lead to formation and expansion of glacial lake. As I have already given you as I already shown that what is going in the Lakshmi-Ban area. Hence, the study of globs should be done on basinal scale. And one of the, you can say, recommendation that establishments or dense monitoring network, whether the in situ or the remote sensing technique in the Indian Himalayan region are the need of the hour to understand the possible impact of the cryosphere changes. Thank you very much. So this is our base camp basically, and it is showing that if you see on the left side, this is the Khadak Glacier. On the right side, this is the Satpura. Thank you very much.
Thank you, Professor Nenwar, for this informative talk. And I think we can have a quick question, if there is any question.
Sir, I'm Shubha here. May I go? Hello.
Yeah, please.
Yes. Sir, thank you very much for a very interesting talk. It was, in fact, educative for me. And it was very educative to see the photographs and the glaciers. So you will see that I'm going to present on the modeling aspects, and I could see a lot of connection between what I heard from you and our modeling work. So I would also like to suggest that there should be some kind of collaboration between modeling and the measurements which is required. And out of my curiosity to know, may I know how do you measure the area of the glacier? You have some equipment which can measure the area for the entire glacier, or may I know that?
Okay, okay. Now, I think you have the two questions. One of the question about the modeling. So actually, it is not only the Garhwal Institute who is working on this glacier. We have a very good group where the modeler is also there. It is the Institute of Mathematical Science, Chennai. Professor R. Shankar is us. And the another in the ICR Pune, Dr. Arga Banerjee. We have also published some of the paper on the basis of the modeling in the Journal of Glaciology. So basically modeling, what we are doing in the accumulation zone, it is difficult to do the field work. So whatever the data we are getting from the accumulation zone, that is based upon the modeling. Our second, one of the students will also present one of the, you can say, presentation here. It is based upon the GPR study. So we are doing GPR study in the ablation zone, but based upon the modeling, but shallow ice approximation modeling, we are doing this work, particularly in the accumulation zone. So this is your answer about the modeling. Second, you have talked about how we calculate the area. One of the things which the people normally are doing is it based upon the remote sensing GIS environment. They are calculating the area. But what we are doing in the field, we have the differential GPS, DGPS, and based upon this DGPS, we are taking the field validation of that particular data. And then we are calculating not only the area, but also the land, each and everything, because the DGPS is giving all the three components, X, Y, and Z. So taking these three components, you can frame out the DEM, digital elevation model of any particular line of whole the glacier. So this is the basic funda that we are using the DGPS, we are using the GPR also. There are a lot of instruments we are using over there. Thank you very much.
Thank you, Professor Nenwar.
I have a question.
I think if there's any other question, they can put it on chat, and Professor Nenwal will answer the questions. The organizers will send the answers. We have now next speaker. We are now proceeding to next one. And the next speaker is Dr. Jonas Svensson.
Sir, please, there is a question from the audience in the auditorium. So can we have that one?
Because we are running shortage of time, you can ask the question in the chat box. That's not a problem.
Okay.
You put the question there, and Professor Nenwal will reply to that question personally to you.
Yeah, certainly I will do it.
Because next speaker is Dr. Jonas Svensson, and he is from Climate Research Program at Finnish Meteorological Institute, but somehow he is not here. He is not able to attend this conference or present the deliberation, but on his behalf, Dr. Rakesh Huda will present the paper, and he is also in the same institute, and he served in building and strengthening the bilateral, multilateral research activities in his expert areas of the atmospheric aerosol and has carried out more than 20 research projects with widened responsibility in India and in Finland since 2003. So I invite Dr. Rakesh Huda to present the paper on behalf of Dr. Jonas Sevenson on the topic vertical distribution of the light absorbing particle in glaciers snow of the Sundarhanga Valley of northern India. So Dr. Rakesh Huda, please.
Yeah, good morning, everyone. Am I audible?
Yeah, you are audible. Please go ahead.
The screen is...
the screen is also visible.
Okay, thanks. So, thank you very much, Chair and the organizing committee for giving us this opportunity to deliver our groundwork with the audience there. So, on behalf of Jonas, I thank again everyone, and we call him as our snowman basically, but unfortunately he is unavailable, and I'm highlighting on his behalf his work basically. So, you know, as title suggested, the work is based upon some groundwork over the years, and the work presented here is in a collaboration of several institutes, and the main partners from FMI or from Finland, FMI, our institute, Finnish Meteorological Institute, and the University of Helsinki, and with our Indian potential partners, Terry was our collaborator for this cooperation, and with Terry we have a cooperation for the dates back a long time. So, and in this talk, actually, it will be based upon field campaigns which were carried out in the year 2015 and 2016. Actually, we had hopes of going there this fall again, but decided not to go. And hopefully next year, this will continue, and we'll address and collect some more samples from the same glacier domain. Okay, so here, if you see the background actually of light absorbing particles in Himalayan glacier, as we have seen from the presentations yesterday and today as well in the morning session, we do know that first we have aerosols produced in greater numbers and mass in IGP area, and which likely transported to snow and ice covered Himalayas. And here we are focusing on light absorbing particles. It is black carbon as well as the mineral dust. So in other words, black carbon, or we can say the elemental carbon, which is depending on the measurement technique, we can distinguish that. And also the mineral dust, which has an importance for the radiative balance of surface snow. So if you see in this figure, which is taken from the Hay et al. 2018, which gives a kind of clear picture of the domain, and it shows the spatial distribution of BC in snow in the subregions of Himalayan region over here, and different subregions of the Tibetan plateau. And if you see in the two distinct seasons, it is clearly visible that there is a spatial as well as temporal variability between different seasons. In the non-monsoon and the monsoon season, you can clearly see it. And also in the bottom pictures, if you see that there is a difference on the data sampled, which are at altitude more than 5,200 meter, and also the lesser than that. And it shows that the deposition of BC concentration on the snow varies drastically. And they came out with using some modeling techniques, perhaps the sneaker model. It was used, and it came to the conclusion that it's a interseasonal variabilities also, and then for the different seasons, and the ranges for radiative effects is ranging quite drastically. So in this picture, actually, it's a Durga Kot glacier in 2017. We took it. So this is one of the glacier in Sundardunga Valley, what we are investigating basically with our ground measurements. And it is worth to mentioning that there are essentially no local emissions of carbonaceous aerosols in the Sundardunga Valley. So most aerosols are expected to be regional and long range transported to this valley. Here in this picture, actually, here it's a schematic overview of the two glaciers, if you see, and the general area. And it is on the southern part of the Himalayas, if you see over here. And point out Mukteshwar especially, which we do have a lots of aerosol observations, and in conclusion, very good some research papers on atmospheric aerosols, heterogeneity, and the variability. So in this glacier map, you can see we have over here, if you see, we have dug snow pits, and where we have installed the AWS also in 2015. And if you see the pits A, B, and C, D, and as well E, basically. So these were sampled in 2016, whereas the pit F, which was sampled in 2015. So this was the kind of working domain or the field area for our actual measurements at the ground in the glacier in Indian Himalayas. So to come to some results, basically, this work was already published by Jonas in AMT, and you can see more about the methodology and the other perspective of this work in his paper. And in that manuscript, actually, we mainly focused on the surface snow characteristics of light absorbing particles. Here, there were some questions in the previous talks about this mineral dust and then absorbing aerosols compositions and the implications of those. So we try to address some of those questions basically by this ground truth activities in Indian Himalayas. And here we presented some deeper snow pit actually in this presentation. So in this paper where we highlighted a couple of other activities, I picked this one pit basically to illustrate some of the results with the audience. And if you see over here, so based on the concentration profiles of light absorbing particles and pit stratigraphy, this pit estimated to represent 5 seasons basically, as Professor Ritesh also mentioned about the intra-seasonal perspective to have to be addressed also while we are seeing the mineral dust deposition implications basically. And with this new snow pit sampled from the same 2 glaciers in 2016, and along with available say AWS data, which we started in 2015. So let's see, we are in the process to dig out some more results on this 2016 collection, but we are not pretty sure whether the results which we presented already would be replicated or can be deviated. So over here, if we see the elemental carbon and the organic carbon, and also the mineral dust deposition, it is seen over here that it covers the 5 years of snow accumulation, and though it's to come to some conclusion, it's a short period. So we have to see some more evidence basically, but based upon this picture, it is seen over here that light absorbing impurities or the aerosols basically, especially in the top 20 centimeter depth basically, it is seen that the mineral dust is quite high in a way, and then the elemental carbon and then OC also. But without having any concrete conclusion. So with this time span of snow pit, we can say that this increase present a short-term pollution event or indicates increasing light absorbing impurities, which could be due to a longer time period or it's episodic. But this is a kind of variability we found with the depth ranging from say 20 centimeters up to 120 centimeters. So over here to have a better illustration with the actual snow and the impurities deposition. So first, we would like to show the visual difference between the pits in 2015 and the 2016 over here. And these two pits are from the same glacier, which is Bharolti Glacier. So on the left side, if you see over here, which is from 2015 with the 5 centimeters of relative fresh snow, followed by a brownish gray melt layer where particles have accumulated, and below that there is an older, coarser grained snow over here. If you can see this one and then the middle part and then over here. Whereas on the right side, if you see from the year 2016, we can see the young snow at the top, and then the very distinct dark melt layer over here with lots of particles concentrated. So the big question is, so what caused this big difference in these 2 years respectively? Whether this is a forest fire in 2016 in Uttarakhand during the spring season, as many of in the audience have published some articles based upon that as well. But we are working on this data set and coming out what could be the possible ways, or whether there is a very intense melt period in 2016 and we are going much deeper to the snow deposition of the particles. So to highlight that for the rest of the presentations, we refer this whiter snow as young snow, and the dark layer, which is over here, is a kind of matte layer, and the gray snow as old snow. So based upon that distinction, when we see some of the results basically, and when we try to analyze these snow samples with the filtration and then deposition on the filters and drying out for analysis of EC, OC, and also the mineral dust, the methodology part can be seen detailed in 2018 paper. So with the analyzed EC content on the filters, which were derived from the filter snow samples, the results are usually presented as EC concentration per mass of volume of melt water, nanogram per gram, we can say in the unit, or microgram per liter. And but to keep in mind that whereas the individual concentration values potentially can be very different in different pits due to local processes, and the scientific choice of layer thicknesses, etc., and also the aerial deposition of elemental carbon is expected to be less variable than the more layers of snow that are accumulated in the derived values. So therefore, we used the approach of transforming the concentration into the accumulated deposited as a function of snow water equivalent basically. So here we have the EC accumulation and with as a function of snow water equivalent. So this was actually done for each layer in the pits with the EC concentrations, which were rescaled to mass of EC deposited per square meter using the aerial amount of SWE. And this is simply done by multiplying the EC concentration by 1 meter square layer thickness and the snow density, and the EC and this SWE per meter square are then accumulated from the surface layer downwards, and resulting in the pit profiles which are presented in this figure from this A to F actually. And what we observe over here, we have several common features that can be associated with the visible layering of the snow described above in terms of young, mild, and old snow. So if we see over here in the pits A, B, C, and over here in D, two similar slopes are present at the top and the bottom, if you see distinctly over here in these four figures, and the bottom and the interlaid by a drastic increase in the middle. And then this top slope corresponds to the layers we refer to as young snow, while the bottom slope, as we have described, as considered to be old snow layers, and the middle layer, which could be the melt layer. So in the pits where the general outline deviates, basically it's not similar over here if you see in the last picture and also in this one. So it can be explained by the fact that in pit E, whereas in the pit F, the melt layer was essentially encountered at the surface of the pits. So there is no young layer if you see over here in this F basically, and here we are missing with the old snow. So these were some of the distinct results. We are in the preparation to further scrutinize the results and coming out with the in collaboration or in the deviation with our previous work. So this was the publication basically, which was articulated in a way of differentiating between Himalayas and the Finnish Arctic. So to focus on the mineral dust again, the methodology part, which is written on the right side. So here we use the fraction of minerals, which is expressed the percent of total optical thickness, and it is estimated for one this wavelength. So the methodology part, it can be detailed out from this this paper in AMT. But if you see from this figure, actually, if you by going the same definition of young snow, melt layer, and then old snow, we can see the mineral dust fraction, which is over here in the snow sample of Sundardunga Valley Glacier. So in this figure, we show that the fractional deposition, the fractional absorption remaining after burning the filters during OC-EC analysis, the diamond shape basically over here, if you can see, these are the individual values of the filters, and then this line, which is kind of arithmetic average, and this is in the box plot. You can see the different quartiles and the median values, and over here you can see the number of samples collected for these distinct snow layers basically. And we can see from this figure that the absolute values for young snow is very large. If you see, the deviation is quite high, varying from say 5 to about 70%, and the range is also varying between say 30 to 47, and the median value is about say around 38. And but if you see in the old snow, the values are somewhat larger, but not different from the young snow, which is about 45 over here. But in the range and the quartiles altogether, which is ranging from say 25 to say 69 for the young one, and also for ranging from 42 to 50 respectively for the melt one. But if we see the melt layers in the middle, basically, which is consistently quite high as compared to with these two layers, basically. And here we can see the median is quite high with 77, about 77, and then range is also varying from say 48 to about 95, and or also the quartiles, if you see, ranging from 73 to 82, something like that. And also we should be keep in mind for this melt snow, only 16 samples were collected out of total 95 samples. So from this picture, I can deliver on behalf of Jonas that this is the take-home masses that overall what we observed, that the mineral dust accounts for about 50% of the light absorption in snow. So this is quite interesting that half of the light absorbing impurities is attributed because of the mineral dust, in addition to, say, other half could be the other light absorbing particles, basically the brown carbon, or if we distinct further this OC into the brown carbon, which we'll try to address in future. So from this picture, on behalf of Jonas, I close his talk basically. And now the form is for the question and comments. And also, if you have some very specific questions, please post your questions to us, so that after discussion with Jonas on his behalf, we can share with you some answers. But on my behalf also, we would like to invite the other researchers working in the domain in India for the potential collaborations in our future work, adding upon the remote sensing and the modeling component. Though we are trying to first make a kind of robust measurement from which we can have the direction to our remote sensing and the validation of our modeling activities. Thanks a lot.
Thank you, Dr. Huda. And I believe that you are ready to take one or two questions on behalf of the Jonas.
Yes, if I could. Yes.
Okay, then this talk is open for the discussion. We can have a couple of questions.
Can I ask one question?
Yeah, please.
Yeah, thank you, Rakesh, for a very nice talk. Hello?
Yeah, please go ahead.
Okay, so in one of your slides, you were showing the light absorbing species, mineral dust, elemental carbon, and organic carbon.
Yeah.
And where organic carbon was more than orders of magnitude higher than elemental carbon. So my query is, first thing is either whether you are considering OC as light absorbing, or you are considering part of it as a brown carbon. Yeah, this slide.
Yeah, we got your point. Basically, this OC was its brown carbon fraction is not yet estimated. So as part of the deposition on the filter of these impurities, so using this OC analyzer, it was analyzed in form of EC as well OC. So it's absolute of total organic carbon, we can say, not a kind of distinction between the absorbing or the non-absorbing part.
Okay, so so here when you were saying this LAI, so OC is a part of it, or it's not a part of it? Here.
In total, it's not part of that.
Okay, so you have built it, you have indicated that. Okay, yeah.
Rakesh? Hello?
Yeah, hello. Please go ahead.
There is one question. What is the effect of the brown carbon glacier melting?
Can you sorry, I couldn't hear you properly. Can you
what is the effect of brown carbon glacier melting?
It's a good question. Basically, even Dr. Sain and other groups, they came out with this Western Himalayas activity using some isotopes and other things. They also come out with this biomass burning attribution to the organic carbon. But I posted some questions to that whether we are dealing with the brown carbon also. But so far, we haven't yet touched upon the brown carbon based upon the groundwork in the Indian Himalayas. But hopefully we do have the methods ready. Maybe in the coming years, hopefully we'll address this brown carbon also.
Thank you.
Thank you, Dr. Huda.
Hello, sir. May I ask? Very
Okay, the last question, please.
Yeah. So, Dr. Huda, Dr. Rakesh.
Yeah, please.
Hello.
Yeah, you are audible. Please go ahead.
Okay. So you have given that there is a younger ice and older ice, younger snow and the ice, where there is a different density or in electrical conductivity.
There was a break in your voice. Can you
repeat it?
Okay, I will write my question. Okay, if not audible, you can answer me on that one on the chat.
Okay, good. Okay, thank you.
So thank you very much, Dr. Huda. And
thank you,
it was
Chair.
a nice
Thank
presentation.
you.
And though you made this presentation on behalf of your colleague, but very nicely you answered all questions. Thank you very much. Our next speaker is Dr. Shubha Verma. And before inviting her, let me give you a very brief introduction. Professor Shubha Verma is a faculty member at Indian Institute of Kharagpur. She obtained her PhD degree from IIT Mumbai. Her area of expertise are environmental engineering, air pollution, and aerosol modeling, and climate changes. And she has a number of quality publications in this field. So she will be talking on the topic, some simulation of black carbon and other aerosol species over the Hindu Kush Himalaya region and their impact on glaciers. So I now invite Dr. Shubha Verma for her deliberation.
Good morning, everyone. I hope I am audible and my
screen you are audible and your screen is also visible.
Okay, thank you so much. Okay, so the topic is the simulations of black carbon and other aerosol species. Just a second, let me.
What can you?
Yes.
Hello. Can you go in slide mode?
Yes.
Your presentation is not in slide mode.
Yes. It is being done. Is that fine now?
Yeah, thank you.
Okay. So I'm with my research group, Shavik Santra, Sanhita Ghosh, Karishtha Dubey, and Ritamar Ray. And the work is supported through the NCAP Police project from the MOF CC. Thanks to the organizers for creating a background to present this work. Previously, we have seen very good talks, and it gives me a background to present this work and to tell you that I am not a glaciologist. I just work on the environmental engineering area on the aerosols and air pollution. And when we started to see their impact on the glaciers, from the modeling studies, we could see some of the hotspot locations from the model to the spatial mapping. And then we went back, started to go back that what are the glaciers located over there, and then the rivers which are coming from there. And then this is kind of like, for me, it was a kind of exploring the details, and it went to a very interesting for us. All this has already been talked about, but to create a background of my study, I still go ahead. The Himalayan glaciers feed important rivers in South Asia like Ganges, Indus, and Brahmaputra. So any changes induced in the Himalayan glaciers reflect upon the downstream hydrology. And due to anomalous hydrology, downstream river-dependent human settlements of South Asia, they get affected. And hence, it is very much required that we should study the pollution impacts and also look at the hydrology of the specific rivers which are targeted to find out the pollution impacts. This again was the Gangotri Glacier was shown in the previous slide, and it was quite very interesting for me to look the photographs of the various glaciers and their retreats. I'm not going to those details now. The Himalayan region has been exposed to the particulate pollution and deposition of BC as reported in various observational studies at high altitude stations. The absorbing aerosols such as black carbon, they affect the cryosphere, altering the ablation rate of ice and snow. The deposited black carbon enhances the absorption of solar radiation, darkens the upper mixing layers of the snowpack, and thereby reducing the snow albedo, leading to accelerated melting of snow. As also it was interesting to me that people talked about the aerosol species, and we have now also this is our ongoing work to explore aerosol species also for dust, organic carbon and sulfate from the model, and to look about their deposition, because as we know that it also depends upon the properties of the aerosols as well as the amount they are deposited. Of course, the black carbon amount deposited in the snow is much lower than that of the particularly the dust. But my talk will further let you know that what happens when we see the comparison between the different species. So based on the measurements, we know that this is happening, that the aerosol species are leading towards change in the snow albedo reduction, and hence, but what happens? What do we need to know? The inaccessible terrain and several severe weather conditions in the higher Himalayan region, they hinder the measurement of atmospheric BC concentration at regular spatial as well as the temporal intervals. So, so what happens? This kind of what happens is the measured data that therefore becomes like region specific, or it can be location specific, but it doesn't describe about the distribution, and hence we need the modeling study to do the spatial mapping and to know the specific hotspot locations which needs to be targeted. However, the model studies, they need the measurements data to validate, to understand, to improve the model for different processes in the model, and to represent as adequately as possible the distribution of the species. What we face the problem in the model is the coarse gridded models to simulate the snow depth adequately, and thereby the BC concentration in snow and the atmospheric radiative forcing is limited. There is a lot of divergence between model simulated atmospheric concentration of BC. It is already reported in various literature studies. So in my work, what we have done is to spatially map as adequately as possible the estimates of atmospheric BC concentration. And also I will present other aerosol species. This is based upon an integrated approach, which is based upon the merging the relevant information from the observations with a relatively consistent atmospheric chemical transport model estimates. So what needs to be done? So what we do in this present study is we see that how does the free and the constrained simulation, which I will explain later on, how they compare with observations over the Himalayan stations, and how do they compare, can we locate the hotspot zone, what is the impact of deposited BC and other aerosol species on the snow albedo reduction, and further the implication of SAR on the HKH glaciers, and does the predicted runoff, like what do we do from the model, does it show any signatures on the glacial recession as observed over the recent years, and what are the sources of BC over the HKH region, and some of the representative glaciers which are already shown over there, and on the right hand side is shown the hypsometry of the specifically the 9 glaciers which were chosen in the present study, which are widely distributed over the hotspot locations of the deposited pollution which was identified from the model studies. And this hypsometry presented on the right hand side is debris free area of the glacier. And so this is how the importance of the border lies, that we can do the sensitivity studies. We took away the debris part, and then this takes care of only the role of the black carbon aerosols on the change in the glaciers. So these are the representative glaciers which we chose. Already these are abbreviated like Barashigri, Chodabadi, Gangotri, Milam, Pindari, Poting, Shankal, Pensonapani, and Zemu. I'm very happy to see that my previous colleagues, they presented a lot of talks they happened on these glaciers, but for us it was like exploring. We just located the hotspot locations, and then we started to see what are the glaciers located over here. So for us it was exploring, but it is very nice to see the talks already happening and measurements going on this specific glaciers identified. And then coming into some of the telling about the modeling framework which we have applied here. This is our free running aerosol transport simulations, which is conducted in the general circulation model. There is the various physical, chemical processes which are conducted together. And then we have the aerosol model, which is coupled with the GCM to understand the role of the aerosol species over the Himalayan location. And this is a specific work which I have applied in the present study, that what can we do with the modeling tools? What we can do is, this is one of the work, I think one of the unique developments from our group, where we call it as region and source tagged aerosol simulations, where you can see that we have tagged specific regions like IGP, Central India, Northwestern India, Southern India. We have Africa, West Asia, Southeast Asia, East Asia, and rest of the world. And this tagging in the GCM is done basically based upon their distinct emission flux. These regions are having specifically, in terms of the emission characteristics, they are distinct in nature, and so we tag them specifically to understand their, and then we do the simulations in the model through the emissions from these specific locations to know the role of the emissions from these regions to the various locations, either it is Indian Ocean region or the Indian land region, or it can also be we have also done the present study over the Himalayan Hindu Kush region. And this is just giving you the glimpse of the transport coming from the tagged region simulations, which is from our previous work. So specifically to consider that how the IGP, from where is the plume of IGP location goes, and then the Central India, how it goes, and then particularly to look at how the transport from intercontinental region comes toward the Indian region. Like we have the transport coming from far off, like the nearby Africa, West Asia towards the Indian region for the black carbon noted specifically here. Further, when we look at the aerosol optical depth, specifically the transport was seen for the organic matter and also for the dust. This was typically noted because what we saw was the AOD, the aerosol optical depth. We could see a very high contribution from the far off region, and also for the dust compared to surface concentration. And this was mainly because of the transport in the upper atmospheric layers, not at the surface from those far off regions. So this has already been published in our previous study. However, what is problem we face is the underestimation of the model estimates, which in general give the observed black carbon from the models, which are about a factor of 2 to 4 during the summer or the pre-monsoon, and goes to as high as 4 to 9 during the winter season. So how to use now, what to do with the model estimates, what are the strong points, and what we can take from the measurements which can help us to improve the model data, and so that we can represent adequately the aerosol species distribution that was the target here. And then to the various reasons which has been already discussed or presented in the literature about why the discrepancy happens in the model. That is because of people have been saying that it is the processes in the model, and also because of the emissions going. However, the point to be noted here is the processes and the emissions, they are independent. They are not related. So here comes what we can do. Can we do? So how to know that whether it is the problem due to the processes or due to the emissions, and hence our development of recently our developed approach of constrained aerosol simulation, which has led to obtain consistent aerosol species distribution over the Indian region, both prognostically and diagnostically. So when I say prognostically, it means that we are able to improve the emissions going in the model in a consistent way. And when we use this model, these emissions in the chemical transport model, again, we see the distribution, how does it work? And when I say diagnostically, means we apply some inverse modeling technique. We constrain the model by some observational data and say, for example, we have done for the aerosol optical depth here. And then we do the inverse calculation for the mass concentration and see how the inverse calculated mass concentration compares with the observed. And so this is our two-way constant approach goes, the diagnostic and the prognostic. And some of the results which is presented. So these are the emissions which we have estimated over India from our constant approach. And this really indicated that how you can see the modified upon base. Base means the old emissions which were implemented in the model, and we could see a very large improvement over particularly central India and also all parts of India. And we were actually underestimating by a factor of 8 to 13 times compared to the old emissions which were implemented in the model. So we call these emissions as the observationally constrained emissions in the model. And then this is our very recent work, which was prompted by Dr. Dunka, Kaskote, Shanti Kumar, all these, the group who prompted us to take the PM 2.5 studies over the lockdown scenario. And we could again simulate very adequately the PM 2.5 concentration for the April month, and then the lockdown scenario, and then how it is decreased. So I'm not discussing all these things. And this is our recent work, which is with the recently published with the ACPD. And I think I can say that is for the first time we have been able to simulate adequately this feature of the Indo-Gangetic plains, showing the large scale pollutant, or this was adequately missing in the modeling studies. And since this was missing in the modeling estimates, so it was very difficult to understand to go further with the model estimates, that to how to understand their impact on either the Himalayan glaciers or further to study on the health impacts or further studies. And this is our comparison with the model and the observed, which indicated that there is a very low, very good match between observed and the model data with our work. This is again the work published in the ACPD recently. So we have seen particularly the Indo-Gangetic plain, where the atmospheric, the BC warming, the warming due to BC aerosols is by a factor of 2 to 3 times compared to atmosphere without BC aerosols. And whereas it leads to the surface cooling by only 10 to 20%. So the question is this a reason for enhanced, as yesterday I heard people talking about the temperature inversion. So we have to explore further. And since we have now been able to simulate adequately the features, so we are looking into further the feedback effects, particularly on the fog or on the interaction between chemical species and the chemical transport. And here lies the importance of the integrated study between model and observations, where we have the combined study of the chemistry, chemical transport, and the radiative effects. We can do the sensitivity studies like take away the specific aerosols and see the effect. So as we have done in the present study. And hence, we have applied our integrated approach to the Himalayan Hindu-Kush region, and the flow sheet is shown over here. So it is based upon the diagnostic approach, and we have the inversion algorithm. And once we have the validated observations or the model validated with observations coming up, it goes to the various other models, like we have SNECAR applied for studying the snow albedo reduction, which is also validated with observations. And then we apply this to the energy and mass balance model to estimate the runoff, the annual runoff increase due to BC deposition. And this was our validation studies with the model at the different locations. Like we divided into the locations under study under 2 categories, particularly this was the low altitude stations and the high altitude stations. So low altitude consisted of the Kullu, Dehradun, Nainital, and then we have Hanle, Satopan, and NCOB as high altitude stations. And this was classification was done particularly to see that because in the high altitude stations, the transport was mainly the primary governing feature to study the aerosol species impact, whereas for the low altitude locations, it was the local emissions which were playing a role, and so we could see the model performance. And now coming towards our main objective here, like how they are impacting the glaciers, and we studied with the as I discussed the various models applied. So so as I also told that the specific glaciers were chosen on the located hotspot region. So it was particularly found out over the Manora Peak. So as we could do the spatial mapping, when we did the spatial mapping, we found the hotspot location was found near the Manora Peak. And so we started to go back that, okay, what are the various glaciers located over here? And so we found, we took into account the specific glaciers and started to find out the because of black carbon, how much is snow albedo reduction, and also what is the impact on the runoff. So here we could see that among the glaciers which were studied, the Pindari, the Poting, Chorabari, Gangotri, which were located near the Manora Peak, they had the high value of the black carbon concentration in snow, and the snow albedo reduction was noted to about 5%. And also we could see the high black carbon concentration in snow in the ablation zone of Gangotri near the snout, that Gomukh. It was it was found in our suggested study, which was published in ACP. Other important thing which was found in our study was the decadal increase. So we applied here, as I discussed, we applied different models. So we had the long-term study from 1960 onwards to 2010, and we found the decadal increase in the black carbon concentration in snow over the glaciers. The typical thing to be noted here was the Zemo Glacier, which is on the eastern Himalayas, and the rate of increase was specifically high over the Zemo Glacier. So we still need to explore that why it is increasing at such a high rate over the Zemo Glacier. Is it the eastern India, which is facing a lot of black carbon pollution, is one of the reasons to find out to lead to such a high black carbon deposition on the Zemo Glacier? We need to have more observational studies as well over such locations. And as people discussed, that it is very important to see that whether it is because of the pollutant or it is because of the glacier hypsometry, the changes happening in the runoff. So we had done the sensitivity analysis with changing various sensitivity analysis were done with the glaciers to find out the snow albedo reduction, and presented over here. So what we could see here is the HKH glaciers were found to be more sensitive to albedo change than the Tibetan glaciers, and these sensitivity analyses were particularly aimed to see that the changes were happening because of the black carbon pollution and not because of their own features. We wanted to segregate this part. Just a second, it is, yes. So analysis, when we estimated for the annual runoff increase, it showed that it was found to be, the median value was found to be the highest for the Pindari Glacier, and it was followed by the Sankalp Glacier. So although the ARI for the Milam Glacier also showed it was also very high, that it was 261 water equivalent per year. This glacier, the Milam Glacier, particularly witnessed the highest percentage increase when we did the control run. When we nullified the black carbon, we kept it as 0. And so we found that the increase was the highest for the Milam Glacier, although the overall the ARI was particularly highest for the Pindari Glacier. So the Gangotri Glacier is also most rapidly shrinking one among the HKS glaciers under study, which has a maximum yearly recession as high as 34 meters. So 5 out of the total 9 glaciers which we found was retreating at a rate of higher than 20 meters per year. So this is based upon our study and the literature information, and we have seen already more educative or more intuitive talks about the glaciers. I'm not into that part, but I'm just looking for the pollution impacts. So recently this work is ongoing. We wanted to see about what happens with the other aerosol species like OC, sulfate, black, and how does it compare with the black carbon. And we could see that the percentage snow albedo reduction due to dust is more than the organic carbon and sulfate because the deposition of dust is more. So this work is under, we are studying in more details this study. This is ongoing in our group. The induced SAR due to OC at Gangotri is 30% higher than the Pindari, whereas due to sulfate it is 26% higher in Gangotri than the Pindari glacier. And the dust has a particularly affects the SAR in the Gangotri glacier, and it is notably it is 22% higher than the Pindari. And this was a comparison done between.
Please conclude. You have already talked for more than 25 minutes.
Okay, sorry. Yes. So this is the various species role in the over the Himalayan Hindu Kush region. Okay. Actually it takes time for the slides to go because of their. Okay, so I think there is some problem in the slide to go forward because of, I'm not sure whether it is because of the.
I think you can conclude it.
Okay, fine. So overall, I could say that there is, we have seen the role of aerosol species over the Himalayan Hindu Kush region and how integrated, this was the kind of regional transport over the Himalayan Hindu Kush region, and we could see the role of IGP and the Africa West Asia region particularly. So we identified the regions which was like 30° north and above 30° north, where we had the role of species, and this was from the various sectors, like it was from biofuel or the organic carbon. So fine, with this I would like to conclude. Thank you very much. I could take up any questions if they come.
Thank you very much for this nice presentation, but I am sorry to say that we don't have time for the question answer because we are already running late by 45 minutes, more than 45 minutes. And now we'll break for a tea, and I think it's a 20-minute, but we'll break for 10 minutes only if everybody agree, especially the organizers.
Hello.
Can you hear me, Dr. Gautam? And
yes, sir.
We'll break for 10 minutes only. I think we'll back at 11.
Yes, sir.
11:35. Is it okay?
Yes, sir. Yes, sir.
And if anybody has the question with the previous speaker, they can write in the chat and send it to the organizers, and they will post it to the individual one, and maybe you can reply to the chat.
Thank you, sir, and Tiwari for nice session chair, and it's a very descriptive session. Thank you very much.
After 10 minutes, okay.
Yes, sir.
Okay.
भाई अपना डॉक कॉपी कर लो यार.
Hello.
Yes, sir.
All are in, I think.
Yes, sir. नहीं आया सर. अभी फैकल्टीज नहीं आई हमारे.
अच्छा, फैकल्टीज आ रही है. 2-3 मिनट में आ जाएंगे.
उससे भी कम में सर.
क्या मतलब बाहर चाय का इंतजाम है क्या?
हाँ सर, ठंडा ज्यादा है नहीं सर.
ठंडा ज्यादा है.
ठंडा ज्यादा है.
हम स्वेटर पहन के घूम रहे हैं.
अच्छा, श्रीनगर तो बहुत ह्यूमिड है आजकल सर, बहुत ज्यादा.
बस सर यहाँ जब बारिश हो जाती है, ठंडी हवाएं चल जाती है, तो ऐसा लगता है जैसे क्या कहते हैं, हिमालय पर पहुंच गए.
बढ़िया है. कुछ मतलब टनल से कुछ श्रीनगर में भी हवा भिजवा दीजिए.
सर उधर से तो इधर आए हुए हैं हम इसी चक्कर में.
हाँ,
नीचे रुड़की भी नॉर्मल रहता है, बाकी इन दिनों गर्म रहता है.
ये पीछे कौन, जयदीप है? जयदीप नहीं है सर. एक जयदीप रावत है, हमारे एमएससी स्टूडेंट रहे हैं सर, यहाँ से पीएचडी कर रहे हैं.
अच्छा. नेक्स्ट स्पीकर कौन है? संदीप, वो रेडी रहे तब तक. सुन रहे हैं आवाज संदीप?
Yes, sir, I can hear.
Can you hear me?
Yeah.
Okay, we'll call you within next.
Yeah, sure.
So kindly share your presentation, sir.
Yeah, I'll share, yeah.
संदीप कैसे हैं?
सर ठीक हूँ सर. आप कैसे हो?
बढ़िया है. कहाँ है? इंडिया में, बाहर?
नहीं, बाहर है सर.
अभिलाष सर को बोलते वो भी ज्वाइन करते हैं.
सर बोला था कल, वो पता नहीं वो.
अच्छा.
गुड मॉर्निंग सर. आदित्य.
आदित्य, हाँ आदित्य कैसे हैं?
सर अच्छे. सर आप कैसे हैं?
बढ़िया. आपको देख के और अच्छे हो गए.
सर मैं भी अभी एक बार स्लाइड तब तक चेक कर सकता हूँ जब तक अभी शुरू नहीं हो रहा है. संदीप, आप अपनी स्लाइड क्या मिनिमाइज कर सकते हैं?
या सॉरी
सर. आवाज
अभी टाइम
तो वॉइस क्लियर है सर मेरी?
एकदम वॉइस क्लियर आपकी, परफेक्ट है.
ओके, थैंक यू सर. जस्ट शेयर.
आया क्लियर.
कोई प्रॉब्लम नहीं है सर?
नहीं, आप इसको अगर प्रोजेक्ट मतलब उसमें, हाँ ठीक है.
स्लाइड शो सर एक बार करके देखता हूँ.
हाँ कर लीजिए.
ओके सर.
ठीक है, परफेक्ट.
I think we should start now. Otherwise, we will be getting late and late. The organizers are ready.
Yes, sir.
Shall we start?
Yes.
Okay, then welcome back. I think you had a nice tea of your own. And as I told you that we are running behind the schedule by about 1 hour. And we still have 12 presentation. And I believe that we will try to complete or conclude it by 1:30, though the scheduled time is 1 o'clock. And I once again request all speakers, because all are the contributor talks except one in between, which is the invited talk. I request all of you to conclude your presentation within 7 minutes and leave 3 minutes for the discussion. And if somehow we will not have time for that 3 minutes, then we will skip the discussion or we will skip that question answer session.
Okay.
So I once again request all of you to keep the time. And the first presentation, which is by Sandeep K, and the title of the presentation is Black Carbon over a High Altitude Central Himalaya Glacier, Variability, Transport, and Radiative Impacts. So,
yes, sir. So thank you, sir. Good morning to all. So Sir, am I audible?
Yes, you are audible.
Yes.
And my screen is shared,
It's
right?
also visible. Okay.
Yeah,
Please.
okay, sir. Sir, today's my topic is black carbon over a high altitude central Himalayan glacier. And I'll be talking more about our observations over that particular glacier Sadhoban region. So I'm very much thankful to HNBGU, IITM and MAS Government of India, and to Aeris also for this international conference. And my outline of the talk will be like introduction, data and methodology, and very briefly preliminary result and the conclusions. So basically, all of you know, we have a lot of talks today about the black carbon warming of the glaciers, especially. There are, in the last few decades, we know the tropospheric temperature trend over the especially of the Tibetan region and the Himalayan region is markedly high, and the Himalayan Gangetic region is marked by a strong positive trend in May, especially in the pre-monsoon. The resulting in statistically significant warming of 2.7 degrees Celsius. And you know the IPCC report, it's the black carbon in snow, it's a positive forcing, and also the black carbon in the atmosphere, which absorbs solar radiation and heat wherever it dwells. So it increases the top of the atmosphere forcing as well. So this is basically a, I'm concluding all the means like the basic gist of the study and not further. Lots of papers are available on black carbon warming and over the glaciers. And so our data and methodology, basically, we have the ethylometer continuous simultaneous sampling and measurement of mass concentration of BC of the glacier. And our location is basically on the Sadhoban Glacier of Himalayas. And some albedo measurements also we have been taking the shortwave from the shortwave and long wave fluxes as well. And we use some models like OPAC and SPDAT model to simulate the fluxes and finding the surface and top of the atmospheric forcing, and also some transport model and as well as the concentration weighted trajectory to understand the transport over that region, and also the satellite and reanalysis data as well. So this is the all available data we have on the site. This is October 2011. The PSSC people have taken some observations over there for a few days only. And October 2016, we have a week of data, like 11 days of data. And we have somewhat a longer period of data from May 18 to October 18 and May 19 to October 19. So this is the all available data, and we have found a 30% increase in the BC mass concentration compared to 2018 during the month of May. So pre-monsoon peaking of BC aerosols is a great concern due to lower snow ice thickness and high shortwave influx. So that can cause a rapid melting, that may be causing rapid melting and can impact the glacier more. And August month showed atmospheric BC concentration both 2018-19 years, owing to basically on the mainly on the precipitation induced scavenging processes. And I'll come more into the details of 2019 observation we had. So basically the BC observation 2019, if you look at the pre-monsoon, we have a high, and the BC measurements we had on the glacier, it showed varied from 8.12 nanogram per meter cube to a 450 nanogram per meter cube, which is high when we compare this a remote glacial location, which is we consider as pristine, and half a microgram, half a microgram of BC is as high enough to impact on the glaciers. So we have the May month, there is a high, and June also still it is high because the wet scavenging has not been there because of the monsoon has not reached, but still the emissions are there. And then there is a drastic decrease from August to mainly the emission reduction as well as the wet scavenging. So almost like 0.8 correlation we can get from this like during the monsoon season because of wet scavenging. So, so the diurnal variation, there is no usual as such pattern for the diurnal variation over the region because of the missing of local sources. And May and June, as you said, the substantial fluctuation in the daytime, probably due to the with several peaks, especially in the noontime with the convective activities and high mixed layer depths. And the absence of local sources and long-range transport from valley regions seem to contribute more in the month of May and June. And also some pilgrimage activities is happening in the valley region. So from there, the transport can happen based on the prevailing meteorological conditions. And atmospheric BC is significantly influenced by the wet scavenging episodes. You can see here in the July and August, and the maximum concentration of BC observed during daytime rather than the night in all other months, indicating a prominence of thermally wind-driven pollution transport. So the BC transport, as you all know, the Calypso also shows a lot of pollution over the valley region, and the concentration weighted trajectory and the FluxPad footprint analysis we have done showed that the air mass from the Indo-Gangetic plain were responsible for majority of transported BC in July and August months, but partially in the September. And the transport from Middle East and far northwestern region was found to be a major contributor in all other months, like in the month of May. And if you see this is a model called FluxPad, and it gives you the footprint of the air mass. So what we have released during 25 during the one of our observation date, and it takes the back trajectory based on the era and wind data field, and from that we can understand that here there's a huge footprint of this area. We can take it as a BC footprint as well if you take. So this this is basic CWT analysis. You can see, but this is with a high resolution, not a low resolution data as compared to the FluxPad what we have done. And during the May month, you can see the transport from far west, and the June also it is like that. But the July and August, you can see a pristine wind field, and there is not much of a high concentration is not seen. And August and September more or less constrained into the IGP itself. And in the October also, if you look at more or less, it's like some the western transport is also there, but more or less it's confined again to IGP region. So if you look at the biomass burning from the kilometer data, so the biomass burning is actually proportional to the so actually the BC concentration measured is actually proportional to biomass burning and well matched with these what the fire maps suggest. So the May and June, you can see high fire counts over this Indian region, especially over the regions of northern Indian plates like IGP and all. And if you consider the July and August, and there's a drastic dip in this thing, and September it increased. So here also you can see the September there's an increase in the BC as well. So it's more or less it's directly proportional to what is happening in the whether it is the cropicity burning or whether it is in the forest fire happening over the slopes of the Himalayas. So the radiative forcing suggests, so when we consider the radiative forcing, we could find that this is the atmospheric radiative forcing what we got, it's nearly up to 10 watts per meter square during the May month, and which can cause as a heating rate of up to 0.4, nearly up to 0.4 Kelvin per day. And it's decreasing, depends on the it depends much more on solar radiation as well, and also because and the heating rate is directly proportional to the BC concentration as well as on the atmospheric forcing. And the albedo sensitivity, if you look at this is a snow cover detected using BRDF albedo during the May month of 2019. And if you look at, if you simulate the pure snow with these type like 50 to 100, 50 to 100, and 150 and 200. This is how the albedo versus wavelength spectrum varies, and it's like a decrease of 10% can be observed with a 50 microgram per kilogram of BC observed. So increase in something like a 56% was observed in the atmospheric forcing by including the SNICA model derived albedo instead of a PRD albedo. So this difference is actually the albedo what we have observed is something like maximum of 0.4 over the region. That is means 40% of albedo, but the model considers it's like high. So the albedo sensitivity is it's one of the crucial factor for finding the forcing at the top of the atmosphere or the surface. And when we consider the no BC and with a BC simulation, this is how the radiative forcing varies. And the so I'll try to come to the conclusions. Like the May and June month showed a significantly high concentration of BC aerosols over the Southern Glacier, and the diurnal variability is feeble due to lack of local sources, and daytime convections and transport from the valley region increase the concentration during the day. The long range transport is prominent due to May and during May and June month, and strong positive correlation is observed between black carbon mass concentration, intensity of biomass burning, and the total direct radiative forcing and heating rates are significant enough to alter the natural snow evolution of glacier. The sensitivity of snow albedo to radiative forcing was steady. It is found that the snow albedo decreases the increase in BC deposition in snow for a fixed BC mass in the atmosphere, leading to a decrease in the top of the atmospheric forcing. I thank the director IATM and Dr. Abhilash Manikar, my guide, and Guphead and MOES, and Dr. Alok Sir Gautam Chinpiju for this immense support in this measurement activities of the glaciers. Thank you.
Thank you very much. And since we have already taken 10 minutes, so we don't have enough time for the question.
Okay,
but if there is a very quick question, we can have only one quick question, if there is anyone.
Yeah, from Aries audience, we have one question.
Okay, so, okay, please.
Let's talk. And you have shown the footprint sensitivity in flex part. So
Yeah.
up to height you are taking the footprint.
Yeah, I'm taking like surface to 1 kilometer along. Yeah.
Okay, thank you.
Yeah, thank you.
So thank you very much.
Yeah.
Let's move to the next speaker from Vadai Institute of Himalayan Geology, Indira Karakoti Bora. And the topic of her presentation is seasonal variability of black carbon aerosols over the glacier of Central Himalaya, India.
Yes, sir.
So Indira Karakoti, please.
Yes, sir. Sir, am I audible?
Yeah, you are audible.
Okay.
And,
thank you, sir. Thank you, sir, for giving me the opportunity, and good evening.
Share the screen. You see at the bottom, there is a share screen. This is the program.
Yeah.
Okay, go ahead. Unmute you, please. Unmute you, please.
Yes, sir. So I'm presenting my work on seasonal variability of black carbon aerosol over the glacier of Himalaya. Here I want to introduce about the black carbon aerosols. Black carbon aerosols are formed through the incomplete combustion of fossil fuel, biofuel and biomass, and has long atmospheric lifetime of several days to weeks depending upon the meteorological condition. As we know that BC play a crucial role in the global as well as the regional climate change process and contributing significantly to the atmospheric warming. Also, BC has a long atmospheric lifetime and wet removal mechanism. In the lower atmosphere, its lifetime is mainly from 7 to 10 days. And also, but in wet season, the lifetime is slightly reduced, and it has a lifetime of 3 to 5 days. And why? Why this means why I have chosen black carbon aerosols? Because BC aerosols on the highly reflecting surfaces like snow and ice reduce the surface albedo, that the reflectivity of the surface, and which result the positive radiative forcing at the top of the atmosphere, and that might enhance the recession of the glacier, and thus there is a dire need for the black carbon study in the glacier environment. So in the study, I have chosen two glaciers. First one is the Darkening Glacier, and second one is the Gangotri Glacier of Central Himalaya in the Bhagirathi River Basin. Darkening has an area of 6.6 kilometers square and a length of 5.4 kilometers, while Gangotri is the largest glacier and has an area of 86.32 kilometers square with a length of 30.20 kilometers. And here with the similarity in the ablation zone of both the glacier, that they are thickly supraglacier. They are covered with the thickly supraglacier debris. And for BC monitoring, black carbon monitoring, we have established two stations using the new generation 7-channel accelerometer A at Darkening Glacier at an altitude of 4,000 meter ASL, and at Gangotri near to the snout at an elevation of 3,600 meter ASL for the continuous real-time data monitoring. This was the boundary of this Darkening Glacier, and we have the AWS as this one at the altitude of 44, nearly 44 meter ASL, and here is the 37 or 38 meter ASL, and this near to 4,000 meter ASL. This is near to the snout. We have established an accelerometer for black carbon measurement, and second one is the Gangotri Glacier. In Gangotri Glacier, this is the Gangotri Glacier, and this now near to the Gomukh. Here is the Chidwasa, where we have set up an accelerometer and an altitude of 36 meter ASL. And the aerial distance of these two glaciers are nearly 50 kilometers. And observations, ground monitoring observations are being carried out at both the glacier to know the impact of black carbon atmosphere on glacier melting. And these are some field photographs, field photographs showing the installation of accelerometer. This is the moraine, moraine near to the snout of Darkening. And to know the impact of BC on the BC on glacier melting, we have first of all study the meteorological conditions of both the glacier, as the meteorological conditions of any site greatly influence the transport of aerosols. So we have first compared the meteorological condition of both the sites. Here we see that this is for the Darkening Glacier, this temperature, and here is the relative humidity, and here is the rainfall. We see in all the three parameters, Docrani Glacier has higher temperature, higher humidity, and also higher rainfall. It means that Docrani has much humid and temperature than the Gangotri Glacier. And the temperature of Docrani, average temperature of Docrani noted as 11.4 degrees centigrade, while at Gangotri it is 3.81 degrees centigrade. Also, the relative humidity at Docrani is high, and it is nearly 56.85%, and for Gangotri it is 30.25. And rainfall is very high at the Docrani. It is at the average rainfall is noted at 4.14 millimeter, while at Gangotri it is only 0.17. So it was the meteorological study before going to the BC aerosols. Now coming to the aerosol study. Here we have plotted the temporal variation of black carbon for the Gangotri and the Docrani Glacier, and we see that in Docrani Glacier, this red one is for the Docrani Glacier, and we see that in Docrani Glacier, black carbon concentration is high in almost all of the days. Only in the month of December to in the starting of January and in the month of August, black carbon is high in the Gangotri Glacier, which might be due to in the monsoon season, as the rainfall is high in the Docrani Glacier. So due to the wet removal mechanism, this black carbon is low in the Docrani. While in the winter season, it might be due to the it might be due to the high upslope wind in the Gangotri glaciers, which transport the pollutant to the glacier valley. But for the other month of the glacier, we see that this BC is high in the Docrani, as Docrani is lies in the leeward direction, and this Gangotri lies in the backward direction. So the pollutant coming from the foothill and also from the urban area and out of India directly influence the BC concentration at the Docrani Glacier and contribute to the BC mass concentration. So it seems that all these regions, due to all the region, BC concentration is high at the Docrani. Now coming to the seasonal variation, we have also plotted the seasonal variation, means winter, pre-monsoon, monsoon, and post-monsoon, and we see that in the month of the pre-monsoon month, BC concentration is high at both the glacier valleys, and at the Docrani it is very high, nearly 1121 nanogram per meter cube, while in the monsoon season it is very low. Here we again see that the BC concentration is high in the Docrani Glacier than the Gangotri glaciers. Now here is an interesting thing, the diurnal variation. Diurnal variation at both the glacier valley for the four seasons, and here is also similarity there in the pre-monsoon season. The peak of the BC concentration is high in the pre-monsoon season, and the peaks start from post-monsoon, post-noon at 12 p.m. to and attain a peak at the late evening hours, nearly 6 to 7 p.m. and remain minimum during the rest of hours at both the glacier valley. And one interesting thing is that about this peak that which is maximum at 6 or 7 p.m. And also we see that the glacier runoff or glacier melting is also high during this period. So there might be some correlation, or we can correlate this BC mass concentration with the glacier melt modeling, or glacier runoff through some modeling. And this is the future plans which we want to, which will contribute, means which will actually quantify how the BC concentration influence the glacier melting. Because only measuring BC at the atmosphere, we cannot say that BC influence the glacier melting. So there might be some correlation.
We have already exceeded the time.
Okay, sir. These are some findings that Gangotri Glacier Valley, in spite of being pilgrim places, so the slight lower concentration of BC, which means that BC Indo-Gangetic transported from the nearby localized area and urban area through the upslope valley wind, and also due to its leeward position. As the study in BC aerosol in Himalayan glacier is a matter of scientific interest, and the investigation of BC in the glacier environment, BC in the glacier and environment is a vital step toward the exploration of the factor responsible for the enhancement of glaciation and warming over the Himalayan, over the high altitude Himalayan region. However, hence the monitoring atmospheric pollutant, mainly BC in the Himalayan region, seems to be a prime need to reduce their impact on the glacier, and this effect this effort will be helpful in the government planning of pollution reduction technique in the Himalayan region of India.
Thank you very much for your presentation. And we don't have time for the question here. And anybody, if you want to question, can post in chat session. And the next presentation is by Aditya Misra from Himati Nandan Bhagwana Garhwal University. And he will be talking on the topic thickness and volume estimation of Indian Himalayan glaciers using field-based geographical techniques, a brief review. So please complete it within the given time. Total time is 10 minutes, 7 plus 3.
Thank you, sir. Thank you, Chair, sir. Ramola, sir. My talk is on this ice thickness and volume estimation. This session is basically based on the studies have been carried out, glacier studies have been carried out in Himalayan region, so I will not much discuss, just come directly to my topic. And this is in continuation of previous talk by Professor Nanwal, who is my supervisor. And I would also like to mention here that the study is done by the funding.
Indira has not stopped the sharing. Indira, please stop the sharing.
Sir, my is not sharing.
Okay, now it's coming. Yes.
Okay. Screen is visible?
It's visible. Please bring it to full screen.
Oh. Thank you, sir. This work is done by the funding agency under the DST funded project, and all the issues have been discussed in this session and in this and before this morning session. So glaciers are are valuable resource of fresh water. They provide water to the perennial rivers of northern India and feed large number of populations, and they are also useful for domestic and agriculture purposes and hydropower generation. So the major question is, now I will not go to this, the major question is water availability. How much water is available in the Himalayan glaciers? What are already available estimates are reliable? Is there any uncertainty in the range? And if yes, of course, yes, the high range of uncertainty lie in the available estimate. So what is the range of uncertainty and how these estimates can be improved? This is, of course, the reason that the studies have been done of on the remote sensing studies and lack of field studies. That is the reason the higher range of uncertainties in the results. And so how many glaciers have seen these field surveys, and what are the challenges and possible solutions? So basically in Himalayan region, the volume have been estimated by using scaling laws. These scaling of laws are nothing but this is regression method, which is based on the glacier studies done in Alps, Andes, and other part of the world. But if you will see this table given here, where it is based on the basically 144 glaciers in Alps, 61 glaciers in Chinese region, and most of the are not from the Himalayan region. So that is the reason. That is the reason why huge uncertainty lies in the volume estimates in Himalayan region, and that is this scaling method is basically volume. It is in this volume estimation, area is the only input, and these are two scaling parameters, C and gamma. So another is this has been substantially added by the numerical methods. Numerical methods are basically based on in these numerical methods, remote sensing are the basic input. So it is another chance of increasing uncertainty in the range. So what is the alternative? I have summarized here in the table that what is available estimates in the Himalayan region and what are the uncertainties in the results. If you see the table by Srivastava and Rana and Srivastava estimated the volume. It is also based on the scaling method, and Bolch and others. And you will see the huge uncertainty. Volume ranges between 2300 to about 6500 kilometer cube. It is for entire Himalayan region, Himalayan and Karakoram region. And whereas the above study is restricted in the Indian part of Himalaya, where this Nepal and other Bhutan and other parts have been left. But in the study by Bolch and others have taken all throughout the Himalaya from Karakoram to Eastern Himalaya. This is another study by Kulkarni, which is also indicating the huge range of volume. And this is a recent study by Farinotti, which have taken numerical models in the to estimate the volume. This shows the range of uncertainty to be lower, but basically no field studies have been taken from the Himalaya, especially from the Indian Himalaya. So we have also tested this hypothesis in the Himalayan, in the Uttarakhand glaciers, Uttarakhand region. I have taken part of Alaknanda basin, where 166 glaciers are located and covering area of 360 kilometers square. So this is I have plotted this observed volume and the observed volume and the modeled volume. It is showing that you can see from this table, from large area to small area, uncertain volume varies significantly. And from this table, it is very clear that none of the observed volume is lie on the scaling or modeled volume. So this is under review. Also, this is another figure which is showing that the volume of glaciers, how volume varying from one method to another method. So this is all under review. And now this is why this huge uncertainty lie in the estimates. This is basically because of lack of field estimates. Basically, if you see this map ranging from Karakoram to Eastern Himalaya, we have only 11 glaciers, 10 glaciers where field studies have been done. One only in Karakoram, and most of the studies have been conducted in the Western Himalayan region. And in Central Himalayan, only one glacier have Dokriani, which have seen GPR survey, that is geophysical method, and one or two in the figure. They are Donagiri and Tipra glacier, where the resistivity and seismic survey have been done in 1970s by GSI. And in Eastern Himalaya, no study has been done except on JMO where seismic and resistivity survey has been done. So this is the basic lack of study which increase the our understanding towards volume estimation in Himalaya. So now this is the detailed result have been presented here, and interestingly you will see this only in central Himalaya, of Indian part of central Himalaya, where more than 1,000 glaciers lie, but only one glacier has been studied have been studied for GPR survey. So it is in 1995 by Gargan et al. So, and there another glacier which have been extensively explored for GPR survey, that is Chota Sigri glacier, and it is also mentioned to here that only these are two glaciers which have been taken for validation and calibration in the Himalayan region in volume estimations in Himalayan region. So by Frey et al. Has taken these two glaciers only for his calibration of his results. So it is so this is the reason that their results are very uncertain. So now what we have also have estimated thickness on the GPR is estimated field-based thickness of Satopan Glacier. Satopan Glacier is located in the Alaknanda Basin at the head of Alaknanda River, and it is varying from 3,850 meters from snout to about 6,400 meters at the accumulation zone. It is extensively debris covered, because I will not discuss much because Professor Nanwal has explained all these things in his morning session. So this is the how debris cover, because since morning we are listening debris. This is the how debris cover glacier look like. They are extensive debris cover glaciers, are long, narrow tongue, and have very small accumulation zone, as you can see from this. This is the accumulation zone, and these are fed by avalanches. Glaciers are fed by debris covered glaciers are fed by avalanches. So you can also see the avalanches cone in the accumulation zone. And the lower picture showing the debris over the glacier, and you can imagine how big boulders over the glacier are. This is the survey, GPR survey over the ice, near the ice cliff on Satopan Glacier, and boulders in the order of tens of meters you can see. So these are this debris is creating lot of problem. I will be discussing all these things in my next slide. So what is the principle of GPR? GPR is basically, it is a geophysical metal which uses the radio waves, and in the order of 10 to 2000 megahertz. It is assembled. It is generally it is basically three components are there: transmitter, receiver, and antenna. Waves are generated through the generated by the unit and transmitted through the transmitter, and then reflected to the through the antennas, and then received by the reflectors. This is the how depth is calculated by GPR. This is based on the just two-way travel time. And I will not going. This is the mode of GPR operation. Basically, there are 4 or 5 methods. So I have used these 2 methods to estimate ice thickness of Satopan Glacier. So these are field photographs. And you can also see we have taken thickness from debris cover glacier as well as from the debris free region also. We have used, this is the location map where we have done our GPR estimation. We have covered almost 4.5 kilometers by GPR survey, but by the way, unfortunately we could get bedrock reflections in only few profiles. This is the low success rate have also been achieved in other glaciers of the other glaciers of the Himalaya. This is why less studies have been done. We could assume that this may be the reason. We have also estimated the velocity of this radio waves in ice, and this is the first study which have been conducted in Himalayan region so far. So we have estimated 0.156 meter per nanosecond velocity of radio waves in ice, whereas in polar region it is 1.60, which depends on the this is the thickness. sorry, sir, just I'm quickly going through. Yes. This is the thickness which we have measured. We have used this 16 megahertz frequency antenna near the snout of the glacier, and we have estimated thickness. It is varies from 39 to 50 meters, and this is also confirmed by the cliff exposed near the glacier front. And this is also, we have also validated that profile with other different frequency antennas, and it is showing the consistent throughout the estimation. This is another profile, GPR profile, which is showing that which is at altitude of 4,500 meter, and we have estimated the thickness varies from 90 to 110 meter, which is at very high altitude, and this you can see the reflections in the. We have also estimated the thickness at another place. It is varies from 140 170 meter, and but bedrock reflections are not as clear as much in the previous slide profiles, because it has been used by in the debris free and also in the avalanche region, so it may be in glacial debris may obscure the bedrock reflections. This is the this is very important to mention here. This is the schematic diagram which is showing that glacier is flowing like this. Himalayan glaciers, which is had number of tributaries. This is the schematic diagram. We have estimated the thickness. This profile is which is perfectly usable, but we could not. It's a half. We could not get, but it is one of the best profile in Himalaya, which we can say yes. So, what are the challenges? Basically, debris is the problematic, and the location of these Himalayan glaciers. Debris is problematic in sense of supraglacial debris, because supraglacial debris is playing role when we are placing our GPR over the glacier. Then it is decoupling with the ice and antennas, so it is problematic. So signals are scattered. And another thing is debris in glacially also move in glacially. So in glacially debris obscure the bedrock reflections. Another reason is Himalayan region is temperate glacier. Temperate glacier is always at the present melting point. So the radio waves cannot travel or propagate properly in the water, in the wet or moisture medium. So it also dampens the propagation, and waves cannot propagate into it. And other technical issues I'm not going to discuss here. So that I think we should, because it's a DST program, we can say that representative glaciers, because there are a number of basins or sub-basins where no studies have been carried out. So we can say that representative glaciers can be taken at the basin scale, at least one glacier in a basin. And second thing is low frequency antennas are especially designed for the rugged Himalayan terrain. This is my talk and all about this. And this is my research team, my supervisor, Professor Nanwal, R. Shankar, as Professor Nanwal has mentioned in his slide, Professor Dr. Arga Banerjee, Sunil Singh Sir, research scholar, Ankit Pandey, Saurabh Saha, and Kuldeep Singh. This is all.
Thank you, Aditya.
If you have any questions.
Since the talk has already gone more than 15 minutes, so we don't have time for...
very less time has been given. Yes.
And we still have 9 more talks, and time is very limited. So I now invite another speaker, Chandan Sarangi from Indian Institute of Technology, Chennai, and the talk of presentation is "Can elevated dust layers explain the altitude heterogeneity in snow melt trend over Western Himalaya?"
Adit?
Hello, I'm audible?
Yeah, you are audible, please.
Yes.
And the screen is visible, right?
The screen is also visible.
Okay. Thank you, Professor Ramola, and the organizers for this opportunity. And also thank you for all the participants present here and the presenter who presented before me, because they have already laid down the background on which I will start my talk. This picture is the whole motivation of what I'm doing since last 3 years. You can see there is, this is a Colorado Basin picture, and you can see a lot of dust being deposited over this, over the snow caps, snow cover there. And you can also see patches where it is pure snow, that is white color, and also patches where it is the dust deposition has caused it to be a little more darker, or we call it as snow darkening. And this darkening is supposed to change the radiative forcing at that surface, and therefore it affects the snow melt. Now and here in this talk I will try to explain how the snow mass reduction trends are happening over Himalaya, and can the elevated dust layer, I will explain what is elevated dust layer, although many of people might be knowing, is it a factor which can explain the elevational signatures we are seeing in the snow melt over Himalaya. And my name is Chandan Sarangi. I presently is at IIT Madras. It's in South, and I have joined as assistant professor. And this work I have been collaborating with my collaborators from NASA as well as PNNL, National Lab in US. Yeah. So now, first of all, I will be talking about snow melt explicitly, not glacier melt. And there has been a lot of study, and the people presenting before me has been talking about how the glacier melt or glacier balance is getting affected by air pollution or absorbing aerosol deposition. Here I will talk explicitly about the snow melt. Now in this figure, it has been beautifully quantified by Armstrong et al. 2018, and they show that in our river basins, you can find around 50% of the stream flow is being contributed by snow. The snow that is deposited every winter season and which gets melt. So if it is above a certain height called as snow line, then it remains back for the or it get deposited as glacier. Below that snow line, all the snow that precipitates on Himalaya is melted and contributes to the stream flow, and that is quantified as about 50% over our region, which is quite significant. Yeah. And why we are focusing on Himalaya? Because okay, so this is an image of what is the snow cover trend in a global perspective from satellite observations. And you can see that our region, the HMA or the High Mountain Asia region, is at least one of the most vulnerable place where the snow cover is decreasing at a rate of like 2 weeks or 15 days per decade, right? So this is significant because this will affect the 50% of the snow melt into the rivers. And the second perspective is that HMA is surrounded by air pollution in all sides. Like you can imagine it as a water tower which is frozen, surrounded by air pollution in all sides. From China, from India, from Afghanistan, there is a mixture of air pollution going there, like black carbon, anthropogenic emissions, as well as dust. Dust is a big contributor here. And going further, another study, Smith et al. 2018, which tries to go deeper into this reduction trends in snow mass, and they have shown the elevational signature in it, right? So I would like to focus on here. What you are seeing is the y-axis is the elevation of the place, and x-axis is the annual snow water equivalent trend, and it is negative, which is showing that it is reducing, right? And you can see a parabolic shape appearing where the reduction increases with elevation till 4.5 or between 4 to 5 kilometer, and then decreases, right? And it should be noted that this parabolic shape is not found in each river basin. Now these lines are colored as per different river basins, and which you can see here. I am pointing it out if you can see it. And Ganges is yellow color, Indus is red color, and Amu Darya is black color. Now if you want to see where these are spatially, you can see the first A panel. You will see the Ganges River Basin, you will see the Indus River Basin, and I believe near the point 1, you can also see the Amu Darya River Basin. Now this figure clearly shows there is a distinction or a distinction in the elevational signature of how snow mass reduction is happening in the western side or the western side of HMA region. The reduction has a parabolic shape in snow mass trends, while in the eastern side or the Ganges Brahmaputra basin, it is not like that. It is quite different. And now till now, most of us believe that these snow mass trends are primarily changing because of climate change or global warming and the temperature rise. But if we are talking in terms of this domain which we are seeing in panel A, then the whole region is within means it should not change so much. Like the climate effects should not change so much that Indus basin is affected differently and the Ganges basin is affected differently. In this context, we plotted aerosol columnar properties in the same figure, and we are trying to see if there is an association. Like the red and yellow color you are seeing here is aerosol index from OMI satellite, and it is averaged over 10 years, and you can see this this specific patch of columnar loading, the red color, which is very specific specifically dominated toward the western part of the domain, or in other terms reaching the western Himalayas, right? When I say western Himalayas from now on in the rest of the talk, I mean number 3, number 4, number 7, or the Hindu Kush region, the western Himalaya region, and the Karakoram region. I combine these three and I talk it as western HMA, and you can see that a very prominent association is being seen, that the western HMA has a distinct snow mass trend, and the aerosol distribution is also very distinct, which is reaching the western HMA. Now I want to talk a little more detail about the vertical distribution of the aerosols that are reaching the western HMA. This is a very good illustration by Gautam et al. 2009, and they shows that you can see the Himalayas. It suddenly rises up just after the IGP, and this is IGP. This dot is actually Kanpur, and the arrow shows the wind coming into the valley. And during the or the dry seasons, mostly it starts from February and goes up to July end, we see a lot of dust transport coming in from transported dust from as far as Saudi Arabia, and these dust come and eventually get deposited in the Himalayas, right? And if you make this picture shows AOD, and if you have a ground-based remote sensing like LIDAR kind of thing, what you will see is a similar picture being seen in right panel that I'm showing, which is from one of my studies in 2016. We used a micropulse LIDAR in Kanpur to see how is the vertical distribution, and we clearly see that the distribution of aerosol can be divided into two parts. The first is the surface layer. The surface layer extends from 0 to say 1.52 kilometer, and then there is a distinct elevated aerosol layer which spreads from 2 to 5 kilometer, and it is a very prominent feature over this region. And many other groups have also reported in last 10 to 15 years. Many of the people who are attending this conference, presenting, they all are very much acknowledgeable about this elevated aerosol layers. Some of the groups like Dunka et al. Group, Dimitris et al. Group, they have studied this in great depth, and many other groups. So I don't want to go into much detail. Now, what I'm trying to focus is, if you see a parabolic shape in this snow mass reduction trend, and you also see a parabolic shape in the elevated aerosol or the aerosol distribution, then the inquisitive mind instigates, can these elevated aerosol layers reaching the western Himalayas explain this elevational heterogeneity? This is the exact basis on which we started our study. And so first we took calypso observation of last of 2006 to 2017, and we identified these elevated aerosol layers. You can see the elevated aerosol layers distinctly separated out of the surface layer, and they are clearly reaching the Himalayas at a certain height, at not at near the ground, but at a certain height. So what we did, we calculated the frequency of elevated aerosol layers from all the calypso observation we got in this domain, which is shown in panel D. And this is the gridded distribution of number of EALs. And again, it is quite clear that most of the EALs are restricted to the western part of the domain, and they are reaching the western Himalayas explicitly compared to the eastern part of it. Now, if we also took the depolarization ratio estimates from calypso and compared it with the elevated aerosol layers that also observed from calypso, and we see a clear correlation, which shows that if the elevated aerosol layers are bigger or more occurrence is happening over that grade, then the depolarization ratio is also higher, which indicates that it is more coarser, or we can tend to say that this is mostly dust dominated one, although many papers are still researching about the exact composition, but it is reasonably safe to say that these are dusty EALs basically. And you can see the box here, which denotes the Indus basin or the western part of the subdomain. If you average out the EALs in that Indus basin box, you will find a very beautiful parabolic shape in the dust reaching western Himalayas. It will increase till 4 to 5 kilometer and then starts decreasing. Now this is the distribution of aerosols reaching the western Himalayas. Next, we try to see what is the
conclude within 1 minute. We have already exceeded 15 minutes.
Yeah, 5 minutes more I will do it.
You have already taken 15 minutes. It's 10 minutes talk only.
Okay, so this is the elevational profile I also got by using remote sensing, applying the MODIS data. I found that the snow albedo darkening happening in the western Himalayas from the MODIS, and we were very excited to see that there is the parabolic shape structure, which is very clearly seen in the last panel. And if you see this structure and this structure, it matches quite well. Hence this is also supporting our argument. I will quickly in 1 minute show that. Again, we used MIRA, which is a reanalysis product for last 10 years to correlate it with the satellite observations, and y-axis is the albedo change because of dust, and x-axis is the dust concentration, and we see a very strong correlations, which is again sustaining our hypothesis. And the last one is model simulations. We used very high resolution simulations to show that the first one is change in albedo because of BC, second one is change in albedo because of dust, and third one is the ratio of the change. And what I'm trying to just emphasize is the parabolic shape that is explicitly simulated by model. It is not dependent on the meteorology, so we can say this is because of only dust, at least in the model. And all these three approaches, like long-term satellite observations, reanalysis, as well as explicit high-resolution modeling, show us again and again and strengthens our hypothesis that the elevated aerosol layers coming and getting deposited in the western Himalayas can actually be a main factor explaining the snow melt trends. Thank you. I will stop here.
Thank you very much. And as I told in the beginning that we have 12 contributory papers in this session, and it will take about 2 hours to complete these papers. And we have already consumed 1 hour for 4 presentation only.
Sorry.
So I have a request to all the speakers, please keep your presentation within the time so that we can conclude in the time. We are already late by more than 40 minutes. And then you can imagine that still we have now 8 more talks and 1 invited talk in between. So thank you, Dr. Sarangi, for your presentation. Of course, it was a nice presentation, but I'm sorry that we did not have that much time for discussion.
And no problem. Thank you, Professor Ramul.
Now, the next presentation is the invited talk. It has been converted to invited talk by the organizers. And I also have the same request with Dr. Kuniyal that the time of presentation is 15 minutes and 5 minutes for the discussion so that the talk may become the interactive. And the title of the talk is Climate Change and Changing Behavior of Water Resources in Different River Streams of the Himalaya. And the talk is being presented by Dr. Jagdish Chandra Kuniyal from Govind Ballabh Pant National Institute of Himalayan Environment, Kosi Katarmal, Almora. So Dr. Kuniyal, please.
Yeah, thank you, Professor Ramulaji. I'm really very much thankful to the organizers and to give me this opportunity. And respected chairperson and other fellow delegates. Slightly, I have changed my.
Excuse me, sir.
Hello.
Yeah.
Yeah. Am I audible?
Yeah. Now it's coming. Yeah.
Okay. So slightly, I have modified my title: Climate Change, Changing Water Resources and Land Use Pattern in Different River Basins of the Himalaya, and it was especially upon the request of Dr. Dumka and Dr. Alok that I should deliver the lecture on this topic especially. Although, as a brief, I should tell you that this is the project on which we have worked, but the results are still on finalization stage. So the final results are, I could not be able to show you at this time, but I am supposed to show you the glimpses of this activity. Having the 5 research partners throughout in Himalayan region, including Kashmir University from Northwest and CSR, Northeast Branch Laboratory, Imphal, 2 partners and other 2 partners from our regional stations from Kullu as well as Itanagar, having coordinated by headquarters, Kosi Katarmal. The activity was started, having the major objectives to monitor snow melt and headwater contribution and river flow, and to assess the impact due to erratic seasonal behavior of river flow on land use pattern, hydroelectric power projects, and aquatic biodiversity, to enhance the capacity building in the of changing land use pattern and livelihood options of the local communities, if some mitigating measures as well as to suggest and as well as to propose some policy guidelines which are still under preparation. So these are the slides. You can see how much square area we have taken. I will not go into detail. In Jammu Kashmir, Sindh Basin we have taken, in Parvati Basin in Himachal Pradesh, and the Dholi Ganga Basins, in Uttarakhand, Ganga Nadi Basin in Arunachal Pradesh, and Imphal Basin in Manipur. So for this, we have analyzed, all the drainage system patterns in the Sindh Basin and as well as in Parvati Basins, and the drainage network also in Dholi Ganga and Imphal Basin. And we have installed some of the important equipments, WLR, which we call water level recorders, along with the rivers headwater region, and to see the seasonal flow of seasonal flow of river water in every basin. And these are some of the methods to analyze the cross section of the river and how we are going to analyze the flow from every river. These are some of the methods. I will not go into detail. Average discharge form, what we found from 2018 and 19, that is going to increase. Site is selected to understand the contribution of snowmelt in total river water flow. And for a single case study, because still our data under finalization stage. So at a set, it is 50% in general for the northwestern Himalayan region. But when I think that when we will average this data, then this value will come down. Same pattern is also observed throughout the gauging period, and average discharge increased from 2018 to 2019. Average daily temperature is higher in the year 2019 compared to 2018. As a result, snow melt also influenced in different river systems. If suppose I take the example of sediment load in river basins, then you can see monthly discharge cubic per meter per second is under very different situations and day by day. If suppose monthly average discharge we take into account, you can see how it is going to differ. Sediment yield is also accordingly to be influenced, and sediment load per tons per day is also going to be decreased with the altitude also. If suppose we are in down slope regions, sediment load is going to increase. And variation in suspended sediments with discharge of Nula River in Dhauli-Ganga. This is the discharge pattern of this stream, where you can see it is going up to 11 cubic meter per second, and along with daily, along with total suspended solids, you can see how it is going to vary. The variation of suspended sediments concentration, you can see how again they are having a very dependency on day-to-day activities of the seasons and of the weather of the locations. And some of the data based on month-wise, we have derived that the discharge was maximum in the month of July in 2018, August, and average is 7.14 in 2018, whereas in 2019 it was also almost, the pattern is similar, although it is little bit decreased. And also the Dhauli-Ganga also variation of suspended sediments with river discharge also is differing based on the months and seasons, depending on the monsoon and snow melt periods. And these were the weather stations we have installed in every basins. And the data due to this COVID situation, this year's data we could not derive, but just you can see the glimpses in 4 basins. And status of rainfall, as just last year's data we are showing that it is also markedly differing from one day to another day. And but you can see in rainfall is total 1842.24 millimeter. Maximum rainfall in single day was observed 67.07 on 25th September 2008. Status of air temperature is also differing, sometimes in minus and sometimes in plus, and in minus times you can see how minus it can touch up to minus 15 degree in these locations. And similarly, status of relative humidity is also variable, but not as differ as the temperature. And water quality also we have assessed, but you can see maximum EC was observed in Dhauli-Ganga basin, whereas alkalinity in Parvati basin, and all the parameters at different sites were within the permissible limits specified by BIS and WHO. And the salient features of every basin, if suppose we see the impact, though we have assessed, we have found that 43 blazes are located in Sindh basin, Parvati basin 40, Dhauli-Ganga 26, Ganga Nadi 74, and Impal 44. And there are also hydropower projects lying in downslope regions. And based on the settlement pattern is also going to be affected along with the land use patterns. If suppose water resources are going to change. And if suppose we see the anthropogenic pressures in every basins, that you can see basin-wise, we have analyzed that waste problem, air quality, carrying capacity, loss of glacier area and volume, in its volume, we found in Sindh basin, and similarly impact on land use pattern, decreasing water discharge, loss of forest in Parvati basin, Ranga Nadi basin in Arunachal Pradesh, Jhum cultivation, reducing forest cover, Jhum cultivation again in Imphal basin, affecting water quality and drying of streams are the salient features. And we have also taken the public perception survey in Sindh basin of 650 households, 7 Ganga 373, all were of the view that climate change is one of the burning issues to them. As a result of that, their land use pattern is going to be affected adversely. Similarly, in headwater regions, non-glacier regions of two basins, Ranga Nadi, number 190 households we took. Imphal basin, 350 households we took. And here, since the glaciers are not the important feature, so but headwater regions are also going to be in transitional phases depending on the monsoon. And the land use pattern, the forest in Sindh basin changed 41%, 20% in Parvati basin, 11% in Dholi Ganga, 67% in Ranga Nadi, 30% in Imphal basin. Whereas the arable land, 14% in Sindh basin, 87% in Dholi Ganga, 74 Parvati basin, 17. Changed, I mean to say here that the forest land is decreased, whereas the arable land also is, decreased. This is the thing to mention. Land cover in the other basins, you can see some of the other glimpses because time is very limited. And I don't want to explain more. Just you may have its glimpses. And impact of hydropower projects and 77% in Sindh basin, more in between 100% observe that negative impacts due to hydropower projects. And the main features, cracks in houses due to blasting, drying up of water resources like springs, dust deposits on crops during blasting were the major component. And some of the macro invertebrates identified in the Sindh basin also, aquatic biodiversity, you can see periphyalic algae identified in the Sindh basin also. And based on this, because the data is still to compile, so the definite conclusions are yet to come. But along with this, based on our results, that we found that the people are interested to adopt some of the alternative livelihood options. You can see based on this capacity to building programs in every basin, in Gagangir, in Sindh basin, we organized this in second consultation meeting in Imphal during this date in 2017, third consultation meeting. And based on these meetings, we found that the people are interested to have the practices of some of the alternative practices like beekeeping and local, handicrafts, and so that they can supplement their, agriculture eroding or declining agriculture yield with this alternative livelihood options. So we found some of the conclusions you can see based on this in scarcity in drinking water supply, poor tourism development, unfair road connectivity, need upgradation of health services, need educational facilities in Sindh basin. And whereas in Imphal, we observed that excessive proliferation, choking, deterioration, water quality, degrading catchment condition and siltation, and dwindling fishery resources. Fumadi deteriorates habitat of Kabul Lamjao National Park, low diversity in Changaboom forest due to felling and burning for Jhum cultivation. Ranga Nadi, we found that scarcity of drinking water, deforestation, water logging, mining, non-plantation of native species, larva of dragonfly or Tasing reduced due to frequent use of pesticides and weedicides in Ganga Nadi basin, whereas in Parvati in Himachal, drying up of spring solid waste problem, need of microbial biocomposting from biodegradable solid waste, need to skill up the women for local knitting, beekeeping and embroidery to enhance their livelihood options were major suggestions proposed by the local communities. And among all the basins, agriculture practices are being affected due to climatic variability. People are willing to have capacity building or training in agriculture-based livelihood options, followed by embroidery and local handicraft. And based on this, then we organized the training programs on different aspects. Say beekeeping was one of the major major livelihood options considered by the local communities. And as a result of that, the institute also distributed some of the sample boxes to them, so that they can expand this activity and work on these activities. So with this, I think that stakeholders, consultation from capacity building workshop in Ganga Nadi basins told that Forest Department has framed guidelines for access and benefit between sharing of forest resources with community awareness programs. They realize to put forward promotion of livelihood framing in coordination with concerned department organizations is required. Organization of training program with the help of agriculture and horticulture department are required in different based on different issues. And with this, the participants, the main aim of these workshops were to improve the capacity building of the partners and to analyze the seasonal flow of river streams, which the data is still under pending and under process, and strategies and responsibilities, so that the proper livelihood options could be suggested in due time. Building could be enhanced. And with this, I would say that this is the summary of all. But in summary, I would let you know that climate change by our data as well as perception studies have definitely affected the water resources in the regions as well as their land use pattern, which need some of the policy implications which we are supposed to develop, and that is under developing condition this time. And this activity, I would like to thank National Mission on Himalayan Studies, which could support this project from MOA and Delhi. And thank you very much. And thanks here, Lord, for your kind patience.
Thank you, Dr. Kuniyal. And it was very informative and nice talk. And I think we have time for a couple of questions. So if there is any question, this talk is open for the discussion.
No questions, sir.
If there is no questions, of course, we can proceed to next one. No question?
Yes, sir. We can proceed.
Okay. Thank you once
sir.
again.
Thank you very much
for your nice presentation.
Thank you,
and now there is another talk by Dr. Asha Thaplial from Uttarakhand Space Application Center, Dehradun. And the title is Glacier Retreat Analysis in Context of Climate Change Impact over the Alaknanda Basin. Dr. Asha Thaplial.
Sir?
Okay, please share your screen.
Okay.
And you have 10 minutes, 7 minutes for the presentation and 3 minutes for discussion. So please conclude within the given time.
Nihal ji.
Hello.
Nihal ji, can you unshare your screen?
Hello.
आप अपनी स्क्रीन अनशेयर करो प्लीज स्टॉप द शेयरिंग ऑफ स्क्रीन कुनियाल जी
अभी हुआ नहीं
नहीं सर
ना
ओके आई विल
प्लीज स्टॉप शेयरिंग इट इज रिटन देयर स्टॉप शेयरिंग
ओके थैंक यू
Thank you very much.
Thank you. Thank you.
So you can share your screen. Okay.
Hello.
Yes.
Now my screen is sharing.
Yes, yes.
Okay. Good afternoon, everyone. Myself, Dr. Asha Thapiya, and today I will talk about the remote sensing based studies. And my topic is a glacier retreat analysis in the context of climate change impact over the Alaknanda Basin. As we all know that Himalayan glaciers are a storehouse of fresh water and play a significant role in influencing the runoff through the numerous perennial rivers flowing over the Indo-Gangetic plains. Glacier monitoring and management is extremely important in current scenario of climate change and water scarcity. To address this concern, the present study endeavors to find suitable methodology to quantify glacier area loss or retreat in the Alaknanda Basin. And in this study, remote sensing data sets and change detection approach are used in delineation of glacial boundary to estimate the total glacier area loss and retreat rate. Earlier, field work carried out by our team in year 2013-14. So we used that data for the validation and assessment over 2 glaciers of the Alaknanda Basin, which are the Satokanta and Bhagirathi glacier. Changes in the snow cover area and LST data is also assessed to understand climate change impact, and meteorological data which is derived from FART, temperature and rainfall is also assessed. Glacier ice velocity is assessed using SAR data for the 2 major glaciers. This is our study area, and this is the Alaknanda Basin. Mainly glacier retreat or glacier loss area study is carried out for the this catchment of Alaknanda Basin, and the area lies between the latitude of 30 degree 48 north to 79.84 east. Satokant and Bhagirathi Glacier are 2 major glaciers with the elevation ranging from 3200 meter elevation to 60 meter ASL. The elevation range of the Alaknanda Basin lies between the 3000 to 7000 meter ASL. For achieving different objectives, different data sets are used, and glacier loss area study, we use the data set of Landsat MSS, Landsat 5 and Landsat 8 for different time spans from 1976 to 2017, and S3 GTM is also used to generate the elevation profile. The snow cover and Landsat surface temperature is assessed by the MODIS data, which is a MOD 9A1 product of 500 meter resolution for the year 2002 to 2018, while Landsat surface temperature is assessed by the MODIS LST product of 1000 meter and for the same time period for 2002 to 2018. Glacier surface velocity is also assessed for the year 2017, and 12-day interval SAR data is used for this. Randolph Glacier Inventory version 5 is also assessed. Here you can see different time period data sets. This is for 1976, 1994, and for 2017. The remote sensing dataset selected for the mapping of glacier outlines fulfill the following criteria: minimum cloud cover, minimum snow cover, and identifiable glacier terminus in Landsat images. Because unsupervised classification produce so many errors, so NDSI approach is also used by taking the band ratio of TM4 and TM5, and a threshold of 2.0 is also applied. All the glaciers are demarcated and classified based on their size. For glacier change measurement and quantification, glacier outline of 2017, here you can see, which was overlaid on TM data of 1994 and MSS data of 1976. A bitemporal comparison between 1976 and 2017, as well as decadal change analysis, was carried out in 2 distinct time spans from 1976 to 1994, and 1994 to 2017. The overall glacier area loss has been determined by calculating the difference in the spatial extent of glacier in 1976, 1994, and in 2017. These are the results. You can see that based on the glacier size, the glaciers are classified in different sizes, less than 0.5. And here you can see in 1976, 6 glaciers are measured, but in 2017, it was 8 in number. It means the glaciers are increasing, but the reason behind this is the glaciers are fragmented in this region. And here in this image, you can see the snout position in 1994 is here, while in 2006, this is here. Total number of glaciers in 1976 are demarcated 40, which was increased up to 44 in 2017, but the area is decreasing over here. This is one of the another study in which Satopant and Bhagirathi third glacier are measured. And in Corona aerial photographs of 21st September 1968 having 7.5 meter resolution is used for the historical position, and this for 5.8 meter resolution of 2013 and 14, while and 2017 is used. Tatopant and Bhagirathi third glacier indicates that snout position retreated from 1968 to 2017 was about 23.2 meter and 8.2 meter respectively. This is our second objective, snow cover assessment. The snow cover area in the mountains frequently shift with period of time due to many possible reasons like circulation of wind and also with the change in temperature during snow melt season. Manas, a watershed of Alaknanda Basin, is used to examine the spatio-temporal changes in snow-covered area from year 2002 to 2018, and Mod 9A1 product was used for this estimation. As snow cover reduces with the time, I will see the result in the next slide, and each point of time melt can be related to air temperature. Since the meteorological data is not readily available, therefore, we tried to establish a relationship between the snow cover area and LST. This is the land surface profile, and here you can see from 2004 to 2018, and in different months, the LST is increasing towards higher altitude. Similarly, in 2002, 16 and 18, and similarly in 2001, 2008, and 2018 in the month of March. Here you can see in the March 2001, the snow cover area is this much, but when we see in the 2018, the snow cover is depleting. Here, this is the curve. When the LST is increasing, the snow cover area is depleting. This is the here. This is the month in 2004 and 2010. Here you can see when the LST is decreasing, snow cover is increasing. Sorry, LST is increasing, snow cover is decreasing. Similar pattern is observed in Zone 4 and in Zone 5. These are the temperature trends, and this data is downloaded from the SWOT. And here you can see in Zone 1, Zone 2, Zone 3, and Zone 4 and 5, the temperature is increasing from March to September, and similar pattern is observed in different years in 2011, in 2012, and in 2013. Here you can see in rainfall trends over 4 years in 2010, 11, 12, and 13 in different zones. In July and August, the rainfall pattern is higher in all the zones. This is the glacier surface velocity mapping, and SAR optic data is downloaded from Copernicus site for year 2017, 12-day interval data is acquired, and all the process is carried out in the Snap Toolbox software. And then ice velocity maps are generated. Here you can see the maximum velocity. This is the profile of the velocity. And maximum velocity is found in the area having highest slope. The maximum velocity profiles are generated here. 6 velocity profiles are generated. And the difference of glacial velocity is higher in August than September. And it was observed that the difference is higher in summer than in winter as a result of high melting and precipitation over there. Higher flow velocity in each region are associated with the highest topography. This is the summary. The results indicate the possible impact of increased temperature on snow cover, especially in the low-lying mountain regions. And in all the 4 zones show that increasing trends of maximum and mean temperature and decreasing trends of snow cover were observed during the winter and spring seasons. Glacier area has been lost at heterogeneous state since 1976 in the study area, and during the observation period from 1976 to 2017, glacier area changed from 81 kilometers square to 271 kilometers square, and a decrease of 10.38 kilometers square observed, and the number of analyzed glacier increased from 40 to 44 due to fragmentation. It was also observed that the retreat rate of SPT is much higher than DKG due to the fuel action of Bandhara scale and its confluence with the glacier meltwater associated with a high velocity movement due to sharp slope at the right margin of the snout of SPT, which signifies our study and the results. This information may be further used to analyze the climate change footprints such as the snow line movement, snow volume change, and glacier mass balance studies. And this study developed by the understanding of climate change impact on the Laknanda Basin by analyzing the basin characteristic and degree of glacier. Thank you so much for giving this wonderful opportunity to me to present my work over here.
Thank you very much. And it was really a nice talk. And we can have one quick question, if there is anyone. If there is no question, I think we should move forward.
Can I ask one question?
Yeah, one question.
Yes, sir, please.
Thank you, Dr. Asha.
Thank you, sir. Thank you so much.
So you have given one of the results that area vacated by this glacier is 10.38 with an uncertainty band of plus minus 6.9.
Yes, sir.
I think this uncertainty band is too high. Why it is so?
Maybe due to the technical problems of the data sets, because we done all this work during the based on the satellite data. Maybe we have to select more other data sets for this.
But I think we have to relook on this because it is too high. In the 10 kilometer square with an uncertainty of around 7 kilometers square.
Yes, sir.
It is too high. Okay, thank you.
Okay, thank you so much.
Okay, thank you very much, Dr. Asha Thapliyal, for your presentation.
Okay, thank you so much.
Now we move to the next presentation. This is by Rais Ahmad from University of Kashmir. And the title of presentation is Spatio-temporal analysis of glacier lake in Jhelum Basin, Kashmir, Himalaya, India. So, Rais Ahmad, is it present? Hello?
I think he is not online.
Rais Ahmad is not online?
I think, let me check.
If it is so, we can move to the next presentation.
He is not online.
He is not online. Okay, let's move to the next presentation. And it is by Swagata Paira, Birla Institute of Technology, Mesra. And the title of presentation is Simulation on NOx and Ozone during lighting event in pre-monsoon season by WRF Chen.
So this will be presented by Manish Soni.
It will be presented by Manish Soni.
Yeah.
Okay, so your time is 10 minutes, 7 minutes for presentation and 3 minutes for discussion, please.
Manish?
Yeah, yes, sir, I am online. And can you hear me, sir?
Yes.
Okay, sir.
Slide mode.
Yeah, just a moment. Okay. So the topic, hi, I am Manish Soni. I am from BIT Mesra Jaipur campus. The topic of my presentation is simulation of NOx and ozone during lightning event in during pre-monsoon season by WRF-Chem. So the motivation for this study is ozone is one of the greenhouse gases. It is present in the atmosphere as a shield to protect the Earth's surface from the sun harmful ultraviolet radiation. If this barrier weakens, we will be more susceptible to skin cancers, cataract, and human system damage. On the other hand, tropospheric ozone is a harmful pollutant. So it is very important to monitor ozone as it is so vital to life on Earth for both humans and ecosystems. So the topic is about the lightning. So what is lightning? Lightning is an electric discharge which is caused by an imbalance between a storm cloud and the ground or the cloud itself. It can start inside a cloud inside a thunderstorm also. The clouds get an excessive amount of positive or negative charge during the lightning, and this may be enough to destroy the air resistance which is present between the cloud and the ground. It can then stay within the cloud, which is called intracloud, and it can travel through the open air and reaches the ground, which is called cloud to ground lightning. So there are roughly 5 to 10 times as many as flashes that remains in the cloud as there are flashes which travels to the ground. So the individual storms may have more or fewer flashes reaching the ground. Lightning can strike when it is not raining or even before the rain reaches the ground. So the process of lightning and ozone formation is like this. The major precursors of ozone in the lower troposphere are carbon monoxide, hydrocarbons, and the NOx. Lightning can lead to significant increases in the NOx in the middle and the upper troposphere, and it can also contribute significantly to the columnar abundance of NO2. The lightning can trigger a temperature of around 1000 degrees Celsius, and it can break the nitrogen dioxide as well as oxygen. And when the temperature comes to normal, the nitrogen can mix with the oxygen again to form nitrous oxide. This is similar to the high temperature fuel combustion. The most sensitive area of the total ozone is located nearby tropics, about below 25 degrees north and below 25 degrees south. So this corresponds to the maximum of lightning emissions. So ozone formation is a complex process due to its non-linear chemistry and meteorology, and NOx play an important role in the photochemistry of the troposphere. These species can undergo the chemical reactions, and there is an interconversion between the NO and NO2 through the following reactions, which are specified here. And now the model which we have used is WRF-Chem, which is the next generation meteorological model, and it has been developed by NOAA, NCEP, and all these agencies. It is a limited area non-hydrostatic model, and based on the primitive equation model, it uses Arakawa C horizontal grid, and WRF-Chem is a model coupled with chemistry. This is the research methodology layout for the simulation study, and we have done a simulation experiment with WRF-Chem for NOx and ozone, etc. We have validated the ground-based observation. We have validated the model outputs with the satellite data also, and we have also carried out the sensitivity analysis with LNOx and without LNOx module in WRF-Chem. So this is the block diagram of WRF-Chem. And the time period we have chosen is 16th May to 24th May 2008 and 2009. There is an extreme event during 2009. that is Ayla cyclone. So we have concentrated over that. The domain we have used is single. Map projection we have used is Mercator. We have taken horizontal resolution as 27 kilometer, and the physics and the chemistry we have taken from Wong et al. 2015. So we have taken the chemistry boundary conditions from Moscow, and the lightning scheme which we have chosen is Price and Ryan 1993. The method of forecasting the LOX is first we have to do the flash rate comparison. So these flash rates are related to the fifth power of cloud top height. This is based on convective parameterization schemes. Second method is you have to predict the IC and IC by CG ratio, inter-cloud by cloud ground ratio, which is estimated with a fourth order polynomial of cloud depth, cold cloud depth, which is the distance between the freezing level and the cloud top. And then this parameterization is then generalized for the mentioned grid size during with the help of extrapolation. So what we have done is we have done the ozone simulations over India, and this is during 2008. You can see on the top left, you can see this NOx without the lightning module, and at the bottom, this is with the lightning module on. You can see the change in the concentration of NOx over the eastern states as well as at the Myanmar, nearby Myanmar, and you can see the ozone concentration at the top right for 19th May 2008, and similarly with the NOx module on, you can see the concentration of ozone is much higher. You can see nearby Myanmar also, and you can see towards the eastern states also the concentration is much more. So the model has high dry bars, so we have to look for precursors. They are also having dry bars. So we have done the lighting module on and off for using the WAFCAM module. So this is one of the event. And you can see that we have find out the bias over 2008 also with lightning module and without lightning module. And you can see on the top right, you can see the OMI NO2 vertical column density over on 19th May 2008, and this one is the bias from OMI NO2 minus WAFCAM. You can see there is much bias much bias due to satellite. Much bias at the lightning module. So 2009 was a peak extreme event. There is Ayla cyclone. You can see the formation of Ayla nearby Bay of Bengal, and you can see that without lightning module, the concentration is totally flat. You can see, and with the lightning module, you can see there is much more concentration of NOx on the 24th May 2009, and this one is the same picture. This one is the satellite data for OMI NO2, where you can see the white spaces is no data or missing data, bad data, and we have find out the bias at with the satellite data and the model output, and you can see there is much bias over the eastern sides as well as in the Indo-Gangetic plain, nearby Indo-Gangetic plain. So we have compared two satellite ozone toms, OMI toms and OMI, and you can see the effect of lightning module off and lightning module on. You can see the pictures are much relevant when the lightning module is on, and toms and OMI both clarify the results also, that this much is more, the picture on the top right is much more relevant than the picture on the top left with lightning module on. So we have regraded the data accordingly with the resolution of toms and OMI and find out the bias also. So we can see that with lightning module we can estimate the flash rate ozone concentration what is formed after lightning and before lightning. So this is much more relevant picture with the lightning module on 23rd May 2009. So these are my conclusions, that WRF-Chem was able to reproduce the event when lightning module is on, and the IC by CZ ratio need to be adjusted manually to match with the realistic results. So, and satellite data shows a match with lightning module on. And we can clearly identify the hotspots, and these are just the preliminary results, and we are continuing the research. Hello.
Thank you very much. I think we have concluded.
Yes, sir.
I think we can have one short question, if there is any question. So if there is no question, we'll move to the next speaker. And thank you very much.
Thank you, sir.
Manish Soni for your nice presentation. And our next speaker is Lalita Best from Himati Nandan Bhagwana Garhwal University, Srinagar, Garhwal. And the title of presentation is Contamination Assessment of the Potentially Toxic Heavy Metals in Road Dust Deposited in Different Types of Urban Environment over Dehradun City, Garhwal, Himalaya.
Hello.
So Lalita Best, please.
Hello, sir, I'm audible?
Yeah, you are audible.
My screen is...
Screen is visible. Yeah, it's fine now.
Okay. First of all, a very good afternoon to all of you. I'm Lalita Best, research scholar in the Department of Environmental Sciences, HNV Gadwal University. So today's topic of talk is contamination assessment of potentially toxic heavy metal in road dust deposited in different type of urban environment over Dehradun city, Gadwal, Himalaya. So according to ISO 1994, the dust are small solid particles, those particles below 75 micrometer in diameter, which settle out under their own weight, but which may remain suspended for quite some time in atmosphere. The particles of dust that deposited from atmosphere and accumulate on ground surfaces along roadside are called road dust, or road deposited dust is a heterogeneous mixture of different contaminants, including organic and inorganic, originating from natural as well as anthropogenic sources from the interaction of solid, liquid, and gaseous pollutant derived from different origin or sources. Road dust act as an important indicator of environmental pollution from atmospheric deposition, receive variant inputs of anthropogenic metal from various stationary as well as mobile sources, such as vehicular traffic, industrial activities, residential fossil fuel burning, waste incineration, construction, demolition activities, and the resuspension of contaminated soil. Toxic metal in urban areas are subject of great concern due to their non-biodegradable nature and long residence time. The presence of contaminants in urban areas for prolonged time, particularly in road dust, their close proximity to human population significantly increase the exposure of urban population to metal via through different exposure pathways, which are inhalation, ingestion, and dermal contact. Toxic metal can affect human beings in various ways by disrupting their function organs, disrupting nervous system or the endocrine system. This research is carried in Dehradun city, which is the interim capital of Uttarakhand. The Dehradun is one of the largest intermountain valley between the Mussoorie range of Lesser Himalaya to north and the Shivalik range in south. Which is located at altitude of 653 meters above sea level, and the area of Dehradun city is 300 kilometers square. The map shows the locations and study areas. In present study, road dust samples have been taken from 30 different represented locations from different type of land use, which are the residential, commercial, national highways, and mixed zone over Dehradun city, Uttarakhand, India. For sample collection, the samples are collected during winter season in 2019 January. About 100 to 200 grams of dust were collected by gently sweeping an area of 1 meter square along the road edge with the help of clean brush and dust pen. All collected samples were kept in sealed polythene bags to prevent further contamination and then stored in room temperature until analyzed. For the sample preparation analysis, firstly, the collected sample was sieved through 1 mm mesh to remove stone, leaves, and other fragments. The sample were dry in room temperature for 1 week and then sieved through a stainless steel sieve in two proportion, 230 micron and 63 micron to obtain fine particle. We used 63 micron for metal analysis. After that, 0.5 gram of dust sample were subjected to acid digestion using aqua-regia acid digestion in 3:1 proportion. After digestion, sample solution were cooled and filtered through filter using Whatman filter paper for number 42 in pre-marked test tubes, and the final volume is made up to 15 ml. The concentration of heavy metal was determined by ICPMS. To assess the heavy metal contamination in road dust, contamination factor, degree of contamination, and pollution load index are used. Hanks in 1980 reported 4 classes for the contamination factor index and the degree of contamination. The factor contamination factor is the mean concentration of heavy metal is divided by reference concentration of heavy metal. In this study, the reference concentration is the Indian natural soil background value. It is classified in 4 classes. If the value is less than 1, the contamination level is low. If it's between 1 to 3, it's moderate. If it's between 3 to 6, it's considerable. And if it's equal and greater than 6, it means the contamination level is high. For the value of the contamination degree, it is estimated as by the addition of all the contamination factor of all heavy metal. It is also categorized in 4 categories. If the value is less than 6, the contamination degree, contamination level is low. If it's between 6 to 12, it is moderate, and if it's between 12 to 24, it's considerable. If the value is equal and more than 24, the contamination level is very high. For pollution load index, which is described by Tomlinson et al. 1980, it is a geometric mean of all the contamination factor of heavy metals. If the value of pollution load index is less than 1, it means there is no pollution. If the value is greater than 1, it means that it means there is deterioration in site quality. And if the PLA is equals to 1, which means the baseline level of pollutants. Here are the results and results. This is the table shows the average concentration of heavy metal in road dust sample. By table, we can see that the iron found highest in road dust and the cadmium found minimum in all the sampling sites. If we see in decreasing order, Fe is highest, followed by manganese, zinc, lead, copper, chromium, nickel, and lastly cadmium. The table 2 shows the descriptive aesthetics of heavy metal concentration of road dust in different land use type. These values are compared with the background metal concentration of Indian natural soils as well as the world average shell values. By the table, we can see that the mean concentration of Mn, Zn, copper, lead, and cadmium are higher than the background metal concentration Indian natural soil, while the iron, chromium, and nickel are lower than the background metal concentration. For contamination assessment, the table 3 shows the contamination factor of heavy metal in each land use type. By the table, we can see that the Zn, Pb, and Cd are under very high contamination categories, value with more than 6, and Mn and Cu were under moderate contamination categories, the values between 1 to 3, while Fe, chromium, and nickel are under low contamination categories, value less than 1. In all land use type except commercial, where Ni is higher in moderate category. Lead is having highest contamination factor, while iron is having lowest contamination factor factor for oval or studies area. If we see in decreasing order, PB have the highest contamination factor, followed by Zn, cadmium, copper, manganese, nickel, chromium, and lastly Fe, iron. The table 4 shows the contamination degree and pollution load index in each land use type. By the table, we can see that the commercial areas have highest contamination level, followed by mixed zone areas, after that national highway, and lastly residential areas. It is observed that the contamination level in most of the location characterized as very high, with the contamination degree values over 24, and pollution load index is also found higher than 1 in all monitored 30 locations, which show the deterioration in quality of road dust over Dehradun city. And in order to establish the intermatter relationship in road dust sample, Pearson correlation analysis were performed for all representative location. By the table, we can see that Zn, Cu, Pb, Cd, and nickel, Ni shows positive correlation with each other, indicating same source origin, which could be vehicular sources like tire and brake pad wear, fossil fuel combustion. Zn and Cu shows also positive correlation with each other, which shows same source of emission, probably tire wear or brake pad wear. Pb and Cd also shows positive relation. Also, Cd and Ni shows a positive correlation, indicating same source of emission, which could be vehicular paint or road paint corrosion. Fe and Mn shows strong positive correlation, indicating same origin of source, which could be natural in origin. We can see that the PB shows negative correlation with most of the metal, which suggests that different origin of PB in road dust. Major input of lead in road dust could be linked to various vehicular emissions sources coming from automobile paints, flakes, spray painting machines. Also, PB is found in significant amount because of the past deposition and from the lubrication and engine oil combustion, in which lead is present in trace amounts. The agglomerated the cluster analysis shows 3 categories. First, cluster 1 comprises copper, Zn, Pb, which mainly vehicular generated. Copper and Zn family came from the abrasion of brake pad and tire vehicle. Pb, although Pb is banned as an additive in petrol, but it shows the high concentration of Pb shows the long half-life of Pb in soil. Cluster 2 source the nickel and cadmium. These metal rotation to anthropogenic sources, which are associated with traffic emission, burning of oil, and corrosion of paint of vehicles and road. Lastly, the cluster 3 comprises iron, manganese, and chromium, which are considered to come both from natural as well as anthropogenic processes. These mainly influenced by geogenic processes. At last, the conclusion, this study presents a comprehensive assessment of 8 potentially toxic heavy metal pollution in the road dust over Dehradun city. According to the study result, iron is found most abundant heavy metal, and lead was found the most contaminated heavy metal among the 8 studied metal in road dust over study area. Average concentration of all 8 metal in road dust found higher than the Indian soil background, which indicate that dust quality around the road are degraded by heavy metals. The major source of heavy metal pollution road dust are vehicular emissions, mainly via fuel exhaust, brake pad wear, tire wear, and corrosion of metallic parts and paints. Majority of heavy metal like Zn, copper, lead, chromium, nickel, and cadmium are anthropogenic in nature, which are basically came from vehicular and industrial exhaust. But some of metal like iron and manganese are primarily geogenic in origin. Based on the result, the overall pollution load index value from different land use type is greater than the baseline value 1, which indicate that the heavy metal degrade the road dust quality over Dehradun city, which ultimately harm the health of human being. Therefore, a continuous monitoring of heavy metal in road dust should be conducted at regular interval. Thank you so much.
Thank you, Lalita, for this nice presentation.
Thank you, sir.
And I think we can have one question. If there is any question from the audience.
Professor Ramolaji, yes, I'm Punia.
One question. Okay, please.
Yeah. Miss Lalita.
Yes, sir.
So how do you measure the dust from road?
Sir, we collect dust from road by the use of a brush and dust pen. Then we transfer it to laboratory and sieve it through the sieve, and then we measure it by the.
Okay.
Hello, sir.
Yeah, I am listening.
Yes, sir.
Yeah.
Then we measure it by weighing machine.
Weighing machine.
Yes, sir.
So why I'm asking, would it not be appropriate if suppose you could measure it through respirable dust samplers?
Yes, sir. But I'm working on road deposited dust.
Okay.
Yes,
deposited
sir.
only, not
yes,
in
sir.
ambient air.
Deposited dust, which is deposited on the road surfaces.
Okay. So have you followed any of the scholar regarding this, or it is your pioneering effort?
Yes, sir. It's my pioneering efforts because in road dust there is no work in Uttarakhand.
Okay. Okay. So that's why I'm asking. This is very good. Yeah.
Yes, sir.
Yeah. Thank you.
Thank you, sir. Thank you, sir.
Okay, thank you very much.
Thank you, sir.
And I think we still have 3 presentations, but the time does not permit us to continue with this session because it was supposed to close at 1 o'clock and now it is about 1:45. So we are already late by 45 minutes and 3 presentation means half an hour. So with the permission or with the consent of the organizing committee, we decided to postpone these presentations for the next session, which will start, I think, of course, the organizer will announce it, but as per the schedule, it will start at 2:30 p.m. And before concluding, certainly I would like to thank to the organizers of this conference for giving me the opportunity to chair this session, especially Dr. Dumka and Dr. Alok Sagar Gautam. I am very thankful to
Thank you
both
so
of
much,
you
sir.
and
Thank you so much.
the organizers.
Thank you,
And now
sir.
I hand over the dais, or now here it is a platform to the organizers for the further announcement.
So thank you, sir, for nicely organizing this session. Thank you very much. And now we'll break for lunch.
And we'll meet again at 2:30, is it?
Yes, sir.
Yes.
Okay.
Sir, we will.
Thank you very much. Thanks, everyone.
Yes, sir.
And thanks, everyone.
No, sir, in that session, we will take the invited talk first. Hello?
Yeah.
Sir,
Yes, sir. Yes, sir.
We'll take the invited talk first. Then remaining 3 talk.
Okay. Thanks, everyone, once again.
Thank you.
Thank you so much, sir. Thank you
very much.
Yeah.
Hi.
You're the only person here.
Yes.
What is going on? Did you eat?
Yeah, they will come in 5 minutes. It is lunch break.
Hello, can you hear me? Can you see me?
Yes, yes.
Now I think you can see me.
Yeah, hello, Nikos.
Okay, good.
We can see, we can hear also.
How are you?
Αφεντικό σε σένα μιλάει.
Ναι, πες μου, ρε.
How are you, λέει, σε σένα μιλάει.
Ah.
How are you?
It was a noisy atmosphere here. Yeah, fine, for the moment, fine.
What about the COVID-19?
Oof. I think situation in Greece is, yeah, I don't know if it's somehow better or, but it's, yeah. It's tricky, especially in August. The situation was really at the end, almost at the end. So
yeah, here also we have very difficult time now. India is number 2.
Yeah, but at least you are close to the countryside, because here we are in a big city, and we don't know.
We are in very remote area.
Yeah. I know. And this is you have less contact with people, and this is not bad at all.
Yeah.
Dimitris told me you are at 2,000 meters of almost 2,000 meters of altitude. Yeah. So
yes.
At least you have a COVID-free fresh air.
Not COVID-free, but we have some cases in city.
Yeah, come on, especially when it comes from the free troposphere, it's COVID-free. I cannot believe that there are people living higher than you.
Basically, we are in a remote area, so that's why this is advantage.
Yeah.
So, Umesh, there is in the news, India is every day in the Greek news, and today there was a heading saying good news for India. New infections reduced to 84,000 people.
Pardon?
Oh, yeah.
The heading in the Greek news today was like this. Good news in India for COVID-19.
Oh,
daily infections reduced to 84,000 persons.
Yeah, we are 85,000 or around 1 lakh cases per day.
Yeah.
I start sharing the presentation. Can you see it?
Yeah, we are.
Yeah, sure. You can use the full screen. That's right. Very good.
It's fine. Okay, good. Okay, very good.
It's visible.
इसको दिखाओ जरा हमारे यहाँ अगर देख रहे हैं वीडियो पहले वीडियो वाला तो फिर कर देना शुरू में पहले इसको तो मैं रिकॉर्डिंग कर रहा हूं बोलना रिकॉर्डिंग तो ठीक ये नहीं रिकॉर्डिंग
Hello, Nikos.
Yes.
Oh,
yeah, we are going to start.
Okay, I'm ready.
Okay, good afternoon to all. So I am Dr. Narendra Singh. I will be chairing this session along with Alok Sagar. And Dr. Poonam Semwal must be there. Hello, Poonam, you there?
Yeah.
Okay. So I would like to give a brief introduction of Professor Nicholas Mihalopoulos as part of my duty. So he is the head of the Chemical Processes Lab in the University of Crete and director of the Institute of Environmental Research and Sustainable Development, National Observatory of Athens. His research areas are atmospheric chemistry and physics. He has published over 250 articles in scientific journals and being one of the most or highly cited researchers in the field. So he'll be talking about EM-induced oxidative potential with particle chemical composition and sources, year-long measurements from Athens, Greece. So Nicholas, I would request you, so please try to keep it in time. We are running too late. Our previous sessions, some of the lectures are still left. So over to you, Nicholas, please.
Okay. First of all, I would like to thank you for the invitation. It is a great pleasure for me to give this talk. Unfortunately, it's not so much in line with the subject. Talk about Indo-Gangetic plane, but I will talk about something that is quite hot. I already have seen that yesterday there were 2 presentations on that subject, and has to do with the induced potential, oxidative potential of particles. In other words, with ROS, reactive oxygen species in the atmosphere. And I would like to share with you my experience or our experience of the team of what is happening in Athens and using Athens as a test case for that type of measurement. This is the team. I would like to acknowledge the thank of several colleagues that they have worked on in that subject. There is already 1 paper came out, and there will be at least 2 or 3 because they are under preparation. And before giving you details about how we're doing the measurements, just I would like to share with you a view from where I am here. And you see Athens. Our institute also, it's in a hill of 500 and something meters. And from there, we have a nice view of Athens. Up, you see Athens with a pollution, under pollution event. You see this gray cloud here, and this is a clean day. You can see the sea here, and you see Athens, which is for the area, it's quite a big city with almost 4 million inhabitants. For the Indian, the standard Indians, the standard of Indians, it's a medium-sized city, but it's also meteorology plays a very important role. And this is where we're doing measurements. Measurements are conducted downtown Athens. There is at the historical center, it's a really nice place. It's as you can see, I don't know if you can see here, it's just opposite to the Acropolis. So it's exactly downtown at the historical center. It's an area where it is not inhabited. So you see around all the people living there. And so it can be considered as an ideal urban background place. And there we have the stations. We're running a lot of instruments there. among other SCSM, for chemical, physical characterization. We are collecting filters, etc., etc. And we are analyzing the filters by using, for us, we're using a semi-automatic method, which developed in Atlanta by Professor Nene's group. And we are using, and you will see the big advantage compared to the other techniques. Before talking Athens, I would like to show you, we did a lot of works to have an idea about the representativity of our site. This is a mapping that we did in Athens by using black carbon. The take-home message, because it's a complicated figure and I don't want to spend a lot of time, the take-home message is, here is our place, sampling site, CO, and could be quite representative in terms of levels, but also in terms of seasonal, of diurnal variation of what we see in the greater Athens area, in an area of more than 3 and 3.5 million inhabitants. So I will start rapidly to give you a snapshot of what are the sources of aerosol in Athens, and I will then finish with reactive oxygen species. So we have, first of all, by collecting filters and by doing a complete chemical analysis, we have been able to fill the chemical to do a mass closure. This is the mass closure experiment and the various compounds. And these are the PM levels. These are PM 2.5 levels. You see the relative high values. These are monthly mean values during winter time, and which is mainly due to wood burning, to heating, and the relative low values that we have during summertime. And by doing a PMF analysis, these are the main source that we found for Athens. I think this table is the most important, and I suggest you to focus there. In our sampling, we separate the sampling during daytime and nighttime. And here you can see, for instance, that during nighttime, the most, in parentheses, are the percentages. During nighttime, the most important source in the area is wood burning. Wood burning can account for almost 40%, which is a huge number, of the total PM mass. And then it's the vehicular emissions, secondary emissions, oil combustion, dust, sea salt unaccounted. And even only during nighttime can be 11 microgram of cubic meter, which is quite high for PM 2.5, are due to the wood burning. And this is during daytime. And you see, even during daytime, biomass burning is the same importance with vehicular emissions. After doing this type of work, we make more effort by using to have a high temporal resolution measurements of atmospheric aerosols, and by using the ACSM. Again, I would like to give you a flavor. Don't want to spend a lot of time. And this is the chemical composition of the aerosols on the annual basis. You see, organics are by far, organics and black carbon are the most important compounds, but especially if you focus in winter, you see that during winter time, organics can account for more than 50% of the mass. So plus elemental carbon, it's almost 20%. Also, these two compounds, organic and OC and EC, can account for almost 70% of the mass. And there you can see the seasonal variability of the main class of compound. This is organic POM. These are sulfate and ammonium, and this is black carbon. You see, for instance, for the OM or POM and EC, exactly the same seasonal variability with quite high values during winter time. You see, during winter time, as a mean value, we have values of the organics that they can reach 10 or 15 or even 20 microgram per cubic meter. And every year, these are the number of events. We consider events all these situations with POEM exceeding 100 microgram per cubic meter. So you see that due to wood burning, almost every year we have 8 to 10 events, and the situation is continuing, 8 to 10 events with concentrations exceeding the 100 microgram per cubic meter, and this is mainly due to wood burning. Here also you can see the factors that we have identified by using the SOFI software for the ACSM. Again, you see wood burning, which is and this is only primary wood burning, 12%, which is similar to traffic, and the semi-volatile and the low volatile. But from the analysis that we did, I don't want to give more details. For the analysis that we did, both the semi-volatile and the low volatile are highly linked with wood burning. And here you see for all these substances the diurnal variability. Clearly see for the semi-volatile and the low volatile the higher values during nighttime. During summertime, you see we don't have anymore the wood burning, but we have again cooking. Cooking, it was the other big surprise. During both periods, cooking has a high contribution, can account for almost 12%, and it's almost of the same importance or comparable importance compared to the traffic. Here is what I said, that during winter time, the semi-volatile, but even a big part of the low volatile, it's linked to the combustion, because we had excellent correlations with tracers like BC wood burning or NSS potassium. We are doing measurements of NSS potassium also in high resolution measurements by using pills or levoglucosan or the MZ60. So by having this idea about the sources in Athens, with special emphasis of the role of wood burning during winter time, the next step is to see what is happening about ROS. What is the situation? What is the oxidative potential of these aerosols? This is the technique that we're using in the lab. It's a semi-volatile technique. So what is the principle is the DTT. It's using the DTT, and we are having a piece of filter, and we are analyzing. And this is just to have an idea. And this is the time of spectra that we see. We see the evolution of DTT versus time. This is a filter blank. You see there is no big variability versus time. And this is a real sample. And it's especially in that case, it's a sample with high DTT activity. You see the decrease of the DTT activity versus time. And we are using this decrease of DTT activity versus time to estimate the ROS. And we are able to run a big amount of samples per day, the same system, same filters, the same way, which give us a quite high reproducibility. These are the results because initially we have started by doing fine mode, the coarse mode analysis. We did for a period of almost few months to see if there is something interesting in the coarse mode. And what we have seen that the coarse mode can account for less than a third of what we have in the fine. So for that reason, we quit and we focus mainly in the fine mode. So you see here the annual average of the fine mode, 0.33 nanomole per minutes per cubic meter. And the coarse mode is almost three times lower compared to what is happening in the fine mode. And this is until 2018. Actually, we have a complete time series until 2020, and we are still continuing. And we have exactly the same pattern. The high values during winter time and the low values during summertime. Again, I recall you that we have two distinguished sources. During winter time, we have mainly local influence, with the biggest influence coming from heating and especially wood burning. And during summertime, the biggest source is the regional source, the long-range transport. Here are the seasonal variability, the months. You see the high value during summertime. And also you see that is quite repeatability. We have not so big changes as a function of time. The all months and the high values during winter time and the low values during summertime. So then what we did, we tried through techniques like multi-regression analysis or linear analysis or Pearson correlations to understand what are the sources, what is the origin of this ROS value, and we try to reconstruct by doing multiple regression analysis ROS levels during summer and during winter time. This is not a big surprise. We have seen, first of all, a very good correlation, almost excellent correlation with black carbon, and which is, although high correlated during winter time, during summer period is less correlated with DTT, but in general, good black carbon seems to be a key element to explain the ROS variability. Also, during winter time, we have the so-called smoke events. These are events with low wind speed. And as a result, here it's a nice example of what we see as a function of wind speed. This is black carbon as a function of wind speed. You see, especially for low wind speeds, we have very high black carbon measurement levels. We can even be above the 10 microgram per cubic meter. And we have put emphasis on that, on these events that we call them smoke events, which are associated with low wind. And again, you see the nice variability of the DTT activity as a function of the wind speed. This is during daytime, during a case of non-smoke event, during nighttime, non-smoke event, daytime smoke event, and nighttime smoke event. You see the difference, almost a factor of 3 or 4 for the same period under the occurrence of the so-called smoke events. This is the result of the linear regression. We try to understand the source, the reconstruction, not so bad. Still things are missing, and you can see here. And this is, first of all, was the big surprise. Almost 50% of the ROS activity was found to attributed with regional aerosol, means processed aerosols. Aerosol has with the aged aerosols. And then the two big sources are wood burning, accounting for almost 10%, and also traffic. And we have a 30%, which is unaccounted. And actually, we are doing additional measurements, especially we are focused on trace metals and polyaromatic hydrocarbons to be able to fill this gap for the undefined compounds. Conclusion. We have seen that ROS is presenting a seasonal variability with much higher values in winter. The period when local sources are more important, the period when we have low wind speed, and the period when meteorology, especially the meteorology around Athens, enhance the possibility to have accumulation stagnant air masses. Coarse activity is at least a factor of 3 smaller compared to the fine one. Wood burning and traffic can account more than 2/3 of the ROS variability in wintertime. And we have seen that also as a mean value, it's 20%. in summer, long-range transport, so aged aerosol, are playing an important role. And as I told you, there is work in progress with metals and polyaromatic and especially nitro compounds. And I would like to finish with another picture. This is not from Athens. This is from Crete, where I'm professor. And thank you very much all for listening to me. And again, thank you, Efcharisto in Greek, for the kind invitation.
Thank you, Nicholas, for such a nice talk, and moreover, in keeping it within the time allotted. So we can have a quick couple of questions.
Can I ask one question?
Yes,
please, go ahead.
Yeah, thank you, Professor Nikos, for the nice talk. I noticed that most of the results you have shown are volume-based TTT activity you have used. So have you also tried to use mass normalized TTT activity?
Yes.
Because we do such studies over India, and we have noticed that DTT, volume normalized DTT, is usually correlated to all the species which are major species of PM 2.5. That means if DTT, volume normalized DTT is correlated well with PM 2.5 mass, then it will correlate with the major species. But if you go for mass normalized, then you actually see the effect of composition.
I see. Yes, we have tried both, and we prefer, at least in the paper, to have volume because we would like to have comparison with the work already published. But now indeed I have seen there are also works, quite big number of works with mass, and then in the next paper we can try also what you suggest.
More question? Okay, thank you, Nicholas. If there are no more questions, and let us thank the speaker. Thanks for your nice presentation once again.
And again, thank you for the invitation. Okay, I stop sharing.
Yeah.
Good.
So now our next speaker in the line is Professor A.P. Dimri from School of Environment and Environmental Sciences, University of JNU, Jawaharlal Nehru University, Delhi. And he is basically having diverse research interest, but his main interests are basically regional climate modeling, climate dynamics, and variability, and of course climate change. So climate change in the Himalayan region is also one of his interests. He works a lot on western disturbances and other meteorological phenomena associated with Himalayan region. So Professor Dimri is one of the editors for Nature Scientific Reports, and also he is editors for many other journals. So he's a very renowned scientist in the field of climate change. So Professor Dimri, are you able to listen us?
Yeah. Can you listen to me?
Yeah. Please, you are audible. So I would request Professor Dimri to go ahead with his deliberations.
Yeah. Thank you, Chair. I hope all are listening me. Respected Dr. Dipankar, Dr. Manish Naja, and many of my friends I'm meeting here. Can you see my screen I have shared?
Can you make it kind of full view mode, full screen mode?
Oh, okay. Sorry. Yeah. Is it okay?
Yeah. Now it's okay. Now again, it has gone back to the same state.
Okay.
Now it's okay.
I chose to talk on climate in that sense over Himalayas, and Aris is doing a lot of aerosol and good work apart from other physics and other issues. And I'll be speaking here on the climate over the Himalayas. Somewhere, climate of the Himalayas, when we are talking, it is kind of inculcating various processes over the Himalaya, and it will be in the interest of the present discourse that how this climate is having various scale interactions. They are very well-known facts, features. Water tower, it has been told a water tower by various people. Some people also say that it is a pole, third pole. But what I want to say, it is having a very unique geomorphological positioning, which in the paleo sense, when there was no Himalaya and due to the tectonic evolution of Himalaya has come 50 million years back, and primarily from last 15 million years back, a lot of processes started occurring over this region. And that's when the monsoon is first reported, and so on and so forth. And it also not affects only regionally or in subcontinent. It affects globally when there's a large-scale circulation is moving around from one place to one other place. And in due course of time of the recent debate of climate and or climate change, there is a various impacts due to the presence of Himalaya is seen across, and it will be very imperative and urgent to say now if it has an impact, there will be a downstream impact to the social societies, economics, and so on and so forth. So I'm keeping today a very limited overview of the role of Himalaya as far as the climate is concerned over this region, and I'll be talking a bit of the climate change, that how in future it's going to impact them. So this is the Indian Himalayan region, which is generally impacted or represented or discussed at various scales, and it has a elevation. You will see that north-south elevation or east-west elevation across, which is running from 500 meters to 6,000 meters. It's not only this topography, which is like looks as if elevation is increasing. There is a lot of land use, land cover changes are happening from east-west, and some of the changes are at geological scale, some of the changes are at the vegetation scale, and some of the changes are very smaller scale. Very recently, we are working on the pine oak conflict with Jimmy Pant. I can see Dr. Kunial is there. So how the microclimate is changing, that's also very important as far as the vegetation and environmental evapotranspiration and so soil moisture concern is there in the southern foothills of Himalayas. Whereas if you go the higher elevation of this, you will find that there are different changes as the elevation is differing from lower elevation to higher elevation. So what is the climate uncertainty? I would not say now that's unfortunately, but definitely if you look at the precipitation graph overview, these are the three sources I have picked up from three graded data, which is Aphrodite, GPCC, and CRU. These are the observational regraded analysis we call, and most of you must be using any one of them or maybe all three of them, and there are many more also. Here itself, if you look at these three observational inputs, we find that they are in spatial distribution is very, very different. So in observation itself, there is an issue that we have very less observation over these regions. And by virtue of that, the synthetic data which I am presenting here, we find that there is a lot of spatial distribution is happening. And if we come down in the precipitation climatology, if you look at the altitudinal uncertainty, that is the one key graph I would like to say that in the foothills of Himalayas, the elevation dependency I am showing that from 0 meter to 7,000 meters. If you look at the foothills of Himalayas, your spread of precipitation is more heterogeneous. It's spread at longer millimeter per day. But as we climb up in the Himalayas, mid elevations, you see that there's a weakening of the precipitation amount. But as you go in higher Himalayas, or the region of study I'm referring as a higher Himalayas, it's Hindu Kush. So in higher Himalayas, when you go, we find the concentrated distribution of precipitation in the higher Himalayas. That is one. So it means that when I talk in the precipitation following mechanism, it means that precipitation forming mechanism at the lower elevation is more complex than the higher Himalayan region. And interestingly, if you look at the graph precipitation trend there, we find that precipitation trend is kind of decreased in last 30 years in the foothills of Himalayas, but the mid elevation, which is at roughly 5,000 meters plus minus, we find that you have a so this is the basic climatology I am just sharing with all of you. And if you look at the temperature graph in the right hand side, I use seasonal averages from monsoon, pre-monsoon, first winter, then vertical column, then pre-monsoon, and then monsoon, and then at last the post-monsoon. We find all the regraded analysis available across. I have taken CRU, I have taken Afrotemp, I have taken University of Delaware, and so all the observational analysis has a very different kind of distribution all over the region of the Himalayas. Somewhere it's some input is showing warmer, some inputs. So there are a lot of heterogeneity in itself embedded in the observational analysis. However, the vertical lapse rate, which is seen in the last panel in the lower, it is showing that there is a decrease as we go up in the vertical. And I would like to say that whoever is the atmospheric scientist here, that in Himalaya in particular, we found in due course of research that conventional atmospheric lapse rate doesn't work. So we have devised that there is a slope environmental lapse rate because the valley effect also come horizontally there. So fluxes are getting exchanged, and I'll not go in those details at the moment. So to start with, we started the Cortex South Asian domain. I think all of you must be knowing because various people are using this data extensively. Right now, I'm referring only 11 model, but they have gone to 16, and now we moved to Cortex Core. And in particular, over Himalaya, we are planning to run on the 11-kilometer model simulation in future, which will be most probably available by the fall of 2021. Because 44 kilometer, which we have used, was not also able to provide a good justification of the physical processes over these regions as far as the various model physics, model environment is concerned. And if you look at the comparison among these models, we find that some of the model is able to capture the monsoon precipitation, and some of the models are totally capturing it, but there is a lead and lag. Some of the model are talking before May, and then they are drying up. So most of the model have a very dry precipitation bias. They are warmer, and in the foothills of if you look at that, they overestimate the larger part of the precipitation. So what we found in the course of this, that when the precipitation flow, monsoon flow, which hits from the southern flank of the Himalaya, the precipitation mechanism within the model environment makes precipitation faster as compared to the natural environment. So there is a lot of uncertainty possibilities there because of the representation of the physical mechanism and physical processes associated with the orographic forcing, interaction, land use, land cover, representation in the model physics, and so on and so forth. Again, if you look at the various models, they have a very large variability as compared to the observation. Here, these two bars I am showing the various statistical analysis. I would like to draw your attention to the scatter plot. If you look at, there are the dotted black plot, the scatter plot. What we found in this scatter plot, that most of the model could capture the lower intensity event in the precipitation, which we see here very distinctly. But as we move to the higher precipitation event, mostly above 10 millimeter per day cumulative precipitation, they are deviated from the model environment to the. So for a smaller event, these models are good in the Himalayan region. I am not going to the bias correction for hydrological purposes or glaciological purposes, matter of fact for other purposes. But there is definitely a very huge uncertainty. If you look at the last uncertainty plot here, we find that there's a lot of uncertainty when we compare the standard deviation here is ranging from, and in the case of Northeast, we find that there is a much variability as we move to the western side. There's a, so though there are various models and they vary by capturing various aspects of the precipitation climatology over space, over time, but all the models are consistently wet over the region. So some few of the interesting conclusions are like that why the Himalaya is reflecting in this way, and what is the mean ensemble we have to take. And then uncertainty exists there, as we distinctly see it here, and the best model we could try to do it. Similarly, in case of temperature, when we evaluating, we find that higher elevation regions are colder in the model, and lower elevations are warmer in the model. And that is one of the reasons that when you have a warmer event, convection is captured in the lower elevation as compared to the natural environment. So your precipitation mechanism is faster and more intense in the model environment as compared to the natural environment, because model shows that their lower elevations are having more temperature and higher temperature. So these are the uncertainty in the spatial distribution of the seasonal variation in the model. If you look at that, and we find that model is distinctly doing similar distribution as far as their annual March is concerned. If you look at the cold bias, though the most of the model are colder, But if you look at their march, it is very, very similar. I'll come to these, why we are doing this later to clarify. If you look at the Gaussian distribution, somewhere there is a mean is matching with the model, somewhere this is a kurtosis, spread is more, somewhere their mean is matching, and finally the altitudinal distribution in the bias, because that is the reason that we are looking for what will be the altitudinal distribution. So maybe many of you are talking why we are looking for so many models, right? Because we want to know the future. And hence, if we know the uncertainty well, if we know the weaknesses or goodness of the model well, we can talk on the climate change, because the basic agenda is to look at the future, how the climate change will be there, how will the impact will occur in the future coming time. And that's why there are so many models we are trying to run. And before I presented that how good and that bad model will be. And based on these good and bad model, then I'm representing few of the slide at the Himalaya as well as the basin scale today, that how these representation will be helpful to assess the future in coming time. So if you look at the near future, 2020 to 2049, in the percentage in coming time, June, July, August, September, most of the model and ensemble also is showing that northeast region of India is likely to get drier and drier. Or most of the model, if you look at the brown color here, you see that northeast, there will be a decrease in precipitation in the monsoon time, and this Western Himalayan or Central or Western Himalayan region will have increased intensity of precipitation. I'll not go in this analysis which we have done. That is one of the reasons that maximum amount of precipitation is moved from Mosinram, Cherrapunji to Mosinram. And it means that monsoon, which used to encroach to the deep northeast region, is no more going there. And of course, there is we also saw that there is a kind of westward shift of Indian summer monsoon dynamics is happening. In the long time series plot, if you look at there is an increase of precipitation and associated variabilities happening in the future. But of course, this is highly uncertain. So whenever we are using this product for any kind of analysis, we have to be very careful of this uncertainty and these non-linear dynamics available in these. And if you look at the elevation dependent changes and the percentage trend, delta trend from present 1970 to 2005, that is the present I chose as a baseline period, we found that as we climb up in the elevation, precipitation changes are not very much and distinct. They are almost similar, but in the lower elevation region in different RCPs, we find there's a huge amount of variabilities happening, and it may happen in due course of time that lower elevation is likely to have more amount of drying as compared to the higher elevation, because I'll come to the warming rate later. And we have to remember that as far as the monsoon is concerned over the Himalayan region, particularly we both have to look moisture and temperature together. Moisture, when I say it's a water vapor to liquid water and an exchange in the phase, and precipitation is a final outfall of this. So in case of temperature, we see that most of the seasons, we find that the DGF winter, March, April, May, June, July, August, September, these four panels distinctly show that there is an increase of temperatures happening, all averaged, is partially average temperature I am showing here. And the trend are at different slopes, and they are all significant to the level. But interestingly, the vertical elevation dependent warming, when we are showing in the ensemble region, we find that higher elevation regions warming rate is more than the lower elevation region. And if it happens in that case in the Himalayan region, we will find there will be an impact on the snow line, there will be impact on the vegetation line, and it might have an impact on the animal kingdom also, which are the wild animals which are living in the forest regions. So these are the very critical findings we have seen over these regions of Himalaya. And if we come to very specific reason for the changes of the environmental region over the Himalayan, we analyze that if there is a decrease of temperature at the lower elevation, warming at lower elevation than the upper elevation, we found that there are role of the cloud is playing a very important role. It means that cloud is hanging up in the free atmosphere a longer time, and by virtue of that, in the mid elevation region, roughly up to 5,000 meter elevation, we find that the incoming long wave radiation from sun is stopped, and hence these clouds are playing a very dominant role in determining these things. And secondly, the surface albedo is also playing a very important role. I assume that these some of the processes, I am not going in much detail, but these are the two factors we find: the cloud formation. So your lifting condensation level is kind of playing a very important role, which is determining the cloud base. And we gave a kind of a hypothesis. Of course, I am telling in hypothesis because we are talking in mostly from the model feedbacks, and we have a limited observation like Karakoram anomaly, most of you might have heard. And there is some work of the aerosol also, background aerosol people have done and like that. If you look at the panel A, we find that the temperature is colder over the Karakoram Himalaya. This is very, very unusual. You can ask me that I was telling this warming is happening. But here we find that the Karakoram, the temperature of the skin temperature is colder. By virtue of that, there is a likelihood of that snow, whatever form it comes, liquid precipitation or solid precipitation, is likely to increasing trend we have noticed. By virtue of the increasing trend, we find that short wave radiation trend is positive. More short wave radiation is going back to the free atmosphere, and kind of it is supporting the existing of Karakoram anomaly, and it is supporting the growth of the mass of Karakoram, because most of the energy which otherwise could have been captured in the glacier mass is getting reflected back to the free atmosphere. So that is one of the hypotheses we have provided over the Karakoram region, but it needs to be justified with the corresponding observation in that sense. In Ladakh, if you look in detail, Karakoram is in black shape and Ladakh in the back slope, and we found that there is a lot of change of precipitation happening. And I chose these two regions because they are a very, very sensitive region, and biodiversity point of view, the animal point of view, or land use point of view, water point of view. And we found that this cold arid region and Ladakh region, though being very, very adjacent, they are not behaving similarly. So this is a very curious to me why these two adjacent regions like Delhi, Gurgaon, or like Delhi, Noida, they have very close proximity to each other, but they are not behaving like any similar, not in winter, not in summer. So that's very curious here, which we are still studying, that why the near surface temperature and the Karakoram and Ladakh are very, very different over this region. So we are still working, and based on this, we compared this precipitation record with the elevation, and we found that precipitation over these regions, I'm not going into the liquid water or solid precipitation, over these regions are varying very, very differently in monsoon time. Monsoon, we have to understand that winter precipitation is generally by western disturbances, and western disturbances yield precipitation from the top over the region. Whereas Indian summer monsoon is 850 hectopascal, which comes from down and brings the moisture from here. So these are the two controlling factors which are providing most of the elevation ranges in the cold arid region receive higher precipitation than Karakoram, right? Except over the lower. So these analysis we have seen over these two regions. So I have touched upon here very briefly, and then this will be an interest to show that aridity climatology or aridity trend, when you see over these regions, we find that the Ladakh region is becoming less arid in last 30 years trend, which is significantly we are talking, whereas the blue color, which is in the higher Himalaya, we found the positively. So aridity is a negatively influenced. So we find that aridity over these region is increasing. So trend is increasing over the Karakoram. So it means from somewhere aridity is coming over this Karakoram as compared to Leh Ladakh region. Coming to Indus Basin, which is very, very important in this, we found that higher region of Himalaya will be having more amount of precipitation. Or I would not say precipitation, rather I would say water budget in that sense, because water budget accumulates precipitation also, and evaporation and basic cycle. However, their temperatures are increasing most of the time, except green color. If you limit your eyes on green color, we find that in RCP 2.6, we have a very less increase on temperatures happening. And in the above slide, you can distinctly see the trend, where you see how the trend is increasing in the RCP 8.5 and RCP 2.6. These are the trends. So trends are positive, means the RCP trends positive shows that it is kind of precipitation is increasing over these regions. So positive trend means precipitation is increasing over these regions, whereas in the lower riparian of the Indus Basin, we find that towards your precipitation trend is negative, blue color. So precipitation trend is decreasing in last 30 years. So most of the precipitation is limited over higher Himalayas, over the higher upper riparian of the Indus Basin, which is in the Indian Himalayan part of the Indian Himalaya. Rest of the basin shows declining precipitation in the future. This is the total precipitation and water minus water budget. This also supports the climatology that higher Himalayan region will have more amount of water availability over these regions. This is the Kupwara, Srinagar, Gulmarg, this basin. We found that over this Srinagar valley, your increasing elevation dependency doesn't work. Primarily, we looked into that why it is not behaving as the general behavior of the Himalaya. Here we find that upper elevation is warming rate is lesser than the lower elevation. So valley floor is warming as compared to the upper elevation. And then we looked into this, we found that because by virtue of its close shape, atmospheric interaction at the large scale flow is not happening. And that is why this is showing very distinctly different kind of micrometeorology over this region. So Srinagar Valley is behaving very, very differently than rest of the Himalayan region. And precipitation trends also are very distinctly different as compared to the entire Himalayan region. Now I'm talking of the basin scale. In case of Satluj, we don't find much change. Temperatures are increasing in the future, and but precipitation has not been changing. This is very peculiar because Satluj river basin falls in a kind of a interactive zone where your winter precipitation as well as the summer precipitation both increase, both arrive there. So that is the reason where the precipitation doesn't show much changes. If you look at the panel B, you will find the red all colors of graph are having a almost similar kind of variability, and precipitation doesn't show much change, though it is warming. If you look at the previous slide, it is warming much before. Ganga River Basin, we have analyzed. In Ganga River Basin also we find that temperatures are changing. However, the precipitation doesn't have much change. Of course, it has the interannual variability. I am not going into the detail of interannual variability or intra-seasonal variability, or even not even in the orographic forcing. However, we find that there is an increase of temperature, and temperature by 2060 changes that RCP 8.5 is much below over this region, and only after 2060 RCP 8.5 becomes more warming. We are analyzing all these data at 1.5, 4, 2 degree and 4 degree simulations, but here I am showing. So briefly concluding talk of this, the temperature are projected to increase, all of us know, and these all analysis, whatever I have presented here, will have a very good usage for the purpose of the future analysis for the researchers, as well as the finding of the changes in the Himalayan region, with, of course, with the uncertainty factors to kept into the mind. Intermodal disagreement has to be needed into mind, and model biases. Of course, you can have a methods of bias correction if anybody wants to use for Himalayan region. So with this, I thank you for giving me this opportunity, Aries, for speaking my mind. And thank you, Dr. Dhumka, for giving me this opportunity. Thank you very much.
Thank you, sir.
Thank you, Professor Demery, for providing a very interesting overview over the Himalayan region as far as temperature and rainfall trends are concerned. So we can have one quick question from audience. Okay, if there are no questions, so we'll move on to the next presentation. Thanks again, once again to Professor Demery. Yes, please.
Yes.
Okay, thank you, sir. Thank you for your presentation. So our next speaker is he is also an invited speaker, Dr. Rakesh Huda, and he is a senior researcher at Climate Research Program at Finnish Meteorological Institute. So he works on aerosols, climatology and meteorology, but his expertise is on aerosol observations and their linkage with climate change and human health. He also works on aerosol cloud interactions as well. So he'll be talking on atmospheric aerosols, pathways and processes, and IGP Central Himalayan Glacier. So I would request Dr. Huda to go ahead with his presentation.
Am I audible now?
Yes,
Rakesh.
And the screen is also visible?
Yeah.
Yes.
Yeah.
Okay. Thank you, Chair, and good afternoon, everyone. For this introduction to the audience, and of course, with my identity now, since in the morning I was on some others' behalf. And thanks to DST, ARIES, and the university, and of course, the organizing committee, and particularly Dr. Dumka and the associated people with him. So in this work, actually, we'll glimpse you with some work which was carried out and what we have learned over past few years from FMI side while working with our potential partners in India on important topics of atmospheric aerosols. And with this title slide, I also would like to just have a introduction about this special issue, which partly we are invited for the guest editorship, and this is in concurrence with the topic which we are dealing in this 3 days international online conference. So, but we'll highlight later in the last slide as a notification. Okay, so I'm working here in FMI for last many years, and we do have this collaboration with Indian partners, and we were having the understanding of IGP and the Central Himalayas also recently went up to the glacier. So in this talk, actually, we'll try to make some linkages between different processes and the pathways. So if we start with this very fundamental illustration or picture, I think mostly the meteorology people who have used it, and even the atmospheric aerosols or science people might have used this conceptualization. And basically here, if we see the boundary layer, which also we can say convective planetary boundary layer, or also during the daytime, if we say it's a planetary boundary layer or simply convective boundary layer, and also known to be an atmospheric boundary layer. So what is this basically? If we start with a little bit with the fundamentals, it's a part of actually in the lower troposphere, which mostly directly affected by the solar heating of the Earth's surface. And it has, if we see in this picture also, it has this very simple 3-layered structure or flat terrain. We are talking about the flat terrain and the homogeneous terrain. If we start here during the noon time, when we see the deepening of this boundary layer, we can see this surface layer and the mixing zone basically, and then entrainment zone over here. So over the day, basically, lots of changes takes place in form of subsidence, and then there is an inversion layer, and of course the next some remnant of the previous day. So it happens during the diurnal period. But if specifically if we talk in terms of daytime, so in the daytime, actually through this illustration, we can see that for flat terrain, it has 2 ways of vertically transporting air pollutants in the atmosphere. So here pollutants are mixed upward by convection through a deepening this CBL during daytime, and while pollutants on the residual layer, we can see over here in the form of entrainment zone. Here the pollutants which are emanent of the previous day CBL, which are entrained downward in the growing CBL. So it is frequently assumed that the constituents within this CBL are well mixed and kept by an inversion. So the inversion actually, this acts as a lead or limit, we can say, for the transport of constituents to the upper atmosphere above this. But in nutshell, if you wanted to say over flat terrain, we are again talking about the flat terrain. So over the flat terrain, when the CBL grows by upward sensible heat flux at the surface basically, and the downward sensible heat flux, or we can say entrainment at the top of the CBL. So what we can say, the convergence of this sensible heat flux that causes CBL to warm and grow in depth. But if we see in, say, for the flat terrain or the homogeneous terrain, over here, if we see that the boundary layer or the atmospheric thermal and dynamic factors which controls could be air temperature or wind speed specifically, that drives this atmospheric boundary layer. And eventually that atmospheric boundary layer that controls a kind of feedback between atmospheric aerosol loading and the ABL height. As we have seen, there was a discussion in the morning, and through this simplified illustration, if you see on the left side figure, different feedback mechanisms are shown with different components. And as we have seen in the morning, basically there was discussion about the fog, of course, but there can be a similar environment in the IGP where we can see such kind of feedback mechanism, but we haven't yet understood it properly for this environment. And in this, if we see there is a enhancement of emissions, of course the pollutant concentration enhancement takes place. There is a decrease in the turbulent mixing, and then of course the boundary layer height is decreasing, and that leads to again there is a elevation in the pollutant concentration. And it has been seen that more ambient aerosols accumulate, the less solar radiation reaches to the surface, which results in a kind of disadvantageous effect on surface air temperature, as well as a positive impact on ambient relative humidity, we can say. And these phenomena that restricts the development of atmospheric boundary layer. So this and eventually this low ABL height in turns actually forces the accumulation of aerosol particles in the high relative humidity and shallow atmosphere. So this can also be a case, should be recognized or to be recognized in the IGP region, mainly during the post-monsoon season and maybe in the winter season, of course. So in order to do that, we need to have a temporal variability and the vertical distribution of aerosol concentrations at different altitudes, which could have enlightened us also that the changes in the aerosol properties at planes within the ABL and get transported of aerosol to the mountains as a function of ABL growth. So we need to have studies similar to that, where we can intuitively incorporate different processes and phenomena which are driving such kind of air masses movement and which are taking place in the IGP region. And in addition to these real-time source apportionment study, we need to incorporate such kind of interplay between meteorology and boundary layer dynamics and of course aerosols. And this was actually very much illustrated for the reason in China in 2016 by one of our colleagues. And if we see on the right side in form of say source apportionment, which was integrated with these ABL dynamics, and this in this conceptual scheme, it has been seen that this amplified transboundary transport of haze pollution by this interaction between aerosol and PBL. So if you see in this pie chart, it in two ways, basically from say this region, there is a convection and advection of absorption aerosols or secondary particulate matter and some precursors from this region in form of say BC secondary PM extra goes to this region. And of course, in addition to these, there could be precursors of this secondary PM in form of different gases basically. And when from this reason there is a transport of air masses to this region, and here there is an enhancement basically due to local accumulation and secondary production of different organic or inorganic fraction takes place due to this aerosol and PBL interaction. And why it is happening, again the same feedback mechanism works over here. If we see there is a decrease in the temperature and increase in the stability, and of course elevation in the relative humidity, and that gives enough environment for the secondary formation of aerosols. And this sort of environment then leads back to the original one, and there is a fast advection could happen due to cold fronts, and these aged aerosols basically, or the plumes basically moves back to the, so it's a cycling or the closure phenomenon basically, which could happen, or intuitively it has to be in the Indo-Gangetic plane. So we need to design some studies where we can have such kind of phenomenon understanding. So if you come to some results basically which we have been opportunity to work simultaneously in the IGP as well as in the foothills of Himalayas. So here these were the first observations basically to understand the individual BC particles in India using SP2. So this was published in 2017. And if we see on the left side figure, basically it shows this RBC number fraction is somewhat larger in Gwalpari, though to illustrate a comparative way, this Mukteshwar concentrations are increased by a factor of 10 to show a kind of size distribution properly in model form. So over here, we can see clearly that RBC number fraction, which is higher in Gwalpari than in the Mukteshwar. Mukteshwar was in the foothills of Himalayas near to Nainital, and it was considered to be a kind of regional background location. But see, this RBC containing particles seem to have similar RBC core diameters. From this work we came to know, and we also understood that it could have been expected this RBC core size should decrease when secondary aerosol species such as say organics and sulfates get condensed on these existing particles during their transport to Mukteshwar, but it was not effectively seen in our work. But interestingly, it has been seen that there is instead of a unimodal, there is a bimodal distribution of this RBC core size. And so in conclusion, we can see that these observed RBC properties could be common for this whole region, maybe due to similar emission sources, or we do have say relatively short time for aging process, which could be more likely hours than days. And interestingly, if we see on the right side, we also have seen that when we have this RBC to total fraction, we see that 30 to 50% of accumulation mode particles are containing these observable amounts of refractory black carbon. And it was a kind of alarming situation for us also to when we compare with other high altitude stations where we do have this individual BC particle analysis, and it was observed that the number fraction of particles containing RBC at this location was highest reported so far. So what are the phenomenon basically again come to the same point. Here there is a daytime increasing mixing layer height, and at Gwalpari there is a diurnal decrease if we see over here in RBC mass and number fraction, and in Mukteshwar it is seen from this simultaneous observations that there is a air mass flow from low-lying areas in IGP and reaching up to this high altitude Mukteshwar station. So talking about this foothills Himalayas station Mukteshwar, we see this aerosol variability factors which rise over here, and how this temporally or seasonally it is changing. And we did have a series of publications starting since 2009 and up to this time. You can see some of the highlighted, we can say, quotes over here. And so based upon such sort of understanding, we came to some conclusion that though it is quite obvious, but in form of, say, total number concentration or PM 2.5 very fundamental parameters, we see that in the pre-monsoon, there could have been this some anthropogenic activities which leads to have such high elevation of these number and the mass concentration, and of course which are coupled with some dust storms event. And since the temperature is quite high, so and biogenic formation also takes place, so there is a peak of NPF and accumulation of the particles also takes place during this period at this site. And during say post-monsoon, we can clearly indicate that it could have been due to some anthropogenic activities which are relevant or attributed to crop residue or biofuel burning. And in the winter season, we see that there is no specific regional emission sources we can see, but local and secondary aerosol formation takes place. And we found that the station partly in the boundary layer, not full time, but say 20% of the time it was. And in the middle, we have seen that say June and up to September, these are the months where we have a transition time, have a mixed characteristics of a dry and wet season, and in between July and August, where there is the deepest one in both the mass and the number concentration. So it leads to a kind of wet deposition phenomenon we can see. So again, coming to the irrespective of, say, flat or homogeneous terrain, if you wanted to understand the different processes and phenomenon which takes place in the mountainous environment, if we see over here that the atmospheric, we can say, so over here we do believe that the exchange of heat, momentum, and the mass in the atmosphere over this mountainous environment is controlled basically by different synoptic scale dynamics or thermally driven mesoscale circulations, and of course the turbulence which within the valley basically which takes place. So it is well known that the mountainous terrain exerts an important influence on Earth atmosphere, and that affects also atmospheric transport and mixing at a wide range of temporal and we can say spatial scale. So you know that it is recognized that also that the spatial temporal structure of this daytime convective layer is strongly modified and more complex in the hilly and the mountain terrain compared to, say, flat terrain. As we have seen earlier also in that illustration, that CBL or flat terrain is mostly dominated by the turbulent convection, while on the mountainous terrain, this advection basically from multi-scale thermally driven flow plays important role for the CBL evolution, we can say. So, but the detailed observation of this CBL structure and understanding of the underlying processes are still limited, though there were some piece of work. Of course, one was for the Himalayan region from the chair, Dr. Narendra also was attempted, but we need to have some way forward to make some additions to such kind of studies using some high-end instrumentation, and of course clubbing with the other processes also. And you know, some recent studies, of course, it shows that there is a long-range transport of air pollutants and trace gases that triggered basically this understanding of terrain-induced exchange processes between CBL and the overlying atmosphere. So these studies, in one hand, they helped to give some insight into the CBL structure over the complex mountain terrain, but also it gives a kind of indication that still we don't have a universal definition of CBL, basically, which we can apply for most of the mountainous environment. So in this conceptualization image, basically, we can see this this AL height, which can be considered as the maximum vertical extent of aerosol transport, while this dashed line or over here, it's a CBL height. We can define it's a base of capping inversion that limits the depth of penetrative convection. And we can see this generally AL and this CBL heights are approximately equal over flat terrain, but in mountainous terrain, basically, we can say this exerts a profound influence on aerosol distribution in the atmosphere, and the mixing and transport processes are often enhanced compared to those at the flat or horizontal homogeneous terrain. And this equality between this CBL and then AL height, it breaks down basically in the mountainous environment. So we can see these CBL heights are considerably lower than AL heights, which shows more spatial variability, varying from mountain to mountain, and tend to follow the terrain more than AL height, if we see. But although the extent to which the CBL height follows the terrain decreases during the day. So over here, if we see this mountain venting, it's a process basically which leads aerosols and humidity to be transported above this CBL layer. And there is this MCV, another thing, basically another very including parameter.
How many slides you are having left?
4, 5 more.
Can you please try to summarize?
Yeah, so here we have this depends upon the slope also of the mountain, and of course the time of the day as well. And in this, it's a kind of illustration of the same thing, how the different processes are taking place, and this aerosol layer, how it lifts up to, and it's believed that after such kind of this recirculation processes and with this convection, it is believed to be that this aerosol layer reaches up to the high Himalayas. And in a simplified way, it was introduced in form of this topo index, basically, where it was index was created based upon some criteria and a different set of parameters, and it was illustrated that the mountains where we have the observation at such kind of height at the top, it is less influenced by ABL, whereas the stations which are at such kind of slope are highly influenced. So for this location, actually, we also for Mukteshwar, we try to how the air masses are flowing, basically, irrespective of using boundary layer. We try to introduce some proxy parameters, and the water vapors is one of them. We find out when we were working for IGP and the mountainous environment. And here we see generally this blue line, it's for Gwalpari, and this orange one is for Mukteshwar. And we see in the background values such kind of water vapor quantity, and which should be believed during the afternoon hours also, but it's not happening in that way. And the difference we calculated, it can be worked as a proxy for air masses. And when we see such kind of water vapor variability, it is in line with the aerosol observations. So when we see this variability relationship with IGP and foothills of Himalayas, it has been seen that over here, irrespective of the distance, we found that the ratio of Mukteshwar to Gwalpari, it's having a very high correlation. And the same thing when we try to see how this PBL versus water vapor can work. So it's always not good to have this NCEP or GDES boundary layer data for our understanding. Using this water vapor, we found that the station was not all the time in the boundary layer. So that can be a misinterpretation if we always use this MMD. And while we try to work in this work, we found that how the aerosol concentrations can be reproduced by these different model predictions. And we use this REMO and ACAM, but due to different phenomenon or the processes where this coarse resolution and not keeping in, as the previous speaker also just mentioned, most of these things, that what could be the subgrid phenomenon which should be incorporated to align these concentrations and of course the simulations. And going up further, as we discussed in the morning also, we did have this glacier activities also started in 2014 and still going on. So we were having this big kind of studies, and of course this is under the preparation. We found there is a decrease of black carbon, but still the black carbon is reaching up to the high up to the glacier. And there were some other studies also which even claim that this air masses can transport over the Himalayas basically. And but we need to understand different air masses transport and processes. So there is a need of measurement at vertical profile and also at the horizontal level. If you see in this figure where we touched upon IGP, Himalayas, and then Himalayan glacier, we see the outflows which are so far emphasized from west to east, but we need to see outflows of this ICP air masses laden with different pollutant concentrations can go up to the higher to the Himalayas. And in this work on the right side, based upon this AOD and the kind of mass closure, they identified that there is a outflow of this IGP aerosols up to the Bangladesh and also to the Maldives. So such kind of studies, if we do plan that can give a kind of insight how the air masses outflows from IGP and going to the foothills of Himalayas and reaching up to the glaciers. And in this, just emphasizing this, that over here, still we are lacking long-term observations in the foothills of Himalayas.
You have already more than 5 minutes extra.
Okay, so I can skip. So in the outlook, basically, if we see different sources in the IGP, we do understand the emissions, but in the Himalayas, what are the exchange processes are taking place? And of course, we need to study some local boundary layer dynamics, and of course, the deposition at the glacier. So there is a need of multiple measurement sites along with the modeling activities and incorporating some isotope studies. So as we know, there is implications to the glacier, and based upon this EC mode report, it has been seen that the third pole could melt by 2100 years. And then of course, if we limit this up to the 1.5 degree also, then still there is a chances of 1/3 of the glacier would melt. And not forget to acknowledgement for the funding agency and our co-partners, and of course, again, notify this special issue where people are interested to contribute. So with this, I end my talk for the day.
Okay, thank you, Rakesh. I think we are not left with the time for the questions. So thank you for your presentation. So we will have a tea break now.
Rakesh?
Yes.
Are you able to listen?
Yes, please.
Yeah. So we will break for tea.
Narendra, can I quickly ask a question? Is because of
okay, please, please go ahead.
It's a tea break, no?
Yeah.
Is it permitted? Can I?
Yes,
sir. Please, you can ask one question. Rakesh, please.
Yes, please.
Yeah, Dr. Huda, it's a very interesting aspect you have shown. I very oftenly ask the aerosol researcher as far as the Himalayan is concerned. Particularly, most of the discourse remains in IGP and most of the discussion remains during the burning time, which is October and November. But particularly when it goes to climb up the Himalayas, like most probably I think what model you are showing, it is the Europe Himalayas, Europe mountains you are showing, right?
It was Indian Himalayas basically. We consider this Ramoham and Akham basically, and
Remo is at 44 degree maximum. It has gone. Akham is 2.5 degree. I think my question is specifically is of interest actually. Working on the Himalayan and the regional climatology of Western, Central, and Eastern Himalaya is mostly driven by Indian summer monsoon and Western disturbance. So and Garmukteswar is roughly I think 2,000 meter elevation.
Yeah, so, it's about 2,100.
Something. Yeah. So how in the higher Himalaya when you go 4,000 meter elevation in particular, because there is not much turbulent kinetic energy available for the system to rise in general, because the elevation is already minus 10 or minus 20 in winter and 10 in summer. So my question most probably is how the higher load of aerosol will be existing there, because my interest is working on the glacier in Upper Indus Basin to see that how the melt is happening, or like you reported, did a reporting of that HIMAP, I was part of it, how this melting will sustain. So that is my question. And how can we think of?
Yeah, that's what, in fact, we were not yet, we tried to make a linkage between these foothills of Himalayas measurements and linking with the glacier deposition. So we are in the process, we are at the same page basically, that which sort of model we need to use, and whether, because this even the numerical simulations, that those also sometimes get fails basically. So what sort of thing, I think it's a very open question, and we could discuss it, because we have already some measurements and the modeling activities which we can make a kind of coupling with the regional climate modeling, and of course if we have, in addition to RCP, if we have some other emission inventories, local emission inventarization at the high resolution. So in that way, I propose basically to have a more discussion, but we haven't yet attempted the modeling activity for the glacier.
Thank you, Rakesh, for your nice presentations and answer to many questions by Professor Dimri. So we will break for 5 minutes, and then we'll be back at sharply at 3:50, and then we start the remaining presentations. So just a quick break of 5 minutes. ठंडा हो रहा है, आवाज आ रही है। Hello everybody, welcome back to this session. I would like to inform that we are left with 3 presentations from the previous session, before lunch session. So first we will complete all those 3 presentations, and then we'll follow the schedule as listed. So we will be having total 10 talks in this session. So I would request everyone to please stick with the time, and I would like to request Mr. Sudeep Kumar Kundu from National Institute of Advanced Studies, ISC Campus Bengaluru. So he'll be talking about assessment of climate model simulated rainfall pattern based on satellite derived estimates over the Indian region. So please go ahead with your presentation, Sudeep.
Yeah. Yeah. Am I audible to everyone? Hello.
Yes.
Yeah.
Yes, you are audible. Go ahead with your presentation.
Okay. Okay. Thanks a lot. Thanks a lot for providing me to present my topic. Today I am going to assess the climate model simulation, especially CMIP model based on the satellite derived estimates over the Indian region. I am a former MTech student from Indian Institute of Remote Sensing, Dehradun, ISRO. This is the outline of my today's presentation. It will start with the introduction. Then I will go to the study region. Then I will talk about the data sets and methodology what I have used, and I will talk about the result and discussion. And later I will do the conclusion of my work. So as you all know that monsoon season rainfall, which is occurred in the southwest monsoon, is the maximum share of rainfall which is about 18% of the total rainfall. It greatly affects the Indian economy because this Indian economy is heavily dependent on the agriculture, and agriculture is heavily dependent still now in the southwest monsoon. So, but according to the assessment report 5 of Indian of the International Panel of Climate Change, Intergovernmental Panel of Climate Change, that there is a possibility of changing climate, especially for this, the rainfall pattern will also be affected. And to measure the rainfall variability in the future under different forcing scenarios like RCP 4.5, RCP 8.5, it is very important to use the climate model. So in this context, I am using this, I am assessing this climate model, the CMIP model, some base defined CMIP model to estimate the rainfall pattern, which is based on the satellite rainfall product. So this is the study region. I have choose the study region for the Indian region and for the spatial map. And I choose the Kerala region for the time series analysis. As you know, Kerala region first southwest monsoon effect hit the Kerala region. So that is why this is the map, rainfall map for the IMD data that I have plotted here. So the data sets I have used climate model data. Earlier I have mentioned that I have used the CMIP data. This is the global climate model. I have used 5 GCMs that is best defined for the Indian summer monsoon. And I use the satellite derived product called TRMM. It's called Tropical Rainfall Measurement Mission 3B43 version 7, which is the monthly dataset. And for the daily dataset, I have used 3B42 version 7. I have compared these 2 datasets with the CMIP models, and to understand that whether CMIP model can able to simulate this rainfall pattern over the Indian region or not. so this is the methodology of my current study. In the left-hand side, as you were seeing that the CMIP model, 5 CMIP model I have used. I used for the 2006 to 2018 for both the RCP 4.5 and RCP 8.5. I produced the contour map as well as the time series map. In the same way, I have extracted the data for both TRMM 3B42 version 7, TRMM 42, TRMM 3B43 version 7, and I have extracted the time series plot as well as contour plot, and I have compared with this CMIP model. So in this part, the result and discussions. So in this part, I have shown the spatial plot for the mean June, July, August rainfall for the during 2006 to 2018. Here in the left side, as you are watching that, this is the TRMM 3B43 version 7 data. And the middle one is the CMIP data. This is the RCP 4.5, and the right-hand side, most right-hand side, is the RCP 8.5. I have shown the 5 model in the left side and the upper right side of upper 2 column, and the last one in the right-hand side, in the lower middle in the right-hand side, it is the multi-model mean. I have calculated the mean of these 5 models and produced this result. As per the image, if you compare this with the TRMM data, that you can find that the Kerala region is the highest rainfall occurred in the Kerala region. And if you see the Himalayan region, especially the northwest Himalayan region, this model data for both cases in RCP 4.5 as well as RCP 8.5, it is unable to capture as per the satellite data during this 2006 to 2018. And if you see this IPSL CMA 5A LR and the GFDL CM3, these two CMIP model, these two global climate model, which is participated in CMIP domain, unable to capture the rainfall pattern properly. It shows underestimate the rainfall pattern for both cases, RCP 4.5 and RCP 8.5. And this is the rainfall I have taken from the 2010. This is the particular 1 year I have taken. And the previous one was the mean rainfall from 2006 to 2018 for the JJA month. And for in case of 2010, for this analysis, you will find the more or less same result, that the Kerala region for both model as well as the the TRMM data both capture high rainfall. But in case of northwest Himalayan region, there the model unable to capture the rainfall pattern properly, whether the satellite data can. So here is also the multi-model mean also shows the same result, that it is unable to capture rainfall pattern over this northwest Himalayan region properly. And this I have taken the time series for the JJS rainfall during 2006 to 2018. I have used this 3B40 version 7 data. And this is for the Kerala region. Earlier I have mentioned that I produced the time series for only the Kerala region. Here you can find that the upper one is the TRMM data, that the rainfall pattern for daily mean rainfall for each monsoon months called June, July, August, and September. This is ranging between 5 to 10 millimeter per day. But in case of CMIP model, in the left-hand side, lower left-hand side is RCP 4.5 and right-hand side, lower right-hand side is RCP 8.5. Both you can find that the rainfall is under 5 millimeter per day in case of RCP 4.5 particularly. But RCP 8.5, there is some a little bit greater than the 4.5, but it is still lesser than the satellite derived estimates. So from here it can be said that the satellite data can capture the rainfall properly rather than the CMIP model. Because CMIP model underestimate the daily pattern of rainfall. Here I do the analysis for the Kerala region again for the time series over this 2010. Here you can I have shown the JJS rainfall from 1st June to 30th September. Here you can find the lower one. It is the satellite data rainfall. Here you can find that the rainfall is varying from 5 millimeter to 30 millimeter like this. But if you found this semi-pipe data, whether it is RCP 8.5 or RCP 4.5, both underestimate the rainfall pattern, which is under 20 only. So, and one more thing that this time series plot for the model data I have produced using the multi-model mean of 5 GCMs. So this is the conclusion part that semi-pipe multi-model mean that are able to simulate the mean monsoon season rainfall pattern during 2006 to 2018. It is somehow able to do that, but in case of daily rainfall intensity, that semi-pipe multi-model mean unable to capture the rainfall pattern properly. It underestimates the daily rainfall pattern. So it can be said from the analysis that the rainfall pattern, particularly for the over the northwest Himalayan region, it is quite uncertain and quite unreliable to assess the rainfall pattern for the force under the forcing scenarios in near future. That I have studied from this analysis with the satellite data. As you know, RCM 4.5 and RCN 8.5, that data can available from 2006 only. So from 2006 to 2018, I have taken this data to compare the satellite data with the semi-pipe model. How the semi-pipe model for the forcing scenarios under RCP 4.5 and RCP 8.5 is going to know this analysis. And thanks. And this is my present address. Thanks.
Thank you for your presentation. So if there are questions, those can be posted on the chat box, and he can answer directly to the audience. So we will move to the next presentation. Next presentation is by Nidhi Kumar from JB Pant Institute, Kosi Katarmal, Almora. So she will be talking about identification and assessment of vulnerable indicators, a case study of Northwestern Himalaya. Please go ahead with your presentation and try to keep it in time.
Hello.
Yes, Nidhi, are we audible?
Am I audible?
Yes, yes. Please go ahead with your presentation.
So the screen is visible.
Yeah.
So shall I start?
Slide mode.
Okay.
Nidhi, enlarge your presentation.
So shall I start?
Yes.
Okay. Good evening to all, respected chair and co-chair. Myself, Nidhi Kanwar, I am working as a researcher at GB Pant National Institute of Himalayan Environment, Kosi Katarmal. And my presentation is on identification and assessment of vulnerable indicators that are affecting the forest of the Kinnaur district of Himachal Pradesh, which lies in the northwest Himalaya. So this is the study area. The Kinnaur district is situated in Himachal Pradesh, ranging at an elevation between 1225 to 6800 meter, and is known as a Kinnaur Kailash, and which is very much close to the Tibetan border. And most of the Kinnaur enjoys the temperate climate due to high elevation, and much of the portion of the Kinnaur is situated high in the Himalayas, where vegetation is very sparse, and the population of the Kinnaur is 84,000 according to 2011 census, and the area is very well known for Pinus jetiana, which is locally known as Chilgoza. So during the field visit, we saw that the study region forest was affected and getting degraded. So to found its causes, we did this study through a medium of participatory approach, and the study employed a combination of data collection methods like a participatory approach, group discussion, interviews with the communities, and we also did a survey of 10 villages from low altitude to high altitude villages using stratified random sampling, and we also did a prioritized matrix survey for identifying vulnerable indicators for knowing the forest vulnerability, and furthermore highly vulnerable indicators identified by the stakeholders were validated with field observation and secondary data sources. And not only this, we have also used the application of remote sensing and GIS for assessing the vulnerable indicators like landslide, soil erosion, forest fires, anthropogenic activities, and climatic variance. So this is the data set that we have used for the study. And now the results. So based on prior knowledge of the people of study area and of us, these climatic parameters, hazard, anthropogenic indicators were identified as a vulnerable indicators on the basis of ranking. And the climatic parameters include the precipitation and temperature. So during the survey, respondents told that the snowfall has reduced with a gap of few years, and has temperature and precipitation has increased in the areas which has become the major cause of forest degradation. So based on so we downloaded the data from CFSR website, and so based on data, we analyzed that it was made clear that the maximum temperature is showing the increasing trend of 0.05 degrees Celsius per year, whereas minimum temperature is also showing increasing trend of 0.07 degrees Celsius. Whereas in case of precipitation, this is also showing a increased trend of 0.01 millimeter per year, because the nominal change in precipitation pattern have high impact on environment and society due to the weak geology, fragility, and topographical condition of the areas. Next, the fact indicator that is influencing the vulnerability is are the hazards. So the occurrence of landslide is a very common feature in the study area due to fragile structural fabric of geological strata. And the native of the area believed that losses to forest were mainly due to landslide and erosion. So based on visual interpretation of the satellite data, it was found that the area that the forest area, about 2.09 square kilometer forest area, severely affected by the landslide, and about in total 13.13 square kilometer area is affected among the non-forest cover area. And in terms of soil erosion, 20.26 square kilometer area from 2005 to 2015 got forest area got degraded due to soil erosion and erosion because of the fragility and aridity topography and changing precipitation pattern and the ongoing development activities in the study region. And these are some of the prominent flash floods that have occurred in the study region, and the study area witnessed most of the disastrous floods in 1993, in 1995, 1997, 2000, 2005, 2007, and 2013. So based on GIS analysis, the out of total area, that is 6,401 square kilometer, 10% area of the forest found under flood risk. So this is this slide is showing the photographs of the flood incidences that took place in the region. As you can see, this is the before occurrence of flash flood, and this is the after the flash flood occurred in 2005, and this red encircled is showing that this much this area is cut down by the river during the flash flood in 2005. So next indicators that are influencing vulnerability is again hazards, and this is This slide is showing the mapping of identified hazards like landslides. First map is showing the landslide. The maximum landslides were found along the sides of river valley. Then the second map is showing the erosion that has taken place in the study region during the period of 2005 to 2015. Then this is the flood vulnerability map of the region, and these are some of the earthquakes that have occurred, incidences that have occurred in the study region. As per the record, the division has been hit by 28 times by earthquake having a magnitude of 4.0 and has affected the forest most. Next slide.
You are left with 2 more minutes.
So the next indicators is the anthropogenic pressure, in which land use land cover ranked highest. So the data registered in the table reveals both positive and negative changes occurred in LULC. During the 2005 to 2015, the forest has decreased to 0.005%. On the other hand, non-forest category has increased to 0.007%. Next factor in the anthropogenic pressure comes the forest fires, and the forest have very susceptibility, high degree of susceptibility to forest fires, and have degraded the forest wealth. And total 174 forest fire cases have been registered since 2011 to 2001 to 2020, and most of the maximum forest fires occurred in 2014 and 2016. These are the HEPs that are located in the region. Around 30 projects of different phases are located in the study area, and which are also degrading the forest. This is, as you can see, this is the during the construction of Thidong project, a large number of trees felled and damaged at dam sites at Lambar village, and most of the trees were of Deodar chilgoza, which were damaged. So while other indicators like encroachment, timber stealing incidences are not much creating much problem in the area, as per the data obtained from Forest Department, only 264 cases of encroachment were recorded. So after overlay analysis of all the indicators, it was found that that all the indicators are affecting are highly responsible for forest loss in the study area, and yellow encircled in the figure showed maximum losses. Uh, Thank you. These are the key findings. And I would like to acknowledge Director of the GB Pant Institute and my supervisor, Dr. J.C. Kunyal, and co-supervisor, Dr. J.C. Pandey, and DST Funding Agency, and also thanks to the ARIES and HNV Gavar for providing the opportunity to share this research at this time. Thank you.
Thanks, Nidhi, for your talk. We may have one quick question. If there are no more questions, please. Thank you once again.
Thank you, sir.
And now we'll move to the other presentation by Prajwal Rawat. So he'll be talking on variabilities in ozone over the Himalayan atmosphere, role of precursors, metallurgy and dynamics.
कौन सा भाई ये
अच्छा वीडियो भी बंद नहीं कर सकते
कंट्रोल F5
उसको तो रोक ले
कंट्रोल F5
वो रहने साइड में उसे कुछ नहीं होता उसको खाली वहीं से म्यूट कर दो वीडियो ऑडियो रहेगा
क्या हो रहा है भाई? क्या क्या है?
बंद करो से
स्लाइड शो में तुम्हारे क्यों आ रहा है?
वहाँ पे तो नीचे से कॉपी लिखा है
नहीं है ना।
क्या ये पीडीएफ है?
नहीं
कौन सा मोड वगैरह करनी है?
व्यू से कर दीजिए। व्यू में ना व्यू एंड सबसे एंड वाला
वो आगे भी नहीं आ रहा है।
स्लाइड नहीं उसमें नहीं है। वीडियो
Good evening all. Myself Prajal Rawat, and today I'll be talking on variability in ozone over the Himalayan atmosphere, role of precursor, meteorology and dynamics. Firstly, I will talk what is atmospheric ozone. As we know that among the various stress gases, atmospheric ozone is having very unique vertical distribution, which is mainly explored in two contexts. Stratospheric ozone, generally natural production and protect living beings from the harmful UV radiations. And tropospheric ozone, generally man-made production and harmful for living beings. In my talk ahead, I will talk the effect of regional emission and long-range transport on the ozone profiles. Then additional phenomena over subtropical Himalayan region, the stratosphere to tropospheric transport will be discussed. Then I will discuss the importance of the Indian geostationary satellite INSET 3D for the higher spatio-temporal ozone data over Indian region. And then I will conclude my talk. So here at Nainital, we are launching the balloon from Nainital. So you can see that for most of the month, we have westerly winds. So the balloon trajectory are going toward the Nepal region. Wherever in case of summer monsoon, there is a shift of wind, which is easterly winds, we can see that. And there is associated ozone with the east trajectory. And here I am showing the yearly average ozone profile up to 30 kilometer and in the troposphere up to 18 kilometer. So you can see that even in the yearly average during winter and spring, there is variability in ozone profile in the upper troposphere. And near surface, maximum ozone is found during spring, which is more than 60 ppb. So in the first plot, I am showing the monthly variation of tropospheric ozone column and the UTLS ozone column. So you can see that the tropospheric ozone column is higher during biomass burning period. And if you see the fire count over northern Indian region, the fire count also high for the same period. Whereas in case of Asian summer monsoon, we have seen a drop in the tropospheric ozone column, which is mainly being caused by the washout of ozone precursor and arrival of clean oceanic airs to this region. And in the UTLS, if you see the monthly variation, we can see higher ozone in the UTLS during winter and spring, which is showing the influence of downward transport of stratospheric ozone to the UTLS region. We have also encountered some high ozone event during the summer monsoon period. And when we have studied them using the FlexPart retroflume and trajectory analysis, what we have found that the long-range transport of upper tropospheric air is causing this kind of high ozone event during this during the summer monsoon period. And if you see the trajectory height, so you can see that the air from 10 to 12 kilometers is reaching up to 6 kilometers at our region. So here I'm showing the stratosphere to tropospheric transport, which is a very unique phenomenon over the subtropical Himalayan region. So if you see the tropopause variation, monthly variation over our region, you can see the tropopause is coming up to 350 hectopascal lower in the winter and spring. And these kind of frequent tropopause folding leading to 40 to 75% more event of high ozone between 14 to 16 kilometers over the central Himalayas. So in the right here, I'm showing the average monthly tropospheric ozone profile as well as the events which is having higher ozone. So you can see that for winter and spring, the frequency of higher ozone event is very large than the rest of the month. And here I'm showing the background ozone for different altitude and the event. So if you see for the winter and spring, the event are higher as well as with the height, the event are increasing. And one more thing we can see here that up to 10 kilometers, there is a seasonality of higher ozone during biomass burning period. Whereas in case of upper troposphere, the higher ozone is mainly during spring and winter, which is showing the effect of downward transport over our region. So apart from the ozone sondage, we are also utilizing the INSAT 3D sounder ozone product. The INSAT 3D sounder is the first Indian meteorological payload onboard geostationary INSAT series, providing hourly temperature, water vapor, ozone profile over Indian region. And we have studied the ozone profile as well as the ozone column and the different product of this satellite. So we found that the INSAT 3D retired ozone profile captured ozone gradient and ozone peak altitude very successfully despite only one IR channel for ozone. Larger ozone biases were observed for INSAT 3D in the lower troposphere and near tropopause. We are also improving these ozone product based on the INSAT 3D observation, and we are using the machine learning and the deep learning method as well as the traditional physical optimal estimation method to further improve these ozone product from the INSAT 3D. And we hope that we could provide a better ozone profile over Indian region using this satellite observation. So here are my summary and my conclusion. Influence of biomass burning and downward transport on ozone profile are observed. The frequent tropopause folding during winter and spring leading to 40 to 75% more event of higher ozone. The long range transport of upper tropospheric air and the local surface emission contributing toward higher ozone episodes during summer monsoon period. Ozone peak altitude and ozone gradient captured well by INSAT 3D, showing the capability of good retrieval algorithm. So thank you and happy World Day in advance.
Ozone Day.
Ozone Day, yes. Sorry.
Okay. We
So
can
if you have any question, you can.
We can have a quick question if somebody has a question. So thank you, Prajal, for keeping in time. So we will move to the next presentation. And now we start actually the post lunch session presentations. And the first presentation is by Devanshu Banerjee from IIRS Dehradun. We will be talking about the investigation of changes in annual precipitation cycle of Jammu and Kashmir, Union Territory of North to Western Himalayan region.
So am I audible, sir?
Yeah, yes. Please go ahead with your presentation.
Okay, sir.
And try to keep in time.
So first of all, good evening, everyone. The research is named as the investigation of the change in annual precipitation cycle of Jammu and Kashmir Union Territory, which is a newly formed union territory by the Indian government and of the Northwestern Himalayan region. So this is from the Marine Atmospheric Science Department of Indian Institute of Remote Sensing. So as an introduction, we can have a brief introduction of the Northwestern Himalayan region, which has a unique geophysical significance. And the precipitation pattern is mostly controlled by the Indian summer monsoon and the western disturbances in the respective periods of DJF and JJAS. That means the monsoon period and the winter period. And there are different types of precipitation actually, like snowfall, rainfall, solid state, liquid state, and that is based on the orography as well as the atmospheric circulations of the area. So the following study will focus over the precipitation characteristics and the change of annual cycle of precipitation in the last 40 years over the Jammu Kashmir Union Territory. And this is the study area. So this is the Northwestern Himalayan region as a whole, and we are targeting the only this Kashmir province area, which is a newly formed. And so what is the objective of the study? First is the climatology of the precipitation for the spatial distribution pattern and variability. Secondly, the investigation of the annual cycle of precipitation as a decadal analysis. Thirdly, to understand the seasonal trend of the precipitation, how is it going? And fourthly, the vertical profile of the hydrometric concentration and the humidity levels in a decadal level. So the datasets I have used here is the newly 5th generation datasets of the ERA interim, that is the ERA 5, which is released by the European Center of Median Weather Forecasting. And I have used the two basically types of datasets. That is one of the pressure level datasets, and one is the single level datasets that is on the surface level. And so this is the methodology that have been followed using the single level data. We have computed the different precipitation cycle parameters like precipitation distribution, decadal annual cycle, investigation of the annual cycles and computation. And finally, the pressure level data has been used for the hydrometric concentration and humidity level investigations to understand it. So why I have used the ERA interim data? Because a lot of research has been shown that ERA outperforms the other reanalysis dataset in case of the Northwestern Himalayan region as well as the whole Indian region. You can see the papers here as well as the my figure, which is quite equivalent with the literature reviews as well. So that's why ERA 5 is in a coarse resolution quite efficient dataset. So further to the results and discussion, let's come to the climatology of the northwestern Himalayan region now. So this is the December, January, and February precipitations. This is March, April, and May, June, July, August, and September, where you can clearly indicate the penetration of the monsoon winds in the NWH, and the October and November season, where you can see the initiation of the western disturbances is coming from it. And this is the standard deviation. So you can see that the variation of the standard deviation is high. So this is basically a monthly average daily data sets. And the red spot you are seeing at the location where the Srinagar and the Jammu Valley is present. And this is an area where the urban microclimatic parameters or the urban microphysical parameters takes place. So as a decadal analysis, let's come to the DJF. This is the mean of the December, January, February. So you can clearly see that from 1979 to 89 and 2009 to 19, there is a gradual decrease in the precipitation trend over the northwestern Himalayan region. And also in the Jammu and Kashmir Union Territory, specifically you can see the red spot is getting vanished. So, and this is the March, April, May. You can also see a decreasing trend here. Why it is happening, we'll come into the later part. And this is the standard deviation, that where the variation of the rainfall is getting higher and where it is lower. So you can see that standard deviation of the March, April, May is continuously getting lower and lower. So, and this is the most important season, the JJAS, the monsoon season. And you can see the intensity of the rainfall is getting much higher, and the rainfall is also higher in the Uttarakhand area as well as. But Jammu Kashmir Union Territory, you can see that slight increase is there, but that is not that much of significant. So this is also the standard deviation map, but the deviation is getting higher. And you also can see that the Uttarakhand is having more standard deviation than any other states of the NWH. And Jammu Kashmir, it's quite higher, but not that much. So these are the observations that I've already discussed during the present. The second part, we are going through the analysis of the annual cycle of precipitation as well as the atmospheric profiles. So you can see this is a rainfall profile that has been derived from the ERA 5 data. From 1979 to 89, you can see, and the maximum you can see the 1989 to 99, which had almost 3 flood years, and from the IMD data sets. And the most significant change you can see for the snowfall, that the trend which was in the first 2 decades, that means 1979 to 99, but the peak was in the March season, the peak has been gently shifted towards the February season of the snowfall. Similarly, the total column rainwater is getting higher in the JJA season always. But one significant change, you can see that some of the total column snow water, apart from the snowfall in the January and February, you can see, but this is the area where it is getting higher total column snow water, but the snowfall is comparatively less. That is because the total column snow water is generally converting it into the liquid water in the higher atmosphere. It is not getting the ground level set. And this is the decadal distribution of the seasonal concentration of hydrometeors. So this is the cloud ice water content. You can see the 600 hectopascal, that is the maximum area. At maximum amount of cloud hydrometers is present during the DJF season, and from the onwards it is moving towards upwards. So it is basically the cirrus clouds positions, and you can see the cloud ice water is getting higher and higher. So, and similarly you can see the cumulus cloud positions. That means the December, January, February, the cloud liquid water is very, very low. Maximum you can see in the June, July, August, and September. But one thing, 700 to 1000 hectopascal, it's almost doing a similar. That means the cloud present at the ground level in the Jammu Kashmir area, which is very much significant from the spatial plots as well as from the atmospheric profiles. So that's why the Jammu Kashmir receives a much amount of rainfall throughout the year. Secondly, the humidity level. From the humidity level, it's not that much of distinct, but in the October and November month, you can clearly see that the humidity levels are getting higher and higher in the section. So this is the relative humidity, and this is the specific humidity profile. Otherwise, most of the season, it is quite constant. And this is again the observations that I've already discussed. So the final thing is the long-term trend analysis. So this is the most important slide of the presentation. So now you can see that December, January, and February month, you can see a slight change in the total precipitation sector. But when the December, January, February, we are only focusing towards the snowfall. This is the snowfall presentation, and in the snowfall, you can see a very sharp decrease comparatively, but it is equivalent. That is 0.0097 and 0.0013. In March, April, and May, there is a very sharp decrease in the rainfall pattern. Why? Because the snowfall in the March is heading towards the DJF season. That's why the decrease is very much evident over the area. Thirdly, in the October, November, you can also see a very sharp decrease, but most astonishingly, the June, July, August, and September, that means the monsoon season, there is a very sharp, not very sharp, it's a very inclined increase of the total precipitation, as well as you can compare it with the rainfall. So when we have classified the total precipitation into the rainfall and snowfall, we can have a very similar fall pattern. So this is all the statistical analysis that has been done in a 95% confidence interval, and we having a p-value of less than 0.025 for each. So that means the trend is very significant in the area. So finally, we can conclude that is a positive trend is observed in the JJA season, and rest of the all season, the negative trend is observable. In the 40 years, the snowfall trend has been getting very weak. And the most important reason is the concentration of the dust and soot particles over the Himalayan region, as my distinguished professors have already discussed in the session. And also the 40 years, the snowfall trend is getting because the western disturbance is also getting weaker and weaker, which has been analyzed by Dr. Charu Singh as well. So the extreme rainfall events in the evident, because now you can see the extreme events. When in the JJA season, you can see in the first part, the standard deviation is comparatively high. That means the extreme events were higher in this part. But now the extreme events are comparatively lesser in this part according to the data sets, which is a very important trend, and snowfall has been decreasing all over the year, but rainfall has been increasing. So that's it from the presentation, and thank you for the attention.
Questions, please. You can have a question or two. Okay, if there are no questions, please let us move to the next presentation. Next presentation is by Prashant Kumar Chauhan. He is from IGP and National Institute of Himalayan Environment, Kusi-Katarmal, and he will be talking about seasonal behavior of aerosol optical depth and black carbon in the northwest and central Himalayan.
Yes, am I audible, sir?
Yes, sir.
Yeah, Prashant, you can share your screen.
Hello, good evening, everyone. Myself, Prashant Kumar Chauhan, working as a junior project fellow under Dr. J.C. Knyal, sir. Here, my topic is seasonal behavior of aerosol optical depth and black carbon in the northwestern and central Himalayan region, India. Here, my working objectives are as follows: that is, to measure black carbon by using ethylometer and aerosol optical depth by sun photometer and solar flux with the help of pyranometer. Here is my this is my study sites. First one is Kosi, which is situated at headquarters of G.V. Pant National Institute, Almora, while second one is Mohal, which located at Himachal Regional Center, Kullu. Both sites are located in the valley and approximately same altitude. That's why I'm presenting comparative study of black carbon and AOD at Kosi and Mohal. Kosi site has its initial state, so I am comparing only 1 year data. As we know that aerosol is a suspended particle that is solid and liquid in the air or gas. According to their size, we can differentiate into three parts. First one is fine mode and accumulation mode, and third one is coarse mode. We can easily understand with the human hair picture. Fine mode and accumulation mode particles are respirable particles which affect the human lungs, while coarse mode aerosols particles are non-respirable. And natural sources of aerosol are volcanic eruption, dust storms, forest fire, etc. While anthropogenic sources are biomass burning, vehicular exhaust, and industrial exhaust, etc. Different equipments used during study period. First one is ethylometer, which measures black carbon at 880 nanometer wavelength. Black carbon is the carbonaceous component of particulate matter that absorbs all wavelength of solar radiation. Ethylometer is based on the optical method in which it measures the attenuation of a beam of transmitted light. And second one is pyranometer. It measures the solar flux in watt per meter square within a very wide wavelength range of 0.3 micrometer to 3 micrometer. It is based on the thermoelectric detection principle. And the third one is sun photometer, which measures the aerosol optical depth at 5 wavelengths. It is based on the Lambert-Beer law. And AOD basically the sum is the sum of the extinction coefficient multiplied by corresponding height up to top of the atmosphere. Here is my result. This graph shows diurnal variation of black carbon at Kosi and Mohal. Kosi shows unimodal peak, while Mohal shows bimodal with value 461 and 1600 nanogram per meter cube respectively. Mohal shows high concentration of black carbon due to the high anthropogenic stress and also located at near national highway. This graph shows seasonal variation of black carbon at Kosi and Mohal. In winter season, boundary layer downshifts due to low convection at both sides, figure A and C. And wood bunding also the reason in winter season. That's why concentration of black carbon is high at both sides. While in summer season, due to high convection, boundary layer occludes and one reason, and other is lockdown period also played the important role in summer season also, due to which vehicular emission was found very less at both sides. That's why only Kosi has average concentration of 1100, while Mohal shows 5000 approximate nanogram per meter cube black carbon. This graph shows relation between DC diurnal variation of BC. During forest BC during forest fire days at Kosi. In winters in 2019 this graph shows concentration of forest fire black carbon during forest fire days at Kosi. Kosi site is surrounded by pine trees. That's why forest fire events generally occur in summer season. In 2019, forest fire occurred in a very frequent manner. Due to forest fire, maximum concentration of black carbon is to be 7,000 nanogram per meter cube, while in 2020, very less intensive forest fire occurred, in which approx 2400 nanogram per meter cube concentration of DC. In 2019, major role played by biomass burning, as we shown in graph B. While in 2020, fossil fuel played an important role.
Prashant, you are left with 3 minutes.
Okay, sir. This graph shows relation between black carbon and solar flux. There is an inverse relation between black carbon and solar flux. As I told in previous slide about boundary layer movement, we can see here also that when solar flux is high, then concentration of black carbon is less, and when intensity of solar flux is low, then concentration of black carbon is more. Average maximum solar flux is 814 watt per meter square at 11 a.m. in the month of May. Here is the this graph shows aerosol optical depth at Kosi and Mohal. In this graph, overall average aerosol optical depth at 500 nanometer was observed to be 0.4 at Kosi, while 0.34 at Mohal. It shows that AOT decreases as wavelength increases. The solar radiation of a particular wavelength is attenuated by the aerosol of size equal to that wavelength. So large AOT at a particular wavelength means the aerosols of that size are present in large number due to vehicular emission and wood burning, etc. And this graph shows seasonal variation of aerosol optical depth at Kosi and Mohal. The AOD is high due to high degree of human interferences like tourism activities in summer and external dust transport events from the countries lying in the northwestern part of India during pre-monsoon period. So that's why the reason. This is the air mass back trajectory. This is a concentrated weighted trajectory. This is a receptor-based method for air mass. This is a 7-day back trajectory. Long range transport mostly came from south, west, and northwest. And higher concentration of air masses are from local sources. And this is the summary of my presentation. Diurnal variation of black carbon source biomodal distribution pattern at Mohal, while unimodal at Kosi Katarmal. AOD is wavelength dependent, higher at shorter wavelength and lower in longer wavelengths. And western long transported at air mass play an important role in influencing the aerosol buildup. Thank you so much.
Thank you.
Done.
Yes, sir.
And your AUD at 500 nanometer is high. And then our after that it is decreasing, and before in 450 it is decreasing. Why it is 500 high?
Sir, it's because of due to concentration of that size particles matters. Due to size of 0.5 micron particles exist in large manner.
Now, why it is reflecting only in 500 nanometer? This is a microtop AOD, right? MWR AOD.
Sir, here microtop AOD.
Microtop AOD.
Yes, sir.
And second question, and your black carbon you have shown for Kosi Katarmal and Mohal.
Yes, sir.
You are getting two peak at Kosi as well as Mohal.
Yes, sir.
Why? Because in the hilly region, generally we are getting one peak, that is in afternoon peak.
Sir, at Mohal, Mohal is that site is situated near the national highway. One of the reason of second peak, and other one is boundary layer. Boundary layer also plays the important role. That is downshift at the after the noon period.
So I think we can continue the discussion later. We can personally discuss with Dr. Deoka. So thank you for your presentation. Now we move on to the next presentation.
Thank you.
And the next presentation is by Samir Mishra from NED, CSIR lab. He'll be talking about a statistical modeling of particulate matter using ANN techniques over Indo-Gangetic plain using satellite AOD and meteorological parameters. Samir Mishra. Samir, are you able to listen to us?
Hello.
Yeah.
Am I audible?
Yeah.
Yes.
Please go ahead with your presentation. Can you share your presentation again?
Samir?
Yeah, I'm just sharing it, trying to share it. Sir, it is not visible on my screen. Where it is?
you click on share screen and then find it out on your computer. Yes.
Yes.
So has it been shared?
Yes.
Okay, let me start, sir.
Yes.
So, hello everyone. Good evening. I'm Samir Mishra, and I'm working at NIAS ISC campus, Bangalore. And the work which I'm going to present is my dissertation work 2 years back that I had done. That is statistical modeling of particulate matter using artificial neural network techniques over the IGP, using the satellite AOD and meteorological parameters. The outline of the agenda here, it would be the air quality background in the.
Samir?
हाँ sir, please.
Can you slide mode?
Yeah.
Okay, thank you.
And try to keep in 7 minutes your presentation so that we can have 3 minutes for discussion.
Sure, sure, sir. So the agenda is that the objective I would be giving, then methodology, the two statistical approach which I have used in this work, MLP as well as MLR, the outcomes, results, and the future perspectives. So starting with the air pollution and the overview. Air pollution is a series of events as we have been discussing for the last one day, and we'll be discussing tomorrow as well in this very good informative gathering. So the air pollutants are done that deals with the pollutant sources. The very important thing is the site of generation, their transportation, as well as the removal from the atmosphere, and also their impacts on the human health, biotic as well as abiotic components, which is very crucial to the environment and the ecosystem. And today's topic also, which is dealing with the Himalayan fragile system and their livelihoods. So source is very important. There are three types: point, area, and linear. As we see in the Chak Stimney Heights, they are the point sources. Aerial sources, like if we call about the whole industrial area, MIDCs, they are the aerial source. And the line, as we see in the Bangalore where I'm sitting, the linear sources are the biggest problem here. So what do satellites do provide? How can they join the dots of the missing data sets today? And of the data sets missing of what? Of the in situ monitoring. That is the overall networks of the ground monitoring station, what is called as AQMS. So what is AOD? Optical properties which we have discussed throughout the day, so I won't be going on AOD. I would just show the AOD ranges that start from 0.1, 0 to 1, and a very clear sky would be 0.1, which would be the least side, and the greater would be the visibility should be 0 over that side. So what are the remote sensing procedures? As I have taken as a satellite measured spectral radiance, and it goes in a final product, which is used as a institute like ARIES or any institute like the think tanks of the India, which would be giving a policy interventions. So talking about the AOD column, just I would show a pictorial, which would be much easier for you all to see. I'll highlight the downwritten text, which is everyone is exposed. Exposure varies over space and time. That is spatio and temporally. That is the word which is commonly used in this webinar as well. And this conference, sorry. Quantifying the exposure is a challenge due to the lack of monitors, potential misclassification of the exposure, which is like we are saying that the whole bulk is containing PM 2.5, or the whole bulk contains a sulfate, that can come only if we do the gravimetric analysis. And there are many other factors which control it. So the objective to extract and obtain AOD values from the 550 nanometer aqua modis, and we have been dealing with 550 nanometer aqua modis throughout this whole conference. So the same thing I had taken, and I had taken in synced data of ground monitoring station, that is CPCB stations, matched it to the local time to establish. Second is establish the relation between both PM 2.5 and the AOD 550. And also to derive a relation between concentration and the MET parameters, because they are the most important influencing thing, which can dilute, diffuse the pollutant concentration at a certain level. And I had used two statistical approach, which is MLP, multi-layer perceptron, as well as multiple linear regression. So just to give a look out, it's very important to show what kind of studies had made me to work upon this. So these are just a study that methodology they had been using as regression. Somebody used linear regression, but now they are moving towards the non-linear modeling approach. That even back propagation we had seen in this conference, people been using. Yesterday, Dr. Khatri has also showed a very beautifully algorithm how they are showing. And the variables what here I used are like in the cases you see, and in India also a lot of studies now they are focusing here. Materials which I had used are the, as I told, satellite data, modest level 2, 550 nanometer from January 2017 to December 2017, the whole year. The ground monitoring CPCB for the Indo-Gangetic plain cities, which I have chosen, which I will show you just in the next slide. And the Berkeley Earth is a gridded data, reanalysis data that we also call MET parameters, which is available from the micromet stations that CPCB includingly gives, and wherever it doesn't give, lots of gaps are also there. So there I used with other underground gridded data. The software that used was Python, ArcGIS and all. So this is overall the area, a synoptic view, a bird eye view, you can say, of the Delhi, Kanpur, Varanasi, Patna, Kolkata. And this is the region, the population. You can see the NCR being the highest in the population, Kanpur with exceeding Varanasi with some, this was the last census of 2011. So the CAM station, I should also focus here. The continuous ambient air monitoring stations, which are in Delhi, are 6. At that time, it was 6, and Kolkata and all, as you see. This is my methodology. The methodology starts from the data collection. We have, I have been using secondary data. So nowadays, it is the ground truthing is very important. So first procedure comes as data collection that I did for this CPCB, then satellite from models that has already I told there are 2 products, 3 kilometer as well as 10. Now MAYAC is also available, 1 kilometer, but I used the 3 kilometer, and the data measurement, then the sorting, taking out different weather variables, and then outlier removal, and then the model development, which I told you that MLR and MLP model to estimate the PM2.5 concentration. The data on the right side, you can see the level of the hierarchy. What is MLP? Actually, it is the multi-layer perceptron. Perceptron is a very old term, which means to perceive, but the neural network architecture to regression are now readily used in the air quality forecasting. The hidden layers that symbolizes that are in the tangible forms, and they are very important in deciding the network architecture. So coming to the
3 minutes.
Yes, I will be moving quick. So this is the input, hidden, and output layer. So I would quickly give up on the what this matrix says. This is a schematic diagram, but in the model, this kind of parameters on the left side, the neuron networks, the architecture, and the output goes like this. Statistical approach often requires a large quantity, and any retrospective data, historical data, can be used in this kind of learning, artificial learning methods. This is the spatial interposition I used here was IDW, inverse distance weighted. So this you can very easily see here PM2.5 values which were exceeding at the Kanpur, near about the 164 to 197 range. And on the right side is the AOD. This is just an overview of what AOD and PM2.5 I got on a specific location. The R correlation values were found to be within the range of 0.2 to 0.4 for the MLR, which showed weaker, that was a weaker significance level. So a good fit model was MLP, which I will show in the next slide here. MLP output showed a better significant R values ranging from 0.8 to 0.9, thus a better fit. So this is the predicted versus observed graph of Varanasi region, predicted versus observed for Kanpur. And the R is 0.85, R is 0.8, and at Varanasi, R is 0.44. So conclusion I would draw here, the MLR ranged from 0.2 to 0.4, and MLP showed between 0.8 and 9. Significant R values are better fit nonlinear modeling. So in air quality datasets, we have to focus for nonlinear modeling. As I showed here, the study has approached using two approach. Using a nonlinear multi-regression incorporates both remote sensing as well as ground mounted measurements, and generally the model didn't competitively reflect wide temporal because the data set I used was only for 1 year. So if a robust model we require, we have to work on a larger temporal data set. So the current scenarios and the future outlook, I would like to end with that the Himalayan hills that are very fragile and sensitive, and the plains are not only rich in alluvium, but the densely populated cities since ages, as it has been during the river valley are highlighted due to the degrading air quality. And thus the life standard of the people, either old or either sensitive groups, are getting diseases. So moreover, these clusters have highly operative TPPs, thermal power plants and industrial setups in the background of every city that have worsened the air quality. But the meteorological conditions are only restricted, the setup of these AQMS stations are only focused on the urban clusters. So similar scenarios have been favored in the IGP cities post-September. Every year we see after the post-September months, these 5 cities are highlighted. There are a lot of hue and cry is there. And so last line, we still rely on the conventional methods of monitoring source apportionment studies to estimate the share of the various pollutants, which takes time and a lot of resource. So satellite observation using machine learning could be a boon for the restricted field visits. Like now, nobody is able to go to any fields nowadays. So it can save the money also. And for the think tanks, for the policy, and it could be a good and robust model. Thank you so much.
Thank you, Samir. So we can have a quick question. If there is a question, please. You have a question?
Yes.
Please, Samir. Yeah, by the time you can share.
Hello. Yeah, I can listen.
Okay, Samir.
Somebody else is asking.
This is Atul.
Okay, Atulji, go ahead.
So have you checked what are the uncertainty in your model?
The uncertainty levels in my models, like if I was using MLP, using multilinear regression, the biasness was a bit high. So that is why I started using MLP, which was giving me lesser biasness. And so it was giving a result of 0.05. So that was my biasness.
Okay.
Okay, thank you. So next speaker is from Gurukul, Mahima from Gurukul Kangdi Vishwavidyalaya, Haridwar, and she'll be talking about statistical analysis of seasonal variation of solar radiation and meteorological parameters in the Himalayan region. So I would request.
Yes, sir. Yes, sir. I'm audible, sir.
Yes.
So your presentation is being shared from our end. So
yes, sir.
You just have to say next, and I think we'll be able to browse from here.
Okay. Can I start, sir?
Yeah. Go ahead. Keep presentation. Try to complete in time.
Okay, sir. Thank you, sir. Good evening. Good evening to all of you. Thank you for giving me this golden opportunity to present my work. The topic is statistical analysis of seasonal variation of solar radiation and meteorological parameters in Himalayan region. Next, please, sir. These are the outlines of my present investigation, which is used in this study. Next one, sir. Solar radiation. If we're talking about solar radiation, the main source of solar radiation is sun, which emits the electromagnetic energy. It is known as short wave radiation. Solar radiation comes in many forms such as visible light, radio waves, heat, infrared, X-ray, ultraviolet rays, etc. And the given figure shows the different components of solar radiation. The solar radiation received from the sun after its direction has been changed and scattering by the atmosphere, which is called diffuse radiation, and the radiation which is received without scattering and reflecting is known as direct or beam radiation. And again, at any place, the sum of direct and diffuse radiation is known as global or total radiation. Why we need the solar radiation data? Need of solar radiation data for different applications such as photovoltaic, solar thermal systems, and passive solar designs. Next one, sir. In the present investigation, used only two meteorological parameters, temperature and relative humidity. And to check the accuracy of data values, we have used three types of statistical parameters. Standard deviation. Standard deviation quantifies the amount of variation of set of data values, and uh, equation first gives the formula of standard deviation. In this formula, where x is the sample mean average and x bar is the mean value of the observation and n is the number of observation. Next is kurtosis. Kurtosis shows that the degree of peakness or flatness in a curve, and it can be seen that from the given equation. Next, skewness. Skewness is a measurement of symmetry. Uh, the given formula shows that the present in the present slide. These are the description of site we have choose in my present investigation. The information of solar radiation of a region from climatic change point of view. The satellite derived data used in this study over a period of 6 years from 2013 to 18 at 3 stations of Uttarakhand. The table shows the geographical summary of the selected sites in this study, and also given shows the location of selected sites in Uttarakhand map. Next one. Uh, Analysis of temperature for Gopeshwar, Nainital and Pithoragarh location. This talk represents the outcome of statistical investigation carried out on global solar radiation meteorological parameters like temperature and humidity. The seasonal average data from 2013 to 18 of three selected sites in Uttarakhand. Table shows the seasonal average data values of temperature and three locations, and the given figure shows the variation of temperature with seasons. It can be seen that from the given figure, the maximum amount of temperature is found for summer season for Nainital location, while the minimum amount of temperature is found in the winter season for Gopeshwar location. It can be seen that from the given figure. Next one, sir. Now it's the statistical performance of seasonal average temperature for the selected location given in the table. Given in the table, and its graphical representation given in the figure. The maximum deviation found for the Gopeshwar location in spring season, while the minimum deviation found in the monsoon season. Kurtosis is less than 3 in all seasons, so the distribution is platocrutic with negative values. It can also be seen that from the given table, the negative and positive values of skewness shows the left skewed or right skewed respectively, and also the negative and positive values shows the underestimation and overestimation of data values. Next one, sir. Similarly, the analysis of relative humidity table shows the seasonal average data of relative humidity and its data values. The graphical representation present in the given figure. The maximum humidity found in the monsoon season for all the chosen sites. It can be seen that from the given figure, and the minimum humidity found in summer for Nainital location, which is less humid in comparison to other chosen location. Next, sir. Statistical performance of relative humidity. The similar study of relative humidity for statistical parameters. Uh, it can be seen that from the given table and figure, it is similar to the previous slides. Next slide. The main part of my analysis is analysis of global solar radiation for Gopeshwar, Nainital and Pithoragarh location. The seasonal average of global solar radiation data has been performed in the given table, and its graphical representation given in the given graphical representation are shown in the given figure. The highest amount of solar radiation was found for Nainital in autumn season, while the lowest was found in winter season for Gopeshwar location. Nainital location shows the good amount of solar radiation in comparison to Gopeshwar and Pithoragarh location, which is depend on its weather condition and as well as its climatic conditions. Next one, sir. Now, the statistical parameters also calculated for solar radiation, and the data values of statistical performance has been shown in the given slide, and it can be seen that from the figure Gopeshwar and Pithoragarh shows the approximate equal distribution in all the seasons, while Nainital also shows the similar distribution. Similar distribution respectively. Standard deviation for autumn season due to the variability of climate change and its weather condition. The maximum and minimum amount of standard deviation, kurtosis, and skewness can be seen that from the given table. The data values are shown in the given table. Next. These are the main conclusion of our study. This type of study will be very beneficial for the performance analysis of different solar energy appliances. The best way of knowing the amount of solar radiation at any site is to install the sensitive measuring systems at many locations in a given region and to monitor their day-to-day recording. Even global radiation data, which has many applications like engineering systems, designs for solar energy collections and storage, evaluation of performance of solar energy utilization systems. The performance evaluation of data analysis has been confirmed by using three statistical parameters which are used in my study, and to check the accuracy of data. Throughout the study, observed that the weather conditions for any particular site is very helpful for the analysis of hourly, monthly, annually, and seasonally variation of global radiation and meteorological parameters for any particular stations with many time periods. It is very beneficial for the solar tracking systems and also for solar water cooler and solar systems. In near future, plan to similar analysis for ground-based data of solar radiation and with comparison with aerosol and other meteorological parameters also collected from the NREL, NCDC, and NSRDB and India Meteorological Department Center. Thank you. These are the references which is included in my study. Thank you.
Take one quick question because we have 1 minute.
Yes, sir.
Is any question?
Mema,
Yes, sir.
from where you got this solar radiation data?
Yes, sir.
From where you got this solar radiation data for Nainital?
Yes, sir. It's a satellite based data.
And then why you are getting that solar radiation is very high in post-monsoon season, autumn season?
Yes, sir. It's depend on the weather condition of that particular site.
Okay, thank you.
Okay, sir. Thank you, sir.
So we move now. We are left with second last presentation of this session. So next speaker is not second last. We have 3 presentations. So next speaker is Mahinder Chand Rajwar. And he'll be talking about the diurnal and seasonal variations in some non-methane hydrocarbons over Nainital, the central Himalayan site. Share करनी पड़ेगी screen. ये बस.
Full screen.
F5 नीचे लगा ये वो है.
क्या PDF है क्या?
View.
F11 हो जाता है इसमें.
Full screen. Control L.
So,
okay, Mahendra, you can start.
Respected all, my name is Mahendra Chand Rajwar. I'm a research scholar in ARIES, and today I'm coming with a presentation titled Diurnal and Season Variation in Some Non-Methane Hydrocarbon over Nainital, which is a representative site for the central Himalayan region. So first of all, the introduction. In the introduction, non-methane hydrocarbon are basically the primary pollutant in the Earth atmosphere. They play an important role in the ozone photochemistry, and they are also the precursor for the SOA, that is a secondary organic aerosol formation. And they also affect the oxidation capacity of the atmosphere by reacting with the OH radical. This block diagram or cartoon diagram showing the
role of non-methane hydrocarbon in the complete cycle of the production of ozone. And here I'm also showing as a plot diagram. Here red plot is without non-methane hydrocarbon contribution, and green plot showing the contribution of the non-methane hydrocarbons. So we see in the ozone production is more in case of the containing the non-methane hydrocarbons. This is our sampling site, Nainital site, where we took the sample, and this is a gas chromatograph which is used for the analysis of these non-methane hydrocarbons. So basically, I'm starting with the diurnal variation for the non-methane hydrocarbon over the Nainital site. We first time observed the diurnal variation of non-methane hydrocarbon over Nainital Central Himalayan site. And we observed the two different kind of the diurnal pattern. First one is the noon time high, and the second one is the bimodal variation. In the second yeah, actually I'm okay. So so first kind of here we can see in the noon time high value of the mixing ratio of the non-methane hydrocarbon, whereas here we see the two peaks over the side. This is termed as the bimodal distribution, or this term as a unimodal distribution. These species follow this kind of bimodal distribution, whereas these are the highly reactive species which follows the one unimodal distribution. Whereas the seasonal, if you see the seasonal variation of the non-methane hydrocarbon, we see the clear seasonal variation in all the BTX, that is a benzene, toluene, and ethyl benzene, xylene species, whereas a lower non-methane hydrocarbon species showing the clear seasonal variation. If you see the seasonal variation of the lower non-methane hydrocarbon, it has tendency to the maximum mixing ratio over winter or springtime, whereas in case of the BTX species, it's so the tendency to the high autumn time and high autumn time tendency. Whereas apart from this, we compared these results with another IGP representative site, which is a semi-urban site nearby Haldwani, that is Kathgodam. And what we see the contribution of different non-methane hydrocarbons over Nainital site and the Kathgodam. But when we compare, we see the equal, almost same kind of variation or percentage proportion over over both the side. But in case of the autumn time, we over Nainital, aromatic compounds shared more proportion as compared to the other alkene or alkyne elements. Or if we in numbers, if we compare the contribution of non-methane hydrocarbon over Kathgodam and Nainital, almost 2 to 5 times the concentration of non-methane hydrocarbons is as compared to the over Kathgodam as compared to the Nainital side. Apart from this, we are doing some photochemical modeling work using the NCAR box model, because to know the various different kind of the photochemical processes involved in the photochemical production of ozone. So we first simulate the general semi-urban site diurnal pattern for the ozone, and what we first we try to check what is the NOx, that is the effect of the oxide of nitrogen over the diurnal variation. So we see if in the low level of the NOx, we not getting any photochemistry, whereas if we increase the NOx level, we are getting the strong photochemistry. So such kind of these kind of the plots or these kind of the profile for the ozone we are observed at the Nainital site, and such kind of the and high NOx level we can observe at the semi-urban or urban sites. So in the same way, we are obtaining some photo production ozone production rate for the semi-urban sites, and to quantize the role of different mechanisms in the ozone production. Is the upper side show the normally total production interstitial production of ozone, whereas the L is represent the interstitial loss of ozone, whereas the this green shaded region is represent the total net ozone production. So we have seen such ozone production over this semi-urban site. So for different reactions or different mechanisms, we quantize the contribution of different reactions here. So we see the H. The first reaction is very dominated, which is can be taken from the non-methane oxidation products of the non-methane hydrocarbon and other methane species. So we are just trying to find out the role of different non-methane hydrocarbon groups in the ozone production. We switch on and off the corresponding non-methane hydrocarbons. So we see the different production rates were observed for the different class of non-methane hydrocarbons. So here, if you see, the aromatic compounds have the predominant role in the ozone production, and these are apart from this anthropogenic sources. We are also trying to observe the biogenic sources over higher Himalayan sites. So you can, yeah, thanks for this.
Okay, thank you, Mahinder. So we can take a few questions, couple of questions. There are questions, please. Mahinder, I have just simple question. You told that there are, two kind of species. One is having bimodal and other is unimodal. But then some of the, curves are not showing bimodal.
No, actually, we are doing the, these are the primary results. So
means they have already characterized that they will always show bimodal kind of.
Yeah,
And we are not somehow able to observe.
Maybe in seasonal we're getting. So we quantize the if there is seasonal change, because first time we just observed here, so we cannot say completely comment on that.
Right. So some atmospheric chemistry has to be there.
Okay.
To look into.
Okay.
Yeah.
Thank you.
May I also ask a question, please?
Yes.
Dimitris, please.
Yes, very nice talk, even if briefly, and try to limit the time schedule. So there was not so much explanation, or so my question is about different seasonality of the maximum values of different non-methane hydrocarbons, like aldehydes and alkanes and aromatic hydrocarbons, that, if I remember well, I have seen a slide before, each of them maximized at different time period. Can you an explanation about this exactly, a brief explanation about what is happening about this different seasonality of the different kinds of non-methane hydrocarbons?
Okay. So in the winter and other, apart from if we exert the autumn season, or if we compare the winter, spring, or summer seasons, because alkanes are the more less reactive, they have the large lifetime. So when because on Nainital side is a remote site, so here not a strong anthropogenic sources. So pollutants are coming from the IGP region. There are the near IGP regions. So those species which are highly has high lifetime, they can be uplifted here and contribute to the more accumulation over this site. But in case of the less reactive species, it reacts or diluted within the path from this emission source and to our receptor site, Nainital. Yeah.
Okay. Thank you.
I think we can exchange more views later because Professor Kaskotis is always available for discussion. Thank you, Professor, for asking questions. So now we move on to the next presentation, and this is by Sunita Verma from IESD BHU. She'll be talking on aerosol optical depth during fire events in Uttarakhand state using satellite observations. So over to Sunita, please go ahead with your presentation.
Good evening, everyone. So am I audible?
Yeah.
So today I'm going to talk about the aerosol optical depth during fire events in Uttarakhand state using what is satellite observation. So this work was largely done by Harshvardhan Kumar, who was my MPhil student. And this is very preliminary right now, but because it was associated with the Himalayan region, so I thought to show this rather than other work. So thank you for giving me opportunity to present my work, Professor Umesh Tunka and the conveners to stay back till late. So this is the overview of fires in India. We know that forest fires in India are both widespread and concentrated. And every year there is a forest fires, which is around the half of the century, 647 districts. And it covers around 47% of the Indian forest. So if we look at the graph, we can see that the active fire detection is pretty low, but then the burned forest area between 2003 to 2016 is very huge in number in central India and to the IGP regions as well. So this is the study area, which is Uttarakhand, and it is located in the foothills of Himalayan mountain ranges. It is largely a hilly terrain, the upper portion, with a smaller plain in the lower, winter extremes, and with a snowfall in the upper portion, and temperature below 5 degrees also reaches. So for this study, we have used the active fire points from the VRS, it detects the fire based on the brightness, temperature, and thermal anomalies. Then to corroborate the AOD, we have taken the MODIS C6 version dark target deep blue algorithm. Then we have taken this to characterize the spatial temporal distribution of aerosols. And to know what level these aerosols are reaching, we have used the vertical profiles based upon Calypso level 4.10. And we have also used the back trajectories to see the transport of pollution coming out from these fires, which are huge. So this figure shows the active fire points retrieved over the entire Indian domain for the duration of January to June in 2018 and 19. As you can see, the red dots here represent the active locations of fire at a confidence of 80%. The special variation of these fire points show that the fire locations are widely dispersed throughout the India. And from April to May, there are a large number of active fires, as you can corroborate from the figures over here. And more fire points are actually, you can see these figures are in April and May around 710 points for 2018, while for 2019, it is more concentrated in the month of May and June. So this is the figure which shows the spatial temporal variability of aerosols and the monthly mean from the MODIS satellite data. And it shows the high AOD over mid and upper region of Uttarakhand. And the figure also, if you can see, the figure clearly depicts monthly MODIS AOD, which is having a higher values, about 0.6 to 0.67, which is a huge number again for the fires time. This again shows the AOD for the duration of January to June, and you can again see here that May and June has a large number, and there is a drastic increase in the aerosol loading in the month of May, which is again attributed to the intense forest fires over the region. While for the June month, it may be due to the lasting impact of the forest fire emission. For size segregated variability, we have also analyzed the Ozone exponent, which is shown in the figure below. The graph here clearly shows that mid-region has a relatively higher finer fractions, about 1.2 to 1.88 Ozone exponent values, while in the southern plains, A ranges from 0.35 to 0.7. So this corroborates the fire events. For the vertical distribution of aerosol, we can largely see here, as the daytime profiles, we applied the basic filtration to remove large uncertainties. And the mean extinction profile on 5th May, you can see here, it shows maximum extinction up to 1 kilometer, while for the 31st May, which is also shown here, it shows the sharp extinction at 3 and 5 kilometers. So the aerosol are actually reaching at the height of around 3 to 5 kilometers, which is corroborated by the Calypso observations during that time. And if we look at the forward trajectory to see that where these fires are actually forwarding into, and you can always see that this is going into the northeast, Nepal, and also touching the northern areas, more on the northeast areas. So here we can conclude with this preliminary exercise that there is an active fire detection can be done through the satellite data, which is a very important tool to study these fires. Then spatial distribution of aerosols from the satellite reveals there is a higher EOD, which is recorded in the southern and the mid-southern district of the study region. While the temporal distributions of aerosols over the region shows a progressive increase in aerosol loading in May and June month, and the mean extinction profiles during the episode say that there is a maximum extinction from the surface to altitude of around 1 kilometer, while for the other day it shows around 3 kilometer and 5 kilometer. So it may be due to the lasting impacts of the emitted pollutant which are trapped at these altitude. Also, the forward trajectories reveals that probable sink zones for these elevated levels of fires could be Bihar, northeastern states of India. Thank you. So I'm leaving some time.
Thank you, Professor Verma, for your nice presentation. And now the session is open for discussion. We can have a couple of questions.
Hello, Naren sir.
Yes,
can I ask a question?
Yes, please go ahead with your question.
Good evening, ma'am. Actually, it's quite interesting. So I want to have one query regarding to the angstrom exponent.
Yeah.
What is the wavelength band for the angstrom exponent you used in this study?
Actually, the Angstrom exponent, this is a very good question because it should range from 440 to 880 range, but because we've been using the MODIS satellites, this is quite not very good product to use for the distinguish of the size. Here it is around 580 nanometer or something like that. So, but this is a good question because yeah, this is not a good product to use for the size segregated aerosols.
One more thing, did you perform any meteorological analysis like a convection to evaluate the uplifting of aerosol over the region up to 3 kilometers?
Right now, we are actually extending this work for the 10 years and we're trying to see how the evolution of fires have occurred from past 10 years. And then probably we will take up your suggestion as a suggestion to include this. But for now, we have seen the winds role in it, but not the meteorological parameters. We could see that these are uplifted to around 3 or 5 kilometers range, but we have not done that for now.
Thank you.
Professor Verma, I have just one query. How many observations of Calypso have you analyzed where you find that these transported pollutants are reaching up to say around 4.5 kilometers in the Himalayan region?
I don't remember right now what exactly the points, but yeah, you know, the Calypso has a time span of around 7 days. So it has a very less points available on the Uttarakhand region. So yeah, we have a very less points, but right now I do not remember the number of points which we have observed. But they were very less. They were quite less.
So there are some questions on chat, posted on chat. So we'll forward it to you for further clarifications, or we can take one question from Rohini. I think let us we can read it out. There is one more question to you. What about the contribution from dust during May and June? It was asked by Rohini from Pune.
We have not analyzed the dust contribution, but it must be a good point to look at what could be the contribution, but here the major aim was to look at these fires and the AOD during these fires. So we have not looked at the fractionation of the aerosols and the contribution from the various components. We just largely seen that if the satellites could be able to detect the AOD during fires.
Thank you, ma'am. Thank you for your presentation once again. So we move on to the last presentation of this session, and that is by Avinash Chandra Yadav from Indian Institute of Tropical Meteorology, Pune, IITM Pune. So he'll be talking about monthly PM10 concentration patterns over Delhi, a remote sensing perspective. So I would request Avinash to please make your presentation. Ma'am, can you unshare your presentation? Oh, okay. Avinash, are you there? Avinash, I don't know. No.
अविनाश नहीं होगा, इसको प्रेजेंट करने वाला दूसरा है.
अच्छा, कौन?
क्या नाम है? कुछ चौधरी.
Is there anybody from IITM who is going to present on behalf of Avinash Chand?
पार्टिसिपेंट लिस्ट में जाइए और बता देता हूँ, है नहीं है.
चौधरी का बैठो.
कोई चौधरी है.
नहीं. So I think the last participant himself have left already because the session was little delayed. So I would like to thank to all the participants from connected through remotely or on this virtual platform, and those who are present here. So once again, thanks to all speakers and the chairman and co-chair of the morning session, Professor R.C. Ramola, and everybody else who has contributed in this session, all the sessions since morning. So thank you to all, and I would say Dr. Alok Sagar to, if he has something to comment before closing our today's session. So thank you once again for listening all presentations presently, and we'll be back tomorrow in the morning.
Yes, boss.
At 9. Thank you all.
Okay, thank you.
Have a nice evening. Bye, guys.
Lumka sir.
यस आलोक बोले.
सर इसकी मॉर्निंग की इवनिंग की